That's what I'm telling you.
तो स्विच क्या करना है?
क्या?
सर उसका माइक्रोफोन का इश्यू है, उसका ऑडियो कैसे है? माइक्रोफोन ही नहीं पता नहीं चल रहा है या नहीं चल रहा। सर यहाँ से टेस्ट कर लेते ना,
यहाँ से कर लो ना,
कोई एक लैपटॉप लेके यहीं से टेस्ट
सर
कर
मोबाइल से
डजंट मैटर रिमोट है कि कहाँ से।
आपने कनेक्ट किया मोबाइल पे?
मेरा है मोबाइल।
हाँ तो इसमें बात करते थे ना, एक सेकंड बोलो।
सर MOS is in waiting lobby.
ये
ले लूँ?
हेलो.
हाँ
Bangalore, we are not able to hear you. Okay.
Are you able to hear me, sir?
This is Bangalore or okay, Bangalore only, na?
No. This is Delhi, sir. Delhi MOS.
Oh, MOS office. Yeah, sir, we are able to hear you.
Okay, now 1 minute. कैमरा मैं सेट कर दे रहा हूँ.
Sir, can you present something on your screen? Hello.
हेलो.
Yeah.
Just 1 minute. 1 minute. Sir.
Yeah.
Give me 1 minute. Sir. विमल भाई.
जी. हाँ वो कुछ प्रेजेंट भी कर रहा है. हेलो. MOS office.
Yes, sir. Yes, sir.
Your camera visibility should be centralized. It's not visible.
Now
Yeah,
it's
now
good,
now
sir.
it looks to be better.
नहीं ये वाला इधर से ये इधर से आने वाला इधर अभी रुको टेस्टर मारो ना ये हो गया टेस्टर
Namaskar. Suprabhat. Good morning. I request all to kindly be seated and keep the mobile phones on silent. We will commence the symposium shortly. Hello and welcome everyone. A very good morning to all of you. We are delighted to have you here with us today. I, Shravani,
And I, Nikhilesh,
on behalf of entire C-DAC fraternity, cordially welcome all the distinguished guests, invitees, and attendees to this symposium on quantum computing ecosystem. C-DAC has organized this symposium to explore the technologies, systems, and subsystems that make the building blocks of quantum computers. The symposium aims to bring together all the players, both Indian and global, working in the areas of quantum computing.
these two-day symposium will feature a variety of talks, panel discussion, and breakout session on the focus areas of superconducting and photonic-based quantum processor, control and measurement electronics and calibration, dilution refrigerator and SNSPD, quantum processor technologies, software stack simulators, integrated HPC and quantum computing platform, their benchmarking and validation, quantum algorithm and error correction, and emerging Indian quantum computing roadmap. We also have stall exhibits from the quantum technology industry partner for this symposium. To commence the symposium, we are extremely privileged to have Professor Barry Sanders from University of Calgary, Canada, for the keynote talk. Professor Barry is connected with us live. Over to you, sir.
So you're on live. Barry, sir.
Hear me okay?
Yes, we are able to hear you, sir.
Okay, good. I put in AirPods for better sound.
So you can start now.
Oh, I don't see my slides. Do you go through the slides? You're talking about me to start?
So you can upload your slides, or you can share your screen as well.
I was told, is Anandita there? She told me to send the slides and you guys would do that.
Okay. So we will share your slides from here only.
I don't understand. I was told to send my slides and then the slides would be handled for me. That was my understanding. If
So
you
we are
need me
sharing
to
your
show my
slides.
slides. Oh, you see them now, do you? Okay. I see the big screen. I see you're now about to do it. So I'll wait till my slides show up and then I'm happy to start. Okay.
So we have shared your slides. Are you able to see it?
Thank you. Okay. I see it. So you want me to start no introduction or anything? Is that the idea?
Yes, sir. So we have already had your introduction just a few minutes before. So you can start now with your presentation.
Okay. Thanks very much. So it's a real pleasure and honor to be presenting here to this conference. And I'm sorry I'm not there in person. I was visiting in Pune a couple of months ago or 3 months ago. So I'm glad I had a chance to meet that team. I decided what I'll talk about is really, I'll have one slide on my own research, but this slide is really to paint a picture of what has become probably the most important issue for using quantum computers in the near term. And this, I'm just calling this quantum data science. So data science is a big field of research. It's had dramatic impact. So has quantum physics. And quantum data science is really about the issue of what can quantum do to enhance data science. It's also got another side, which is what can data science do to enhance quantum, like machine learning techniques applied to quantum, building quantum computers. I won't go into that side. I'll just talk about how quantum computing impacts on data. Can we go to the next slide, please? Hello? Thank you. Okay. So first, just to be clear, this one slide is, sorry, is somebody speaking? I hear other people speaking. There are other people speaking. I'll continue when other people are not speaking, if that's okay. It seems to be okay now. All right, so this slide is really about, just captures the essence of the nexus, the overlap between quantum computing and data. In that first icon below the orange icon, you can see that I refer to the essence of data science. It's about capturing, maintaining, processing, analyzing, and communicating data. And I'll elaborate that more in the next slide to talk about what each of those are and how quantum computing, a little bit about how quantum computing can impact. Quantum computing is a difficult topic to convey briefly, but it's about replacing the binary information representation and Boolean logic that we build all of our computing on by quantum versions. So we replace binary information by superpositions of bits, and we replace information processing and Boolean logic by quantum information processing. And then the goal of the quantum data nexus is to radically transform aspects of data science by exploiting potentially disruptive capabilities of quantum computing. So what we think about here is we have to analyze the aspects of data science and then look at what the targets are that would benefit from applying quantum computing. And the field is very important right now because there's a number of firms, both large and also startups, that have developed quantum computers of various capabilities. They're available commercially, and there's also software frameworks being developed, and all of these are, really the time is now to think about if, when, and how quantum computing can affect data science. Okay, let's go to the next slide, please. The other direction. Thank you. So this is the slide that just elaborates data science. I'm not going to read to you everything on the slide, but if we take the upper left, it's about capture, data acquisition, entry, signal reception, data extraction. Then in that respect, we might think about quantum encoding, how we're going to capture data and write it into quantum bits. An argument can be that we get an exponential advantage, but that argument, there's a lot of technicality to the argument that raises important questions about what's feasible. If we look at the lower right, analyze, these are, this is about exploratory predictive analysis, regression, etc. We can ask whether quantum techniques would help in that. So regression analysis can be a part of machine learning. There's quantum regression approaches, text mining. We have Grover search algorithm types of things, and can ask questions about where the value is. So personally, I find that when I'm looking at applications of quantum computing, I like to dig into this slide and understand what where the possibilities lie. And you can see at the bottom, I took this slide from a source, I think it was Berkeley University. I've given a bit.ly hashed short reference. So if you, I've given short versions of URLs that you can look up the sources. Okay, next slide, please. Okay, so this is just telling you a little bit about the classical versus quantum computing. So as I said before, classical computing is about working with information represented as strings of bits. Here I write down a string of zeros and ones, and then processing. And one beautiful fact that we use a lot in theoretical work is that if we really want to do what I call apples to apples instead of apples to oranges comparison of the benefits of quantum computing, I can take Boolean circuits and reduce them down to NAND operations, because NAND is universal in Boolean logic. And then on the quantum computing side, instead of that string of zeros and ones, I put it inside of a cat. It's got a vertical bar on the left and an angular bracket on the right. Add it to another one, and this is telling us that we can have two different strings at play at the same time. They're not coexisting. It's a superposition of the two. It's as though you took a wave and another wave and made two different kinds of waves whose description of the waves are represented by bit strings, and then made the two waves superpose, like if you think of water waves. So it's very subtle, but essentially with quantum information processing, we accept information as bit strings, we yield it as bit strings, but in between we take advantage of the wave-like properties of quantum computing. And then with quantum processing, we write our quantum logic operations. So instead of Boolean logic, we map it over to quantum logic, and these can be expressed as unitary maps of states in Hilbert space. I know that's technical for some people. It's the best I can say in a short message. And then detection is, in the end, we have to get bits out. So in the end, whatever's going on in the quantum computer with all this fancy superposition of waves, in the end, we have to see what the answer is as a string of bits. And that detection is a sequence of a ket and a bra in Dirac language. Okay, let's go to the next slide. Thank you. So this is my one slide to just try to get across what's the essence of the mysteries of quantum mechanics and how they relate to quantum information processing. And in this case, this is the famous Schrödinger-Cat paradox. So Schrödinger was concerned about quantum mechanics, even though he's one of the inventors of quantum mechanics, he was also worried about it for good reason, just as Einstein was. And Schrödinger said if quantum mechanics is right, then even a notion like life and death no longer remains objective. So that's a really important philosophical implication. And then he explained how Schrödinger's cat could be placed in a box. You don't see what's going on in the box. There's a poison gas that's triggered by a radioactive alpha particle decay. So on the lower left of the first box, you can see this nucleus. It's got 4 red balls that represent the alpha particle, which is the same as a helium particle nucleus, 2 protons and 2 neutrons. And in a liquid drop model of nuclear physics, we can think of this as being that the radioactive particle is an alpha particle bouncing around inside, and then it can tunnel outside of the nucleus. So classically it's confined, quantum mechanically it can leak, and it's the behavior of that leakage is described by high school level theories of nuclear decay. If it leaks, then the poison gas is triggered, as you can see on the right, and that kills the cat. But quantum mechanically, we don't say that there's a definitive event where the alpha particle leaves the nucleus. Rather, the alpha particle is described by a wave function. It's also a wave. And that wave function has extent beyond the size of the nucleus. So the probability of decay is just related to the proportion of its probability function being outside the nucleus. And so quantum mechanics doesn't say that the alpha particle has decayed or not decayed. It just says that the alpha particle is in a superposition of both possibilities. And we can think of it of being inside the nucleus as being a 0 and outside as being a 1. So initially the alpha particle is prepared in 0, and over time it's becoming less and less of 0 and more of 1. And at some point where the ratio is just right, then then we can think of the alpha particle as being 50% likely to be inside and 50% likely to be outside. But if it's inside the nucleus, then the gas is not triggered and the cat's alive. If the nucleus decay, if there's nuclear decay, then the poison gas is triggered and kills the cat. And so in the lower right box, you can see a cat, that vertical bar with an angular bracket, and inside the undecayed nucleus, which we think of as a logical zero, and the live cat superposition with the decayed nucleus and the dead cat. And this is what Schrödinger's referring to. You can't say without looking in the box whether the cat's dead or alive, but rather that it's entangled with whether the nucleus has decayed or not decayed. And then you can prove with standard quantum mechanics, the theory doesn't allow any objectivities. So Einstein argued that it wasn't complete, and we now know that we don't see any path to completing the theory. So the theory might be correct as it's written. Why this is important for quantum computing, so instead of going into the philosophical implications, we quantum computing people then think, let's just make use of this. Let's not argue about what it means. And so that superposition is of a 0, 0 and a 1, 1. And 0, 0 is 0 based on base 2, and 1, 1 is 3 in base 2. And so we can now think that that whole process, waiting for a nuclear decay for a certain length of time, and then having it kill the cat or not kill the cat, is a complicated way of preparing a superposition of the numbers 0 and 3. And the fact that we do it as a binary string is important. We could have many different states of a nucleus and many different states of the cat. But by encoding in binary, this is what gives us an exponential advantage. We just, if we don't want just 0 and 3, but we want bigger numbers, we would have more and more entities that we consider. So the Schrödinger's cat paradox actually, it's interesting and fun to reinterpret it in a quantum information paradigm. Let's go to the next slide, please. Okay, so these quantum computers, and just without fear or favor, I just picked 3 pictures I like. The first one is IBM's quantum computer that's based on putting a superconducting chip inside of a dilution refrigerator. And the dilution refrigerator here is dismantled, and what you see is a number of gold steps and what I think of looks like a chandelier. And it's really about being able to do electronic driving of the superconducting chip at the bottom of the chandelier in a way that the chip is almost at absolute 0 temperature, and the different stages of electronics are working with orders of magnitude change of temperature. So it's a very tricky system to be able to exquisitely control the superconducting chip to do computing and running electronics where the temperature is changing radically on centimeter scales. That's what you're seeing there. The next picture is, they've reordered, just hang on. Yeah, there's Xanadu's, which is a Toronto-based company. So it's a startup, just raised another $40 million last week, and they're doing photonic quantum computing. And we also see Honeywell's quantum computer. They formed a company, Quantinuum, which combined with Cambridge Quantum Computing is developing ion trap-based systems. So those are just examples. I like all the companies. I'm not trying to tell you these are better or worse than the rest, but that kind of gives you an idea. And somewhere inside of each of these chips, they're able to do in one way or another this Schrödinger cat type operation that generates entanglement. And they're able to program them, and the programming of the system allows them to accept input, solve it, and generate output. The computers are not very good in the sense that they often give the wrong answer, and they only solve small problems we could do in a laptop computer. But the fact that we're able to take such beautifully difficult to manage quantum systems, 2 decades ago, all this would seem unimaginable, and we're actually able to compute is a great victory. So you could be an optimist or a pessimist. In the pessimistic side, you say, well, after 20 years, we haven't got that far, we can't compute much. Or the optimistic side that says, we've taken quantum mechanics from just an underpinning theory that had nothing to do with nature, larger than a microscopic scale, and made real systems and devices out of them. And so that's the exciting thing, is we're rapidly progressing towards machines that will compute. Of course, they have to compute better than the alternatives to have real practical value. Okay, let's go to the next slide. So in this slide, I'm representing the key quantum algorithmic platforms. I don't put in this slide the variational techniques, which are very, very popular now, especially for quantum chemistry applications. The reason I don't do so, the reason I don't do so is they're not yet proven to give advantage. These quantum algorithms are the things that we have reason to believe that they could be very useful, and so these are the three key quantum algorithms that I'm focusing on here. The one on the far left, this is a Wikipedia picture, the picture's behind Wikipedia, and it represents the Grover search algorithm. It's fairly abstract, and the idea here is it's often described from Grover's work as database search or unstructured database search. Technically, it's a function inversion problem. So if you think of f of x equals y, and I give you y and tell you to find x, that's an inversion problem. And then what we know is if we don't worry about the cost of computing f, then the function inversion problem is quadratically faster, quantumly. What that means is if I give you y and you have to find x that maps to y, we can then count the number of bits that it describes x. And then what we know is that quantumly we can solve the problem with the square root of the number of steps we would need in the classical case. And this algorithm is at the heart of a lot of the quantum machine learning stuff, et cetera. That if you see papers that look for quadratic advantage, that's kind of the signature of this kind of algorithm. On the far right, this is another Wikimedia picture that shows you the essence of Shor's algorithm. Now, there are more elegant ways to write it now, but the one in Wikipedia points out it's got 3 steps. And this is the one that gives us, people often call it exponential advantage. Technically, it's a sub-exponential advantage. So in Shor's algorithm, the idea is to factorize numbers. So given a large number, the task would be to factorize it. So the number is promised to be a semi-prime, which means it's a product of 2 prime numbers. The task is to factorize it into the product of 2 primes. And this kind of problem, if we can crack it efficiently, which a quantum computer in theory could do, then it destroys all the security we have currently with public key cryptography. And just to throw in there, recently NIST published the winning bids on its post-quantum crypto standard, and they're expecting to develop a standard for post-quantum cryptography next year to provide quantum-proof cybersecurity. It's all to defend against this algorithm. So the essence of this algorithm on the right is that it makes use of quantum mechanics to find periods. So in code breaking, if you get into code breaking, what you realize is you're often looking for frequencies of different symbols and then trying to map those over to natural language and what might be communicated. So finding periods is at the heart of code breaking. And if a quantum computer can do it sub-exponentially better, by sub-exponentially, what I'm saying is given a number that you want to factorize, write it as a string of bits, and then the cost of factorizing classically is an exponential of a root of the number of bits required to describe the number being factorized. And quantumly, we can do it in polynomial cost. So it means that the cost of running the algorithm is only some power of the number of bits and not an exponential of a root of the number of bits. So this is a sub-exponential advantage. And this is the one that's leading to post-quantum crypto standards, et cetera, that we need, and quantum cryptography, we need ways to be able to defend against it. And this algorithm has 3 steps. The first one with the stack of H's turns a string of zeros into a superposition of all possible bit strings. Then the next step is classical arithmetic done in a quantum computer. This is a way of doing exponentiation by squaring. So if you have to exponentiate a number, this is the most efficient way to do it, not just on a quantum computer, but classically. And the final step is an inverse quantum Fourier transform, and that's the period finding. Sometimes people will tell you that the magic of quantum computers is that it has parallel universes, everything at once. That's the first step. Sometimes people will say the magic of quantum computers is related to being able to find the periods. That's the last step. But we need this whole sandwich. We have to make this superposition. We have to do some arithmetic, and then we have to inverse transform for this. And then this algorithm has a lot of different applications, from linear equation solvers to quantum field theory applications, etc. Okay, and the middle one is, and I said we know their advantages. The middle one is really just representing an aspirational approach, which is using quantum computing for optimization. And the idea there in optimization, there's a simulated annealing algorithm that, that seeks the best solution. In this case, it's the lowest point. You can see that if you just do some local search, if you don't make a good guess, you'll get trapped in a poor solution. And the idea is that to get over that tall barrier, it has to hop. But if you take advantage of quantum mechanics, you'd hope that this particle representing a solution can tunnel through. There is some evidence, it's always debated, that quantum annealing is superior in that it beats simulated annealing. I can go over that in question time if you want, but it kind of gives you the idea of what's going on here. Okay, can we go to the next slide? So for the serious aficionado, like I am, if I wind up with a problem, as I said, data science, and I want to know what will work, I go to the Quantum Algorithm Zoo. This is maintained by Stephen Jordan. You can see his email address. He works for Microsoft Research in Redmond, Washington State. And so he maintains it. And it's just the Quantum Algorithm Zoo is the set of all quantum algorithms. There's a lot of them. And it's very beautiful. You can see here, this is the factoring one, super polynomial. As I said, it's a sub-exponential algorithm. So they don't say it's exponential. And it explains what it is, it gives references, and it updates all the time. It's easy to look it up if you do a search on the web, and it's a great place to go to figure out what algorithms are out there and then do a mix and match. And right now, there's actually a limitation in the world where we have what I call push and pull. The push side is we quantum scientists keep figuring out new things. The pull side is people are saying we want to make use of quantum computing, and the translators, the ones who can go from the push to the pull and figure out what's needed, there's a shortage of them. So the Quantum Algorithm Zoo is helpful, but you need to have some expertise to be able to read it. And over the next few years, I think the community is going to start to address the gap of having people be able to communicate these issues. Let's go to the next slide. Okay, so on this slide, I wanted to tell you about quantum machine learning a little bit. This is written by Nathan. So this is from an article in New Journal of Physics by Nathan Weeb. I'm using the short digital object identifier. So if you put 10/GG73NF into DOI.org, the article pops up. The DOI, or digital object identifier service, runs its own hash function. So just for brevity, when you see 10/, you know that it's a short DOI. So Nathan writes about quantum enhanced machine learning, and so he writes about two aspects of quantum machine learning, which are important topics today. And in his article, he breaks down quantum enhanced machine learning. So he points out that the advantages that we seek are fewer computational steps for training or classifying, lower sample complexity, rich set of data models, and quantum optimization. I just talked about optimizing a test loss function. So these are the kinds of targets we look for if we want to demonstrate that quantum machine learning, if we look for ways to use a quantum computer to enhance the performance of machine learning. The alternative approach is also very popular. And so this is making use of a quantum device or hardware. Make some hardware and make use of that to do quantum machine learning. There's Boltzmann machines or deep learning, neural networks, etc. And then we can say that there are neurons in a neural network, make them quantum. So instead of on or off, there's superposition of on and off. They entangle together, and then we can study those to see if there are advantages. Make use of quantum algorithms. That principal component analysis, the gold standard of that would be using the Shor algorithm type approach. It's called hidden abelian subgroup. So making use of that algorithm goes behind this. And then there's the quadratic time reduction for quantum invertible data training. That's based on the concepts of Grover's algorithm. So the quantum to look for quantum approaches to machine learning, we're essentially making use of those three algorithms and finding ways to apply them to a variety of areas. Let's go to the next slide, please. Now this slide, I'm conveying to you what we call this quantum computing era, which we're now approaching an end to. I'll say more on that shortly. This is called NISQ for short, Noisy Intermediate Scale Quantum. The short DOI is to Preskill's paper in the journal Quantum. And so in these 9 blocks, this is Preskill. So John Preskill is a professor at Caltech and a thought leader in the area, and he now works a day a week at AWS, Amazon Web Service. And so he argued a few years ago for NISC, and he also put warnings in it. And so a lot of the quantum computing these days is about doing NISC quantum computing. So I'll just go through the blocks fairly quickly. Number one, he said, let's do NISC. And so the idea of NISC is, let's just make a quantum computer, not try to make it good. Let it be noisy, let it lose things. Just build something big enough and use it to see whether there's advantages. That's the argument. So he points out that there's an opportunity to test quantum computing this way, that maybe something good will happen, that it gives us an opportunity to hybridize quantum computing, make use of classical and quantum optimization techniques all together, see whether it will accelerate heuristic development. So by building these things, it might give us ideas that we can make things advance better. Also, he said that we should be, to me, I interpret as being disciplined, that even though we're allowing noise, we should build them bigger and bigger with noise resilience in mind. So as we build the hardware, bear in mind, don't build it and then go back and rebuild it. And I'll have a comment on that towards the end of my talk where we can see that kind of story in play. And then we can look at ways to build quantum hardware that would have low error rates. And also, this is a way of giving acceptable risk to be able to make quantum computing companies. By tackling these kinds of problems, we're able to generate venture capital, government investment, et cetera, to be able to do quantum computing. Because we're not, what we used to say several years ago is, just keep giving money to quantum computing and be patient, and one day it'll work. And this is a way to saying there's a chance it will work, so it fits into a high-risk, high-gain policy. And then Preskill points out in the last block that transformative quantum technologies likely will need to be fault-tolerant. So he's saying, let's embark on this NISC effort, but bear in mind that in all likelihood, it won't deliver benefits directly. And I'll have more to say on that shortly. Okay, let's go to the next slide. So this slide is, I just decided that I would give you two slides from Gartner. Gartner is a consulting company that specializes in forecasting. And I just wanted to highlight what they said. This is already 2 or 3 years old. So, or 4 years old technically. Yeah, so it's already getting out of date. But this gives you an idea of what consulting companies are advising on what to look for with quantum computing. And so you can see number one, chemistry, 100 to 200 qubits. The idea is to start to tackle chemistry problems and solve things. Often these boil down to combinatoric type arguments and make use of optimization. Number two, for general optimization problem, hundreds of thousands of qubits. Machine learning, hundreds of thousands. Material science, hundreds of thousands. Unknown problems would be hundreds of thousands and beyond. So this gives us a target. We want to reach hundreds to thousands of qubits, and companies are pushing forward on making more and more qubits, but there has been a U-turn lately. And so again, I'll come back to that later on, but just bear in mind. Okay, but the message here is for foreseeable use of quantum computers, hundreds of thousands of qubits are needed, but whether counting qubits is a good approach and is the question. And again, I'll come back to it. Let's go to the next slide. So this one writes use cases. These are not actually use cases. They're just labels for use cases. And so they've taken quantum chemistry, simulation, communication algorithms, and quantum machine learning and written various use case labels like finance, protein folding, singularity, and then drawn connections between which one fits in where. The honest truth is that if quantum computing really delivers computational advantages, everything is a use case, I feel, because so much depends on these kinds of things. Even right down to, even if you don't use it for the algorithm to solve a problem, it could be that even your compiler, even the way that you compile solve problems would be beneficial. But on the other hand, we've got to be careful not to hype it, that it could be that quantum computing doesn't deliver advantages, and we're still watching carefully this kind of thing. So my message from this is, if quantum computing works well, it's revolutionary and disruptive, and if it doesn't work well, it's not. And then this Gartner slide only captures a small subset of what's possible with use cases. And writing use cases for quantum computing is actually an important business at the moment. Okay, let's go to the next slide. So this article was written by, so let me just tell you, it appears in European Journal of Physics, European Physical Journal, I'm sorry, and 2 years ago. It's written by Francesco Bova and Avi Goldfarb, who are both professors in the business school at the University of Toronto, and Roger Melko, who's a quantum machine learning guy and condensed matter physicist at the University of Waterloo. And they wrote an article based on their experiences with the Creative Destruction Lab. It's a lab, I'm part of this as a scientist mentor. And it's a stream, an entity that fosters ventures to scale up. Basically, the idea is to let them massively scale from small high-tech businesses to big-scale unicorns. And so they've written about their experiences with this, with working with these ventures over several years, and they identify what the opportunities are. So what they highlight in the article is that the opportunities are combinatorial optimization is what they see as the nearer-term benefit, and then they identify 3 areas with near-term use cases where users can support the development. It's banking and finance, materials and pharmaceuticals, and advanced manufacturing. And then each of the reasons is their portfolio management, molecular configurations, and rare failures in manufacturing. So that's what they identify in their article as the nearer-term commercial applications of quantum computing. And it's an interesting article. They go into all the nuances, and it's worth a read. Okay, let's go to the next slide, please. So I promised you I'd say something about work in my own area. So I just have one slide on it. But in the area of making use of quantum computing, you can see here 5 different areas where I'm making use of the quantum algorithms. The upper left is about security for quantum networks. So do quantum algorithms help with security, and how do we counter the effect of quantum algorithms for security of networks? It's not just about key distribution, it's about metadata, it's about authorized access, all these kinds of things. The lower left is work on blockchain, Bitcoin, for example, and what are the quantum computing threats there. The upper right is we have work out with quantum version of support vector methods that support vector regression for facial recognition, specifically algorithms to identify where the eyes, nose, mouth are, and then use those to then employ something like the face, basically to rotate the face to a constrained facial recognition connection. The lower right is some work that my group is doing with health area, where we're using quantum algorithms to approach identification of pathogens. And the middle one is using quantum computing to tackle problems with oil reservoir prediction. So the idea is if you discover oil, you want to know how to drill to maximize yield of oil and minimize the consumption of natural resources in doing so. And it actually has ESG, environmental sustainable development goals, in mind, and it's something of interest to oil companies, how to reduce the impact on environment. Okay, so those are examples of areas I'm looking at to make use of quantum computing. Let's go to the next slide. So on this slide, I wanted to just give you some flavor of what the latest things are. So I picked this story up. This is a MIT Tech Review journal, excellent journal. And so they published in December their top quantum research stories 2022. And so let's just talk about those. One is NIST, the National Institute for Standards and Technology. I mentioned this post-quantum crypto competition related to the whole issue of what I said about the quantum computer threat for crypto systems. And so they just recently announced their winners to develop a post-quantum crypto standard. So the idea of using RSA, elliptic curve, all those things, there might be a level of secure crypto where you need something different. So they announced those, and they're planning to publish a standard by 2024 for post-quantum cryptography. IBM announced its quantum computer of 433 qubits. It's called Osprey. Global Data had a story really is talking about the geopolitical competition. And one way to quantify it is that the market in the USA and China, largely driven by competition, is expected to reach a market value of $5 billion. So that's not an investment value. Market value. And then I got a quote there from Suter of Cold Quanta. That's a neutral atom quantum computing. He talks about biggest hurdles being to reach tens of thousands of functional quantum bits with low error rates, qubit interconnection, and multiple quantum porous connections. And so these are some of the top stories, just giving an indication of where 2022 is. Let's go to the next slide. And the next slide is my last slide. And I'm trying to get this done so I have time for questions. So this one is really a what's next for quantum computing. And then I've got the bit.ly short URL reference. So the first point is interesting. I mentioned on the previous slide that 2022 achievement by IBM with its processor Osprey, reaching 433 qubits, and now IBM is going for 133 qubits. And remember I mentioned about John Preskill's comment of bearing noise resilience in mind? And so I see this, I like what IBM is doing, so it's not a criticism at all, but IBM reached the 433 qubit version. They're scaling up, and now they're going back to their Heron processor and saying, but now we're going to develop a 133 qubit processor. And what they're bearing in mind, my interpretation, they're not very forthcoming about these kinds of technical issues, but my interpretation is that they're recognizing that there are size limits in how big they can make processors. And so I see it as a U-turn to go back to address the need for the quality qubits and to make sure that the architecture is done so that they can make it modular, basically to have different quantum computers interconnected in some quantum way so that they can make smaller processors but have them interconnected with a distributed quantum computing paradigm behind it. So that's an interesting step, I find. It really tells me that we're stepping back from bigger and bigger chips to recognizing that there are limits on how big we can make quantum chips. Let's make them modular and exploit quantum communication. PsiQuantum is a startup. It's a unicorn. So the last valuation I looked at was over $2 billion. And they're doing photonic quantum computing. And so one of the highlights in this article is about the next step, which would be the low-loss optical chip. PsiQuantum's story is if you invest with them, they're going straight for millions of qubits. They're saying we're not going to put our time into developing computers for tens, hundreds, or thousands of qubits. We're going for millions. And so they're claiming that this is the last obstacle so they could go to the million qubit level. The next one is, and this is something I feel too, the optimism about NIST seems to be fading. So the focus is shifting to mitigating noise. But that was exactly the point in Preskill's article. That's why I highlighted it to you. Preskill's saying, let's do NIST for a while, see if it can give an advantage, learn a lot of lessons from it, start to focus on customer needs, and let's be aware that we'll probably need to have fault tolerance, i.e. noise mitigation. And so this point is actually what Preskill predicted. So the person who said, let's do NIST, said exactly this would happen. And so this IBM move to 133 qubits instead of 433, to me, is a reflection of this need to move out of the NIST paradigm. And then the final one to watch for with quantum computing is, to me this is really interesting on a software level, is to replace circuit-based coding on a cloud-accessible quantum computer by non-standard frameworks for looping. And looping, so in a computer, when you write programming, you have loops, if, then, or for I less than 10, do, or something like that. So do loops, for loops. I'm an old Fortran programmer, so I think in that language. But you have to have loops. And I showed you that short algorithm approach. There's no loops. And so the idea that somehow, to go to real programming, we have to have loops is important. And it's not really built into the way that we're doing quantum computing today. And so I find it very interesting that we're reaching a point where we have to then circle back, not just on the hardware, perhaps to make it modular, but also circle back saying, programming is not about using library functions and writing Python code and having a sequence of steps. Programming is much more. It has to make use of loops. It's got to be modular. It has to have ways to build up complex programs. You don't want to use somebody's library function to solve your problem. You want your smartest programmers to figure out how to do it themselves. And the framework is not there yet to be able to do programming of a quantum computer as a true programmer would look at. Okay, so that ends my slides, and I'm happy to take questions. Thank you.
Thank you, Barry. This is Anindita. So initially, I think our apologies for the initial technical glitch. And this was a very interesting presentation. You took us right from the beginning of quantum computing, then its algorithms, to its applications, to the next computers, and to what the world is thinking about it. Just to tell you that for the interest of time, we have kept the format of the presentation where the speakers are introduced via their bio flashed on the screen, and the anchor introduces the speakers. And we have a wonderful audience over here from different agencies, from academia, from R&D, from policymakers, to some critical units as well, who have come here to listen to you. And so thank you, Barry, thanks again. And to everybody, because I think some people joined late, Barry is the director of the Institute for Quantum Science and Technology at the University of Calgary. He's the lead investigator of the Alberta Major Innovation Fund project on quantum technologies. He's a distinguished chair professor at the University of Science and Technology in China, and he's the visiting faculty member of RRI in India. To me, Barry is my mentor, and thank you, Barry, for being there. So let us take some questions now. So the house is open for questions. So if not, I have plenty, but let me start with one. Sir, if you can tell us something about, what exactly fault-tolerant computing is. Right now, you mentioned that we are now moving towards the IBM's 433 qubits is a indicator that we are moving towards the fault-tolerant computing. So what is this actually? Does it mean a technology change from the NISQ computers to fault-tolerant computers? Does it mean a better error correction? Does it mean some more applications? So your thoughts, please, on that.
Sure. Okay. So there's different issues here. One is error correction. And so for error correction, we don't just take the input raw and put it through the computer as we do in the NIST stage, but rather we encode it and then do the computing on the code space. This is something we're not ready for yet. We need much bigger quantum computers to be able to do it. Fault tolerance is a little bit different. So fault tolerance is the idea that as we scale up, we make bigger and bigger quantum computers. We've got to make sure that adding that complexity doesn't come with an overhead that makes it infeasible to build larger quantum computers. So, and Anindita, you mentioned the 433 qubit wasn't the evidence of it. What the evidence is, to me, is going backwards. Superficially, it looks like it's going backwards, saying we've now made a 433 qubit processor. Now we're going to go back a step and make a 133 qubit processor. Why go back a step? Because the modularity might be the pathway to be able to reach the fault tolerance. So the way that we use fault tolerance as a term in quantum computing is saying that as we put more and more imperfect things into a larger and larger computer, we have to find a way to make sure that the negative aspects scale nicely as we build it up. And that's related to Preskill's comment about building with noise resilience in mind. So the noise resilience in mind is another way of saying, let's make sure it's fault tolerant.
Thank you, Barry. I think we have one more question.
Hello, Barry. Been inspired by your talk. I just caught the last part of your talk about programming. I just want to ask, what is the perspective? What do you mean by programmers, the coders of the real application? Is it something that they have to mature in terms of defining the data structures? So far, we've been, coding for only for probably, 1,000 cores or, something like that. GPU when when they arrived. So it took some time for us to, adapt our code to those kernels. And it was easier because all the proponents of the GPUs like NVIDIA, they brought the CUDA libraries and all that stuff to process the data. Still, it was only in binary, but now you're talking about qubit. So, what is that you have seen in your experience there? The application programmers, is it like I believe that computer science data structures have to be improved, so something has to come from there to visualize the binary bit to the qubit. So two-dimensional arrays, multi-dimensional arrays. So we have come in many of the legacy programs are written in Fortran, and or MATLAB and those. So this probably qubit computing is going to probably target those programmers. So what is your perspective on it? Thank you.
Okay, thanks. So currently, the way that we access quantum computers is that we make use of library functions. So the typical way my students will work on things is they'll write code in Python, they'll interface it with commercially available library functions and make use of those, and things don't always work well. You have to figure out, you have to debug it. And debugging it in the quantum computing world, where things are noisy, things don't operate perfectly, is actually very difficult. And so the stage we're at is that there are some companies out there that develop library functions that you access. So what we think of as quantum programming is just ordinary programming with calls to libraries that will interface with hardware to execute. But in order to make sure we get the best performance, we have to be able to optimize things. We have to be able to run code on real quantum computers, figure out what's going on, and then modify our coding at whatever level, even if it's all the way down to assembly level, to make sure it works well. And at the moment, we don't have that kind of access. We're not able to do it, and we're not able to put conditional statements in. Essentially, we don't want a human being being the one who assesses, optimizing, etc. Everything has to be autonomous on the computer. And if we're going to get the maximum performance, I always call this squeezing the juice. You take an orange, squeeze the juice. You want to squeeze the most juice out of it. And if we need to get these structures in place, the whole framework for programming all the way down to the assembly level in some logical way, makes sense, uses the best practice of software engineering in order to be able to get the most out of quantum computers. And so that was the thing to watch for. So a company that's very serious about that, as one example, there are more, but Horizon Quantum Computing, which has been based in Singapore. I just saw news that Joe Fitzsimons, who's the CEO, I think he just moved to Ireland, so they might have moved from Singapore to Ireland. But it's that's the company I know that takes most seriously the idea of getting the framework right for being able to squeeze all the juice out of a quantum computer. Today you can program, but you're just using libraries.
Thank you, Barry. We have one more question from Director General, Shri Mageshji.
Hello, am I audible? Yeah. So, Barry, yes. I have a couple of questions to you. Probably because the legacy baggage I'm carrying, this may be very simple to you. First one is there going to be a quantum memory? And secondly, is there going to be a quantum OS? Will it carry the legacy thing, or it will be something totally different?
Yeah, so you're asking some of the hardest questions imaginable. Thanks for that. So I'll go back to the quantum memory side. So probably, if you're thinking about, really proper architecture for computers, memory plays an important role in programming. And is there going to be a quantum memory? There's not a quantum memory in the architectures at present. We don't have a clear concept about doing it. And so the current approach that people are following is to use a hybrid approach. It's mixing quantum steps into a classical architecture. You also asked about OS, I think. And so I think the answer to your question is, over the nearer term, I think that we're going to hybridize it. We're going to use legacy systems to be able to do things. And then where it makes sense, we'll plug in quantum steps. But then it's really quantum enhanced computing. And it's not in a pure level what quantum computing should be. We know that. There's work on QRAMs, for example, that analyze it, and there are drawbacks of it. So there's huge theoretical problems in getting there. So the short answer is that longer term, we want to get away from legacy and make use of truly quantum parts. Short term, we'll do hybrid and make use of legacy systems.
Thank you.
Thank you, sir. Now we have one question from Colonel Nath, who is the Executive Director of C-DAC Pune.
Good morning, Professor Barry. I think we met, thanks for visiting Pune just about 2 months earlier. Just a quick question, there is a lot of interest in now the microprocessor companies to come up with some special purpose processors which do integer operation, integer factorization very fast to look after this cryptographic code problem. So will that in any way impact the development of quantum computers, the speed with which they are getting developed? Because cryptography is probably at the center stage of the entire motivation.
Right. So for the short term, there's quantum computers don't have the size to be able to do the kind of cryptanalysis, the code breaking that's needed. So shorter term, those kinds of things that you mentioned are really where to put the money. The quantum computer, the reason to develop the quantum computer for things like factorization is because it's a game changer. Basically, I'll put it like this. So integer programming, all that, is still subject to the limitations of the number sieve problem. This is what I talked about with the sub-exponential advantage. So there's still, the scaling up of those algorithms is not better than sub-exponential, whereas the quantum algorithms are polynomial. So basically, there's better and better hardware, better and better software, better and better algorithms to be able to improve the speed of factorization, to do code breaking, but there will eventually be a turning point. If we can develop good enough quantum computers and scale them appropriately, at some point there'll be a crossing where quantum computers are better. The effect of the kinds of things that you mentioned is they delay that crossing point, right? So we can say, based on current technology, the crossing point will be this many years hence, and then if better things come along like GPUs, integer programming techniques, whatever that comes up, then we say, okay, now we have to reassess. The competition's getting better, and it delays it. So the reason to put the money into quantum computing is not because it will beat those things in the near term, but because eventually that turning point will have to happen, and then quantum computers will make a difference.
Thank you, Barry.
So we have one question from Dr. Rahul, Mr. Rahul from MeitY.
Good morning, Professor Barry. I have a simple question. We have so many implementation approach to implement a quantum computer, superconducting, photonics, NMR, neutral atoms, and so many. Which one is a promising approach in the future, which will be feasible and require a less investment amount?
Yeah, it's a difficult question. So the reason that people are putting their money to all of them is because nobody really knows the answer to it. The superconducting quantum computing is the most powerful right now. So it's, if you look at really good quantum computers today, they're based on supercomputing systems. But I will mention that, even if you ask me, like, is superconducting better? Then you have to bear in mind that there's superconducting transmon-like qubits, there's flux qubits, there's bosonic qubits is what it's called now. So there's at least 3 different promising directions there. Ion trap, but then do we do ion trap schemes with ytterbium, with strontium, barium, and then there's the neutral atoms, strontium, there's Pascal with neutral atoms just got €100 million 2 weeks ago in a big announcement. Investment funding, and photonic psi-quantum I mentioned, which is going from millions of qubits. So there's many, many different ones, and even the photonic one, like psi-quantum versus anodine. So each one of these companies has their own direction, and even if you ask about, are photons better, there's many different approaches to photons, many different approaches to ions, and so on. So where we're at the moment is we have to bet on everything, and then be very clear in our minds what constitutes progress and where they're going to fit. Superconducting is probably the best today if we're looking for hundreds or maybe thousands of qubits. If we're looking for tens of thousands, that's where neutral atom quantum computing is placing itself for that kind of thing. If you're looking for millions of qubits, that's where the photons are. This is not necessarily what I believe, but so hundreds of thousands is where the superconducting companies argue for investment. Tens of thousands for neutral atoms, millions for photons. That's kind of where the investment space is right now.
Thank you.
Thank you, Barry. Just one last question from Mr. Chele. He is the Director of 6G Technologies, Department of Telecommunications.
Good morning, Barryji. We have seen the PQC, the fourth round sessions over in the last month. Can you have an idea about what is the outcome of the PQC, fourth round PQC towards the standardization, whether they're sticking to the lattice algorithms or not other three algorithms also? What is the can you target the 24 is there, but exactly how they are going to move the standardization, how they are inclusive to other partners in that standardization in the NIST?
Yeah, it's important to know because, of course, I understand if you know the answer to that question, you know exactly where to put your team to figure out which way to go. So NIST has only published the winners of the previous competition. It doesn't mean that they've decided on a standard, but they've narrowed down the list. I don't remember who's on the list and which algorithms they use, but it's public, as I understand. So it's possible to go through and figure out what they are. So now that that's available, then I think NIST will go through the standard to figure out what it will be, whether it's lattice-based cryptography or whatever. We'll see how that comes. But it's very important. In fact, I've been approached by cybersecurity companies, that guarantee government-style communication, and they've been talking about how to develop the software needed to ensure that, basically to develop cryptosystems that are PQC ready. And so, we don't know who the winner is going to be, and the companies I know that are involved with this are starting to position themselves strategically so that they do have cryptosystems that are compliant with the NIST standard. And they're watching very carefully.
Thank you, Barry. We are extremely grateful for your answers. Thank you. So we now move on to the next session. Thank you, Barry.
Okay. Thank you very much.
Thank you so much, sir, for your enlightening talk. We are grateful for you joining us.
We now proceed with the inaugural session. Before proceeding forward, let us invoke the blessings of the Almighty. I request our colleague, Srimati Lakshmi Panath, to kindly recite the Saraswati Vandana, the goddess worship for knowledge and intellect. Thank you so much, ma'am. Now I request the dignitaries, Dr. Preeti Bansal, Scientist G, Advisor, Office of Principal Scientific Advisor, Srimati Sunita Verma, Group Coordinator, R&D in IT, MeitY, Shri E. Magesh, Director General, C-DAC, Colonel Ekinath, Executive Director, Corporate Strategy and C-DAC, Pune, to kindly join the dais. Our chief guest for today is Shri Rajiv Chandrasekhar, Honorable Minister of State, Ministry of Skill Development and Entrepreneurship and Ministry of Electronics and Information Technology, Government of India. He is connected with us virtually. Now I request Colonel Ekinath, Executive Director, Corporate Strategy and C-DAC Pune, to give the welcome address.
A very good morning to all the delegates, distinguished dignitaries who have come here from far and wide, from across the globe, present here, and also those connected to us from various parts of the country and abroad. It's a great privilege for me to welcome you all to this special symposium we have organized. I'll be telling you the story as to how this symposium was organized. C-DAC, as you know, has established strengths in the area of high-performance computing and is in the process of now delivering TRL 8-9 systems to the country based on its Rudra server, based on its Rudra motherboard which they have developed, and also the interconnect which we have developed. C-DAC has taken on quantum computing, but naturally as one of its other mission areas, because HPC and quantum computing are going to coexist. And therefore, it's very natural that C-DAC should progress towards quantum computing and embrace quantum computing as one of its mission areas like high-performance computing. Quantum computing being a vast field, no institution has the capability of going ahead and delivering or even attempting to do something which is all-encompassing, because any quantum computer has a lot of subsystems, a lot of expertise, cross-dimensional expertise is required. So therefore, in order to do some very serious thinking, a serious, if you have to embrace quantum computing as a mission area, there was a reality check done, and we went about searching the country for the expertise available within the country in various subsystems which go on to build a quantum computer. We could identify a lot of institutions, and I think it's a very great thing for our country that a lot of institutions have identified where work on various subsystems was under progress, maybe for different reasons, not be connected to quantum computing, but it can always be customized towards quantum computing. So we could find out a lot of institutions, and then we found a lot of institutions, companies abroad who are into this kind of work. So it was but natural that we had to find a platform to connect, to synergize all these different institutions where this kind of work is going on, in order to now pave the way forward, to brainstorm, come together and see where we are today and where we have to move in order to realize actionable commercial quantum computers within the country. So our very passionate team, which consists of Dr. Anindita Banerjee and her team, we got together, formed, there's already a special interest group in quantum computing existing in C-DAC. They all got together, we rigged up the blueprint of this symposium, and within a record time of about 1.5 months, we could rig this up, and I really compliment the entire team, not only her, but Amit Saxena and our admin team and so many others who are involved in the backstage to have very quickly rigged up this thing. And we are very fortunate that we have the support of our ministry, and the PSA's office, the PSA himself being out of the country, regretted to be there, but he took a lot of interest, and he spent a lot of time with me when I went to invite him personally. And he said that he would have definitely been here. And he sent his very senior colleague, Spriti Bansal, who's there with us, who's going to stay there with us for the next 2 days. We have Sunita Verma, who's our group controller, R&D in IT, and also looking after the National Supercomputing Mission here with us physically. Our secretary, our additional secretary, everyone appreciated this effort. Unfortunately, couldn't join because of various other commitments, this being just the beginning of the next parliament session. We also have unstinted support from our Honorable Minister of State, who has agreed to join us virtually and give his address. He is himself a very accomplished engineer and an entrepreneur, and will be able to throw a different kind of a perspective on this whole initiative. So with the means of this symposium, C-DAC aspires to synergize the quantum computing ecosystem and get all stakeholders on a common platform to connect the dots and arrive at some sort of a understanding of our present capabilities, as I said, and steps we need to deliver quantum computers with the capability to demonstrate quantum advantage at the earliest for our nation. As I said, that C-DAC brings to the table its expertise in HPC systems, software stack development, application development on these HPC systems, quantum simulators, quantum accelerator development, and we are very happy, we are willing to collaborate with all and other stakeholders in this entire game in order to take this national agenda forward. So there is a need for synergy, there is a need for coming together and moving ahead, and this is all what this symposium is all about. By the end of this symposium, we should have a very clear idea about our strengths in various subsystems, technologies, and global capabilities and roadmaps, and how we need to align with these capabilities, and what are the collaborative opportunities available, etc., etc. The symposium is not about a very deep dive into technology, but more about integration, more about the synergies between various subsystem and system developers, integrators, about evolving designs, architectures, and standards to quickly realize workable machines. Sessions have also been crafted, as you would have noticed, based on the hardware and software subsystems which go on to make the quantum computers. And I'm sure we'd be able to unravel a lot of mysteries and get the answers to a lot of intriguing and lingering questions during the course of this symposium, and would be much wiser about quantum computing by the end tomorrow. In the interest of time, although the kind of response which has been received for the symposium, thanks to all the participants, the logos of whom you see on the screen, who are coming from far and wide to join us, we could have actually carried on for next about 4 or 5 days, but in 2 days, very difficult to accommodate everybody. So in the interest of time, we are just saving time and not making very elaborate introductions about various speakers. And also, we are giving limited time to the panelists, 7 to 8 minutes, and then going ahead with the question answer sessions. So please bear with us for that. In case we find that there is a lot of interest generated in a particular subject and all the queries and the questions have not been addressed we also have the facility of 2 meeting rooms on top, where we can go there, the session chairs and the speaker can coordinate, and we can have a separate session with the people who are interested in asking the speakers more questions. So we have this facility and we can make use of it. We also have separate meeting rooms for any closed door meetings which we wish to organize with any of the participating industries, any participants who have come from abroad and India. So as you see that the who's who in India as far as the quantum computing space is concerned are here, and the who is who in the quantum computing space globally is here. And we are having very good quality keynote speakers. We have some of them having come here physically. Professor Andrew Briggs is here from Oxford. We just heard Professor Barry Sanders. We would be hearing other keynote speakers. Professor Vijayan, our very own pioneer in the field of superconducting quantum computers, will be giving us a keynote address on superconducting quantum computers. He's from the TIFR. We'll have Laura Schultz from Leibniz from Germany joining us online. And we'll also have Jean Gonetz, who is the CEO of IQM, joining us online. And we'll be having a very, very interesting, and we'll have the CEO of Blue Force, I would say, who will be giving us, towards the end, a very super cool talk, because he's in the area of dilution refrigerators as a keynote talk. We'll also be having IBM Quantum giving us a keynote talk. So all in all, it promises to be a very, very interesting symposium with large amount of expertise descending here and also online. So it has been a nightmare for our organizers to juggle between the online people, and it will become more and more difficult when the panel discussions are here, because we'll have some people sitting here physically, some people from outside, juggling between them. And so they're till now doing the job pretty well. We are also having lunch organized just on this floor, as you see my hand towards this way. And we'll have a networking dinner at 8 o'clock on the top floor here in the same building. And we're also having an exhibition just again behind the lunch area. You need to walk through the exhibition area to go to the lunch area, take your food. And we'll be having some high tea sessions. Coffee and tea is also provided outside from where you came, opposite the registration desk. So please make use of all the facilities available. Enjoy, relax, and enjoy the session. We have the exhibition booths from these companies, which you see in the viewfoil. And towards the end, I've already sent some feelers and a questionnaire to our valedictory session participants. But we would I'll be glad to flash these issues to all of you to mull over, and we'll like your comments on email in writing to all of us, because what we are attempting as part of the symposium or the end of the symposium is to come to a consensus on these very pointed questions, the questionnaire we have drawn up, and it will all go into a white paper, a concept note, which we are preparing for our government as far as the national need and our how to move ahead as far as our quantum computing roadmap is concerned for the country. So this will be a very valuable input for that white paper we are preparing, and I would like maximum participation of all of you to answer these questions. Of course, these will be the questions thrown open during the valedictory session, and I think a very interesting discussion would ensue, because they're already aware of what they have to talk, and we have a large galaxy of good speakers who are doing a lot of great work in quantum computing. So with that, I urge you to enjoy this session, and I hand you all over to the other speakers. So thank you very much. Jai Hind.
Thank you, sir. I now request Srimati Sunita Verma, Group Coordinator, R&D in IT, MeitY, to share her views.
Shri Rajiv Chandrasekhar ji, Honorable Minister of State, Ministry of Skill Development and Entrepreneurship, and Ministry of Electronics and IT, Dr. Preeti Bansal, Advisor, Office of PSA, and Dr. E. Magesh, DG C-DAC, Colonel A.K. Nath, ED Pune, Professor Barry Sanders, who is joining us online, and Professor Andrew Briggs. Good morning to everyone. Namaskar. And all the distinguished ladies and gentlemen, I am very honored to be part of this program. Earlier I thought I will join in hybrid mode, but then coming and physically attending has its own meaning, and also interacting with all the participants. And I think we have with us the academicians, the researchers from the policymakers, our academic institutions, and also from the private companies who are closely involved in the quantum technology development. So I think it's a good opportunity for us to all mingle and then share our views together. I would like to express my appreciation to C-DAC also for organizing this conference, this symposium, to discuss about the complete quantum compute technologies. Actually, it's not just a simple development, it's also a teamwork where the different experts are coming together, as DG Dr. E. Magesh was also saying, that we have to think out of the box and look at, leave behind the legacy or the traditional way of thinking, because quantum computing or quantum technologies is not a legacy or technology, a traditional technology. It's something which has to be thought in a completely new way. And quantum computers are the future of next generation computing. They work on the principle of quantum mechanics and uses qubits. I don't want to go into the introductions because all the experts are sitting here. And I believe it will have an edge over the classical counterparts in the complex calculations. Looking at the applications, I feel the fintech or the genomics, the healthcare, every aspect of the life will be touched with it when we have a stable technology over the years that has been building up. So for example, the molecular interaction that is integral to drug discovery. It may take decades for pharmaceutical companies to bring new drugs to the market, as they need to assess billions of possible drug reactions and side effects in different human systems. But with the quantum computing, I think it will be possible to have those fast forwarded and to make it faster. And we can lower the cost and also reduce the time it takes to bring the life-saving medicines to market. So that is one of the applications that I thought would be touching our lives and will be very important to have after we have this established technology in market. Ministry of Electronics and IT also has taken several initiatives in the quantum technology area to promote the research at present, and building state-of-the-art infrastructure, along with it also skill development in this niche area. This is to accelerate the quantum computing-led research in the nation, and with a vision to place India in the front line of nations which are pursuing quantum technologies. World over, this initiative has been taken up at various levels with various quantum of funding. So we would not be, we don't want to be anywhere lagging behind in this. And even to be a step further, to be step ahead in what is happening in the global arena. And it is very important for us to, that is why, come together, think about how the technology has to be built, taken forward, getting all the experts under one roof. The first initiative, I would just like to give a few initiatives which have been taken by the ministry. The first one is on the quantum simulator platform known as the QSIM. It was a journey from a professor's classroom project to making it a national platform. So now we have the quantum simulator built, which can be used by the researchers up to the simulation for at least 12 qubits. This has been done by C-DAC, ISC Bangalore, and IT Roorkee. Then also the Center of Excellence in Quantum Technology has been set up at Indian Institute of Science with Raman Research Institute Bangalore and C-DAC Bangalore to create a sophisticated infrastructure in this niche area of technology. The COE is aligned to deliver supercomputing-based quantum processor and development of quantum algorithms. RRI is working on the photonics approach of quantum technologies and develop basic elements of quantum communication. In this initiative, C-DAC is contributing in the development of FPGA-based control hardware for supercomputing-based quantum processors. So I believe TIFR is also has its own initiative. So we would like to see here in the symposium, since Dr. Vijayan is there, how we can collaborate and come together to make this, all the experts together to make a better supercomputer, quantum computer. In near future, C-DAC also will pursue a two-pronged approach. One would be to scale up and accelerate quantum simulators over conventional accelerators using high-performance computing infrastructure, and also establishing hybrid quantum classical framework using quantum and HPC environment. Since Dr. Kanalnath has already told that we already have in C-DAC the National Supercomputing Mission, it is a vision that in later years, the supercomputing and quantum computing will be aligned or will be merging together to make a better processing and compute facility much faster, and making us or enabling us to handle more and more complex problems, which may be taking over years, which can be done in minutes or seconds. Another initiative in quantum communication is the Metro Area Quantum Access Network, MACAN, which aims to establish a testbed to test and validate quantum key distribution hardware and associate quantum key distribution protocols. Further, C-DAC is also now working on an agile and ad hoc-free space-based quantum communication using drones. So this initiative we have recently taken up in C-DAC, and I hope we'll be able to use this for many applications. And it's a completely new area in which we would like, all the companies also to come forward and collaborate for this initiative. And this is a potential for aerial mode of free space quantum communication. And looking forward to that this becomes a success. I also would like to invite all the industries, startups, and academia to come forward and collaborate for this research in the area of quantum technologies to develop the world-class products and technologies in this emerging technology. So we strongly believe that it's only through the joint and collaborative efforts that we can take this forward, because each of the different institutions or companies, we will be having their own expertise, and bringing the expertise to develop something which is very cutting edge, or it is state-of-the-art, and in which I feel that India is not lagging behind in any sense. So this is the right time that we need to move forward and also establish a lead in this. We have collaboration. We have Professor Andrew from Oxford. So I'm looking forward to more collaboration with his institution, so along with our other institutions and C-DAC, so that this symposium also becomes a success. So what we are trying to, through this symposium, trying to see is where the expertise lies, how we can collaborate, and how we can take forward the initiative and build a complete quantum computing ecosystem. So with this, I feel that this will be a step towards accelerating the development of quantum computing in the country, and a long-term roadmap can evolve in India in the quantum computing. And I would like from this symposium, C-DAC to take and bring back the learnings and participate in the National Mission for Quantum Technologies and Application, which is driven by Department of Science and Technology. And we are expecting that C-DAC will lead in the quantum computing area. Thank you. Thank you for your patience, and I look forward to a very successful symposium interaction in the today and tomorrow. Thank you.
Thank you so much, ma'am. I now request Dr. Preeti Bansal, Scientist G, Advisor, Office of Principal Scientific Advisor, to kindly share her views.
Honorable Minister Shri Rajiv Chandrasekharji, Union Minister of State for Ministry of Electronics and Information Technology and Skill Development and Entrepreneurship. Shri E. Magesh, DG C-DAC, Ms. Sunita Verma, Scientist G and Group Coordinator from Ministry of Electronics and Information Technology, New Delhi, Colonel A.K. Nath, ED C-DAC, distinguished experts, Shri Dirbari Sahab, distinguished experts and participants. A very good morning to all of you. Quantum computing, the kind of presence I see, the experts and participants who are present here in person as well as through online virtual mode, it shows how much we all are interested to start a new journey of quantum. I think it started with 1900 when Max Planck, he came out with a very important theory of physics, and he spoke about that the light is not a continuous wave. It is absorbed and emitted in terms of particles, and which he called quanta. And later on, it was progressed by multiple eminent physicists and scientists who worked in this area. And in 1927, I think, there came a very important Heisenberg uncertainty principle, which is supposed to be the cornerstone of the quantum mechanics. From there onwards, till the 2022 Physics Nobel Prize, which is given to 3 eminent scientists for their respective work in entangled photons, it shows our fascination and our attraction towards this mystic phenomena of quantum, may it be superposition or entanglement. And now we all together want to exploit these amazing properties to convert into whatnot, quantum computer, quantum using the cryptology, using the quantum principles, sensors, devices, so on and so forth. India has also started taking important steps in this direction. I was expecting that someone from DST to speak about National Mission on Quantum Technology and Applications, NMQETA, which is supposed to be implemented by DST. And it is under discussion, and very much sooner than later we are going to see this national mission to start implementing. DST is going to be the implementation agency for this, and with the partnership of Ministry of Electronics, Department of Telecom, ISRO, Department of Atomic Energy, C-DAC, I think as a very important knowledge partner for some of the technology hubs, which I understand. And so many academia, industries, ICER, so on and so forth. And this very important national mission, we are expecting to create convergence, synergy across 4 important verticals: the communication, sensors and devices, cryptology, quantum sensor, and materials. There is huge scope to work in this direction. And a natural question comes that why a national mission with thousands of crores of funding? So if we delve into this, there is huge scope of joining this journey with global partners. If we talk about the data and statistics which market is predicting, then around in 26, 27, the quantum technology is expected to mature. And the predictions are there. Of course, these are predictions. The time would say how much we are going to leverage this. But the predictions are there that around US $300 billion kind of economy boost it can provide to the Indian economy. And therefore, interestingly, the government is planning under the NMQTA with the ambitious target of creating 50-qubit quantum computer by 26. I understand it's a very ambitious target, and unless and until we have this kind of vision, we cannot put all our energy and efforts together to achieve those targets. So this is one of the important things which talks about the potential market for the quantum technologies. Globally, around 100 of startups have already started functioning in various areas of quantum cryptography, QKD, most importantly QKD, because a lot of success is being seen in this direction, and so on and so forth. And if we talk about with the US and European Union, who are contributing about 60 to 70 startups each in these countries which are functional, and they are ready with the market-ready products. If we talk about the India startup ecosystem, we also have some 12 to 13 important startups who are at various stage of R&D, productization, etc. Two of them, I think QNew Labs in Bangalore and QPi AI, they have shown a very successful market-ready trials. They have the products, and they are aligning with ISRO and IDEX for coming out with the QKD solutions and for space, using the quantum communication using the space. So all these things are happening side by side. Ms. Sunita Verma has also spoken about Makan and so many initiatives which MeitY is already taking care of. So ecosystem is ready. Now it is a time to come together and synergize. The next step is R&D. There is immense potential to take research and development in all aspects of quantum. May it be the creating of open standard architecture, the data structures, creating algorithms, encryption technologies, decryption technologies, creating hybrid to classical type of machine learning QML algorithms. And so R&D is something which PSA offices is intended to put a lot of focus on R&D so that we can create those kind of capabilities which are expected through National Mission of Quantum Technology. Various academic institutes, I think IIT Madras, IIT Delhi, IISER, and C-DAC, they are working to create capacity building initiatives, creating different kind of sandbox, applying sandbox approach to create instruments for testing, encryption, and finding new ways how the error correction kind of things can be done to stabilize quantum computers. The third thing and very important thing is how to create a vision to actually exploit the potential of this technology. So for that, we need to identify areas. May it be weather prediction modeling, may it be using the quantum for bio-related research, may it be even using for the financial stock market kind of thing. So it is understood that quantum has that kind of potential. The requirement is to come together, create those kind of platforms where all of us can jointly join hands and move forward and get a kind of early mover advantage, if we really, so to say, if we really want to harness the potential of this technology. Professor Barry, I spoke about IBM computer machine. If we see that physically, if you see the pictures, of course I haven't got any opportunity to see it physically, but if you see the pictures, they appear so similar like old mainframe classic computers. But we know the classic computers they have traveled so long. They moved to desktop, they moved to laptop, now we have in our palm, and even our smartphones are some sort of having those kind of capabilities. which earlier big machines were having. So we all are moving with classic computers. And as Professor Berry spoke about, it will take, I think he was talking about some tens of years to move up to that state. But however, the progress is so fast. When we were studying the physics and Schrodinger equations, we never thought of that in our lifetime we would come across this kind of progress in quantum computers. So I'm very much hopeful that together all of us can embark on this journey and can see all these things happening so soon. This is what I wish, and I stop here with the best wishes for the symposium to success. And I'm going to stay here to listen all of you for another day. And I hope by the end of the symposium, we all are enriched by collective learning and knowledge sharing. Thank you very much. I stop here.
Thank you so much, ma'am. I now request Shri E. Magesh, Director General, C-DAC, to share his thoughts.
Shri Rajiv Chandrasekhar ji, Honorable Minister of Skill and Entrepreneurship, Minister of Electronics and IT. Sunita Verma Madam, Group Coordinator, MeitY. Dr. Preeti Bansal, Scientific Advisor to PSA. Dignitaries on the dais, off the dais. Speakers from the industry, academia, and other research institutes. Good morning and welcome to this symposium on quantum computing and basic building blocks. I'll be very brief about C-DAC. C-DAC has been into high-performance computing for the last 3 decades. And we have mastered the art of integrating compute, storage, memory, and communication. And we have had multiple generations of systems being developed from modules to racks and to clusters. And today, over the years, we also got enriched by the merger of some of the other organizations called ER&D, CIT, CIDT, and NCST. So these organizations bring to C-DAC a lot of expertise in electronics, subsystems, and software technology. And therefore, we are very much enriched with this. And as Madam has already told, in quantum, we have done work on quantum simulator. It is basically to understand how a future quantum computer will look like and how to be ready with some software which will easily run on that and start making applications out of that. Makan was another project in which we are able to use the existing photonics connection between cities, that is Bangalore, Chennai, and to deliver quantum key resistant keys on that channels. Going forward, we'll also explore the possibilities of extending the communication up to Kanyakumari and up to Delhi from Bangalore. This is in the making. And then we have a program called DIRV processor program of the Ministry of Electronics IT, under which we have already fabricated 2 chips, one 32-bit chip called the DIRV Tejas chip, and then the next one called the DIRV 64-bit Tejas. Both have been manufactured. The second one can run full complete embedded Linux, and we are expecting the chips anytime soon. So some of the other projects that is being taken up by the whole of C-DAC, especially in the area of space, where we do work on measuring the burn rate of a torpedo or a rocket or a missile system. And also we work on some of the sub-water, underwater systems, where we evaluate many of the naval ships in the country. And also many other applications which are being run under the NSM HPC systems. All of these, they all need a high computation requirement. So there will be a lot of memory movement, there will be computation requirement, there will be storage needs. They all work around complex fluid dynamics, CFD problems. Going forward, these systems are not enough. We need to go from terabyte systems to exascale systems. And still, it may not be sufficient going forward. So the natural progression would be to go into quantum computing. So now there's another problem, whether we have to define the approach the quantum computing from the programming point of view, from the normal legacy software modeling, or should it be a different one? This is something that through this symposium we would like to know from all of you, from the academia, industry, and all others, whether such an approach is feasible or we should take a radically new approach, whether we should unlearn what we have learned in the past, whether we'll have systems which are going to do specific functions, or there is going to be a software development kit which will allow you to talk to these fundamental qubits, which could be the ion trap or the superconducting or the photonics. And then at the same time, you will have a different kind of SDK to work with different applications. Or this is the road we are going to take, or there is going to be one common platform so that all applications come on board, or all underlying fundamental qubits are going to interact. These are some of the key decisions which needs to be taken up in this symposium so that our roadmap gets very clear going forward. As you all know, that we need a readout system, we need control electronics. I mean, you can see from the exhibitors today, we have Keysight and Tektronix. So if you ask them, they will say, we make high impedance probes. What does it mean? We have taken this for granted for a long time. High impedance probes means with the least interference, we would want to sense a signal. The same applies to quantum world also. We are dealing with subatomic particles. So without disturbing the fundamentals or energy levels, we need to sense those parameters. So there may be one way or multiple ways of detecting signals and controlling them. So it is very important that we have a multi-pronged approach in both at the sensing level as well as software and as well as making system, the whole systems. So there is a need for having a quantum OS also. So in order to make some standardization. So there could be multiple SDKs, maybe a multiple quantum OS also is a possibility. But at the same time, we can't go too divergent. So we should have some commonality, and we can work towards a common quantum OS going forward. I am fully convinced that this symposium is going to bring in those kind of thoughts into this and make it practically possible in the near future. In concluding, we believe that this symposium will help in creating a platform for the development of new technologies, products, services, quantum computing, and help in making a significant impact on various industries. Thanks to one and all for coming up to this symposium, make it a possibility. Thank you all. Bye.
Thank you, sir. Today, we are extremely privileged to have the address from Shri Rajiv Chandrasekhar, Honorable Minister of State, Ministry of Skill, Development and Entrepreneurship, and Ministry of Electronics and Information Technology, Government of India. Shri Rajiv Chandrasekhar is a man of many talents. He is not only an exemplary parliamentarian, but a computer scientist and an entrepreneur too. As a master's in computer science and honorary DSc, and as an entrepreneur, he has invested and built many valuable brands. His 30+ years journey in technology has included being a key part of Intel's path breaking 80486N Pentium microprocessor in the Silicon Valley, to building one of India's first and largest cellular mobile company. He is connected with us virtually and will be addressing us online.
unfortunately, due to absence of two speakers, we'll have to wait for our Honorable Minister, who had given us the time of 10:50. His office is already logged in and joined, but he'll be joining dot at 10:50. So please bear with us till that time, and we'll wait because two speakers dropped out and their time could not be, readjusted accordingly. So we'll just wait till 10:50 for the minister to join us, because he's extremely busy. He was supposed to visit Kerala, and he still said that I will be joining you from there. He was very much interested in addressing this symposium when I went and met him personally. And now, since his visit is over, he cancelled. He's in Delhi, but he'll be in different meetings. So since he has given his time to us, we request you to bear with us and kindly wait till 10:50. We can set our clocks after that and let the symposium proceed. So let's wait for him. Please let us know when he joins, right? Yeah. क्या जी? You're requested to kindly settle down. The Honorable Minister will be joining us very shortly. Please settle down.
Meeting. Conference, they have a group of people.
Very good morning, sir.
Morning.
This is Colonel Nath, and we're really grateful to you that you could take out time to address this symposium on quantum technologies ecosystems, which we are organizing in C-DAC with the basic aim of synergizing all the different kinds of efforts which are happening towards quantum computing, quantum technologies, both in the nation as well as abroad. And we have a whole lot of speakers, delegates and companies which have come to C-DAC, not only from the national ecosystem, but also from the international ecosystem. And we have a huge amount of accomplished keynote speakers who are joining us from online, or some of them even come here. The primary ones being Professor Andrew Briggs, who is the professor in Oxford, who has come here physically, and we'll be having many other keynote speakers. So without wasting too much of time, I hand you over to the audience, and we'll be really glad to listen to your words of encouragement for all of us. Thank you, sir. Over to you.
So, good morning, Colonel Nath, and to all those attending this C-DAC Symposium on Quantum Technology and the ecosystem. Thank you very much for inviting me to speak. I can certainly start off by saying that I am not a quantum computing expert. I have all my life dealt with zeros and ones, and I'm a classic Turing machine student, and from that generation of computing, and so therefore I will not pretend that I can contribute too much to your deliberations, excepting to say that it is certainly something that in the government as a minister, and as certainly as somebody who spent several decades in technology, that I anticipate is going to be one of the next big ideas that will disrupt the world of computing in general, and computing in particular, and technology in general. Let me just share a few thoughts, a few backstory, context thoughts of mine, and then I will leave you to your deliberations. As you know, 2015, when the Honorable Prime Minister of India, Prime Minister Narendra Modi ji, launched Digital India, and some of you have heard this before, so I will say it anyway. He had three broad goals in his mind, three broad ambitions for India in his mind. He, of course, wanted to deploy technology in a way that would transform people's lives, change the narrative of large democracies being dysfunctional, bring trust into the relationship between government and citizen, which is so important in large democracies like ours. That was one of his objectives. The second objective was he certainly wanted, and he looked forward to, our digital economy component of our overall economy, opportunities for young Indians in entrepreneurship, startups, to also grow as a consequence of adoption of technologies in our way of life and in our governance models. And the third one was a lot more strategic in the way he viewed technology. He said that India for many decades has been a consumer of technologies, and we want to be going forward, if not being the producer of technologies, but certainly having the capability to produce, architect, design devices, products, solutions and platforms, along with other countries who choose to do the same thing. So those were broadly the goals in 2015. And as I said recently, I was in the audience when he laid out those goals, and even I was healthily skeptical about how far we would travel and how far we would progress. But here we are in 2022, a nation that is become a preeminent nation in deploying technology in governance and for improving citizens' lives. We have created an innovation ecosystem that is just through its own, in a sense, self-fulfilling momentum, creating confidence and aspirations and ideas unprecedented in the history of India amongst the youth of India. And third, in many, many key areas, ranging from compute to semiconductor devices to the blockchain to artificial intelligence, we are setting forth to create products and solutions that could be shared with the rest of the world, ranging from the India stack on one hand to many, many other devices, products, and platforms. Now, it is clear in our mind as we seek to build these capabilities, these strategic capabilities, these capabilities, that semiconductor on one hand, electronics on the other hand, and microelectronics on the other hand, and compute, and high performance compute and quantum compute certainly becomes a very important part of this capability matrix that we are building for this India Decade. And the India Decade phrase is a phrase that has been coined by our Honorable Prime Minister, and in a very clear sense lays out our ambition that we see the coming decade as a decade full of technology opportunities, where disruptions and changes will be normals, and that India will play, and Indian entrepreneurs and Indian R&D institutions and the Indian ecosystem in general will play a role in the shaping of the future of this technology. So quantum is certainly one of the areas that we are deeply focused on. You are aware in this audience that the government of India, as way back as in 2000, has announced 8,000 crore or $1 billion for a period of 5 years to be spent on and to develop applications and core technology on quantum technologies and applications, the NMQTA program that is being administered by the Department of Science and Technology, of which MeitY is also a member. And that was driven in large part to our Prime Minister's vision, and he said on January 3, 2022, and I quote, "Today India is making its mark in the world as a quantum frontier. India is moving fast in the direction of quantum computers, quantum chemistry, quantum communication, quantum sensors, quantum cryptography and materials." End quote. This is what the Honorable Prime Minister laid out in January 3rd, 2022, about a year ago. And we have this budget that has been set aside, the funding that has been set aside. Now, the vision is there, the capital is there. Now it's a question of really working together and building an overall ecosystem of innovation, startups, R&D institutions, the higher academic institutions, domestic companies, foreign academics, and all of that, creating an India-centric quantum ecosystem that works very well with other partners and players around the world. So this is really our vision. We are committed as a government to realizing this vision, and I said, as I said myself in September 2022, that technologies such as quantum computing will be at the core of the country's growth and expansion in the India Decade. So our vision is to run the whole spectrum. On one hand of the spectrum, at the cutting edge, we intend to build capabilities in quantum and high performance computing. And on the other hand, we want to build consumer products, digital products and devices and solutions that will allow more and more digital empowerment of the 1.2 billion Indians that are being connected to the internet by 25-26. We are the largest connected nation in the world today, and we will certainly by 25-26 reach a 1.2 billion Indian connected to the internet and experiencing the power of digital and the power of compute. I will not add too much more to this, excepting to say that for those who are skeptical, those who are cynical, as is normal in these kinds of conversations, I just point to how far we have traveled in the last 6 years. Just a few years ago, we had little or no electronics industry worth the name, and we have created almost certainly from scratch very fast growing, fast charging, and increasingly becoming a trusted part of the global supply chains global value chains for electronics, which was, as you know, dominated for several decades by our neighbor in the north. And so India has, to quote our Honorable Prime Minister, we are sitting on a very interesting and exciting inflection point in our own growth, as in terms of capabilities, in our own growth as a partner to the world's nations and consumers on all things technology. And in terms of our own capabilities in India and capabilities amongst our young Indians and the startups and the academic ecosystem that support our quest to creating these cutting-edge technology capabilities that are so relevant to shaping the future of not just technology, future of business, future of economy, trade, and indeed even geopolitics going forward. So I will leave it at that. I wish the symposium all the very best. To the visitors who have traveled great distances to be part of this, I thank you for your presence, and I thank you for contributing to improve the quality of the debate and discourse in India around our ambitions of creating and or being a partner to the next generation quantum technology ecosystem. Again, thank you all for being here this morning. Thank you for inviting me. Thank you. Jai Hind.
Thank you. Thank you very much, sir, for sharing your very valuable thoughts with us. You've always been very supportive in C-DAC's growth in the National Supercomputing Mission, our microprocessor development programs, and our other initiatives. And I think we are well educated by your thoughts, and it will definitely help us in shaping our initiative towards the quantum technologies as we proceed ahead, sir. So we really thank you for the time and effort you made to set aside your time and address all of us. Thank you so much, sir.
Thank you.
We now request Colonel Eknath to kindly felicitate the dignitaries. I also request our Director General, E. Magesh, to kindly felicitate Colonel Eknath. With this, we conclude our inaugural session. In the series of talks, we are delighted to have with us Professor Andrew Briggs, Oxford University and Chair Quantrol UK. I kindly request Professor Briggs to deliver his keynote talk. Over to you, Professor.
Well, thank you very much for your welcome. It's an enormous honor to be here. And I bring you, can you hear me? All right, is that better? Okay, good. You know about the talk where the speaker was starting and people looked puzzled. And he said, can everybody hear me? And someone at the front said, yes, but I'll gladly change places with someone who cannot. So I bring you greetings from Oxford and feel very honored to be able to participate in the journey that you're embarking on for the next phase in India's development of quantum computing and the associated science and technologies. Now, why quantum? Well, quantum computers play by different rules. They'll make certain calculations possible that will never be feasible on classical high-performance quantum computing. And there are really two kinds. There's analog quantum simulation, which works by building a quantum replica of the real thing. And then there's digital quantum processing that's based on quantum gates. And the amazing power of quantum information processing comes from these weird but wonderful quantum phenomena of superposition and entanglement. And together these give quantum computing its exponential power. And it was in recognition of the benefits to mankind that may come from the fundamental discoveries in the science that the Nobel Prize in Physics for 2022 was awarded to three of the people who've really contributed to the underpinning science that makes quantum computing possible. And the magic of quantum computing can be summarized like this, that a classical bit can be either a 0 or a 1 for conventional digital information processing. Quantum information processing uses quantum information, which can be simultaneously a 0 and a 1 at the same time. And one of the best ways to visualize this is to think of a globe of the Earth, with a 0 as the North Pole and a 1 as the South Pole. And the information is, as it were, a point on the surface of the Earth. And crucially, to describe that point, you need both the latitude, how far north-south it is, and the longitude, how far east-west it is, which corresponds to the quantum phase in the mathematics. So Nairobi and Singapore are both on the equator. They're roughly equal amounts of north and south pole, but they have very different longitudes. And it's that phase information that's crucial to the benefits of quantum computing, and which is very delicate, which requires great care in creating and preserving the quantum states that are at the core of quantum information processing. Now, the investments in quantum information processing worldwide are huge. This map is taken from a World Economic Forum report from last year. You should look at it with some skepticism. I'm not sure that all the numbers are quite right. I think Finland probably has more than the amount of money that's shown, and some key players like Austria and Switzerland seem to have got forgotten altogether. But the numbers are very big, and you notice that the numbers are not necessarily proportional to the size of the country. So some of the big contributors, like Austria, like Finland, like Switzerland, are countries with relatively small populations, less than 10 million people for each of the examples I've given. And the other thing that you'll notice from that map is that for a country with the size and the capability of India, 1 million is rather a small number, actually. And that means that the resources, the limited resources that are available will have to be used extremely well and extremely effectively. And you get a similar picture if you look at the quantum computing startups. This is a comparison of the situation in 2015, and which are the smaller blue dots, and the huge growth that there's been in startups between 2015 and 2051. And again, you see that the entrepreneurialism is not necessarily in proportion to the population of the country. There are some very, very impressive hotspots. Now, the Nobel laureate Richard Feynman famously said that what I cannot build, I do not understand. And that is a key message for this journey of quantum computing, that you're never going to be a leading player if you simply purchase from other people. And that's why I believe that open quantum architectures will be essential for giving the flexibility to contribute where there's strong expertise, to develop new expertise where it doesn't already exist, and to adapt to particular applications as they emerge, and as new technological improvements are made, which might come from India, but they might come from anywhere else in the world. One of the questions that was asked to Barry Saunders earlier was about the different platforms that there are for quantum computing, the different implementations. And they are manifold. One that has hit the headlines probably more often than others is superconducting systems. IBM has a clear roadmap for its development of superconducting systems, leading out to beyond 2026. And as Barry was saying, they've got their 433 qubit machine, but they're now almost taking a step backwards to a smaller machine. And there's a well-developed way of making quantum computing with nodes. And a rather important result from my colleague at Oxford, Simon Benjamin, some years ago, is that if the nodes themselves are good, the fidelity of the connections between them do not need to be so good for you to achieve scalable quantum computing. So it's rather tolerant of defects in the connections between the nodes. Of course, IBM's not the only player. There are other companies, some of them represented here at the conference. Then there are trapped ions. This was the first way that people thought of doing quantum computing, with a very important scheme from Ignacio Cirac and Peter Zoller. And the ions still achieve the highest fidelity of any implementation of quantum computing. And fidelity is worth having. So here is some experiments from one of the ion trap companies, Quantinuum, which Barry mentioned. And there they're trying different 5-qubit surface code experiments to investigate the possibilities for fault-tolerant error correction. And here is that particular company's roadmap. And they're showing against time something called quantum volume, which is a way of measuring the power of a quantum computer that takes into account not only the number of qubits, but also the fidelity of operations. You can do quantum computing with photons. Photons are, of course, the world's first quantum particle, as we were hearing. You were telling us about Max Planck and his quantization of light. And photons can have quantum coherence times of 13.8 billion years. We know that because we still receive photons from the earliest days of the universe. But they're very fragile and they're easily lost. And for a long time, people thought you could not use them for quantum computing because they don't interact. So how could you do operations? And then a brilliant bit of work by Danny Nill, Ray LaFlamme, and Gerard Milburn showed that if you use post-selection, you could indeed do linear quantum computing with photons. And there's a lot of effort to try to build photonic chips in silicon that will enable photonic quantum computing to take place, like the company Psi Quantum that Barry mentioned. A more recent player on the stage is cold atoms. There's at least one person here who's worked in cold atoms. Where is he? Worked with Chris Foote in Oxford on cold atoms. And for a long time it was thought that cold atoms would only be suitable for simulations and not for gate quantum computing. And that all changed with the discovery that if you excite the cold atoms to Rydberg states, very highly excited states, then the electric dipole can enable you to do gate quantum computing where the dipole controls the response of a neighboring ion trap, a neighboring cold atom. So you can make these things in sort of like egg boxes of created by lasers, and you can have very large numbers of them. So this is a rather recent entrance to the field of quantum computing, but already results are being obtained. And then, in a sense, one of the earliest, but in another sense, one of the last possible implementations of quantum computing is spins in silicon. It's one of the earliest because for over a quarter of a century there's been a major effort at the University of New South Wales in Australia to develop quantum computing based on spins in silicon. But it's been a long, hard journey, and still the number of qubits, connected qubits that have been achieved in silicon is relatively small. But progress has been made at an astonishing rate in the last couple of years, and already now people are demonstrating error correction in silicon qubits. And in the last 2 years, there's been a huge increase in the fidelity of gate operations that can be achieved with silicon qubits. At least 3 independent university groups achieving fidelities of over 99%. And actually doing demonstrations like this and producing an architecture. This is a 6-qubit quantum processor in silicon where universal control was achieved. So what are we to make of all this? All these different possibilities, and within each of these families, there are at least 5 different ways of doing spin qubits in silicon that I know of, 2 of them developed by former students from my own laboratory. How is one to decide where the future lies and which of these different implementations to consider? Well, there's a report that's done by a former colleague at Oxford called Mike Mosca. He's now based in Canada. And he produces each year, with a colleague, the Quantum Threat Timeline Report. The threat because of the threat to classical cryptography, but it's a wider report than that. And here is the summary of the 22 experts' opinion, which was released in December. And here he's asked about, for this particular survey, 36 people, their names you'd recognize, their top names in the field around the world, both in academia and in industry, mainly early stage companies and other walks of life as well. And you can see a sort of ranking. This is people asked, for example, dark blue it means that the person thinks that it's a lead candidate for quantum computing. And superconducting system scores highest. But even superconducting systems, it's less than half of the experts who were asked who think that it's the lead candidate. Plenty of them think that trapped ions are the lead candidate. The others have different numbers, but there's no consensus. There's quite a spread of opinions, which means that, in my view, it's too early to say which is going to be the lead candidate. When I took on the directorship 20 years ago of the UK national effort, people would ask me, well, which of these different methods do you think will be the eventual means? And 20 years ago, I would say to people, well, it's too early to say. And I almost feel it's too early to say still. And that's why I think it's so important that any quantum computing effort is based on an open quantum architecture to give flexibility. So why be open? Well, quantum computers are expensive and time-consuming to build, and conventional computing has shown that open architectures reduce costs and accelerate innovation. So you get the benefits of laying the foundation for creating quantum computers from components, and you accelerate innovation by enabling a broader set of companies, and I would say of scientists and individuals in academia as well, to contribute to quantum computing. And if you're going to have an effective open quantum architecture, you've got to identify what the main building blocks are, and crucially, the critical interfaces between them. Because you've got to have versatile ability to fit the different building blocks together. And initially, the standards for the interface may just be de facto. The day may come when people actually get together and agree what the interfaces should be. So the quantum ecosystem is rapidly evolving, and you can see there that there are some companies that are pretty wedded to a sort of closed architecture, you know, the quantum computing equivalent of Apple, where you do everything within the company. But there are a growing number of companies that are a bit more like Dell manufacturers of computers that are willing to fit in different components. And now we see an increasing number wanting to work with full open architecture implementations. So what is the open architecture? Well, you've got sort of three layers. You've got the quantum applications. These are tools for creating uses of quantum computing that will actually bring benefits to society. They will contribute to human flourishing. You've got the quantum control. That's the means of controlling the qubits, executing algorithms. And then the quantum environment, that's the hardware and what actually drives the hardware. So the quantum application is the end user applications, the application development environment, the quantum circuit compiler, the sort of things that C-DAC has many, many years of experience and expertise in. And then you've got the quantum control, which consists both of the control software and of the control electronics. And I believe that those are areas in which C-DAC has very great expertise, specifically relevant to quantum computing. And you might, into this, insert the interface with conventional classical supercomputing, because for the foreseeable future, I think your quantum processor units will be embedded in supercomputing capability. And I'll come back later to the importance of machine learning for tuning and characterizing the quantum processing unit. And then you have the quantum environment. It could be cryogenic if you're going for solid-state quantum computing. Of course, other embodiments need different kinds of environments in which to work. And you can sort of think of a roadmap for open quantum architecture. I believe that within this year, before the end of 2023, we're likely to see 25 qubit systems already implemented in open quantum architectures. And I would hope that within 2 years from that, by 2025, we'll be well past the 100 qubit mark for open quantum systems. So those are open quantum systems. What are the open quantum challenges to be addressed? There are many, so I'm just going to give you a sample of the ones that sort of float to the top when I think about the challenges facing the development of quantum computing. And Barry Saunders gave one or two useful references to others who've compiled their own lists. One is fault-tolerant error correction. For a long time, it was thought that error correction would not be possible in quantum computing because of something called the no-cloning theorem, which would prevent the sort of error correction methods that are used in classical information processing from being deployed. Basically, because you can't have a fan-out operation in quantum. And then someone who I've written a book with, Andrew Steen, we wrote a book together called It Keeps Me Seeking. Andrew came up with a very, very clever scheme that showed you could circumvent this problem of the no cloning theorem, and that fault-tolerant error correction would indeed be possible. And then others around about the same time came up with similar schemes. So fault-tolerant error correction is possible, and the fault-tolerant circuits, as Barry was explaining, contain the spread of errors as you scale the thing up. And that's been demonstrated. This is an example from the laboratory of Andreas Wallraff in Switzerland in a superconducting quantum circuit. Here's an example of fault-tolerant error correction in an ion trap experiment from a US company founded by Chris Munro. And here's what the experts think. You know, what's the likelihood of the realization of a scalable logical qubit as a function of time? The reason it's hard is because there's a huge overhead in the number of qubits that you need if you're going to do error correction. And it gets much, much worse if you have a lack of fidelity. That's why fidelity is so crucial in reducing the overhead for error correction. And again, you can see there's a spread of opinion. You know, of the 40-something people who were part of this survey, which was a year earlier, something under half think that it might be feasible in 10 years. You know, this is a big challenge. Quantum computing needs patient investors because it's a long-term endeavor, and those who look for quick returns may be disappointed. Another challenge is scalability. Barry mentioned that John Preskill, who created the idea of noisy intermediate scale NISQ quantum computing, thought it would only be a temporary time. So we're going to want to move to bigger quantum computers. Connectivity is a challenge. And another thing that's a real challenge is tuning and characterizing the qubits. I don't know if you know the difference between tuning a piano and tuning a harp. Pianos, by and large, have steel frames, and if you get your piano tuned, it's likely to stay in tune for 6 months or more. Pianos are quite good at staying in tune. Harps have wooden frames, and when you tune a harp, you're quite lucky if it stays in tune for a day, actually. Every harpist who goes to a concert has to arrive early because the variations in temperature and humidity mean that they've got to tune their harp up from scratch for that particular concert. And I'm afraid to say that quantum processing units are more like harps than pianos. They're delicate, they go out of tune, they need to be kept in tune. Humans can learn how to do it, but it takes time to learn how to do it, and it takes time for a human to do it. And as the computers scale up, that's going to become increasingly unfeasible. That's why we think that the use of machine learning for tuning quantum computers will be so important. And this is just a result from my own lab, which I'll talk a little bit more about in the talk that I give this afternoon, of the way that machine learning does seem to be able to learn how to tune and maintain in tune qubits. And again, I'll say more about this afternoon, but it's now becoming commercially available. The third challenge is applications. And we're still in the early days of identifying what the applications will be of quantum computing. We all know where we'd like them to be. We can make lists of problems to which we'd like quantum computing to make a contribution. I thought Barry summed it up very well. Either quantum computing will fail, in which case it'll have no useful applications at all, or it'll succeed, in which case it's hard to think of any area where there will not be applications. As quantum computers are built and people can get more and more experience in using not just small-scale simulators of 19 qubits, but actual quantum computers with large numbers of qubits, I have every hope that human ingenuity will get better and better at finding ways of developing these applications. But it is a challenge. All right, here are some of the areas to which people would like to find applications, where there is a prospect of applications. But if you look at the quantum algorithm zoo that Barry mentioned, and you look at the number of papers that have been published, you'd expect to see, I would have expected to see an exponential rise in the number of papers. But that has not, in fact, been the case. It's sort of pegged, you know, it's fluctuated up and down. But it hasn't been as productive as I would like to have seen it be. So that's a real challenge to develop those applications and the algorithms that will support the applications. What do the experts think? Well, this is the 2022 estimates experts of the particular application of breaking RSA encryption, public key cryptography, within 24 hours. And again, you'll see there's a spread of opinions. There's no consensus. And again, you'll see the timescales are very long. So even 30 years out, there are only 11 experts who think it's 99% probable that it'll be broken by then. So again, you get this sense that you've got to be patient, you've got to think long term, and you've got to use very effective, make very effective use of limited resources to take this forward as fast as possible in the best way possible. And then the fourth challenge that I want to offer you is the challenge for social responsibility. People are only just beginning to think of what the social implications are of quantum computing. In my own lab, we do a lot of machine learning for quantum computing. I'll tell you a bit more about that later on. But in machine learning, we already know that there are huge societal challenges. We know that machine learning can bring very big benefits. We've seen the benefits in healthcare, in machine learning reading of scans to detect early stages of cancer and other diseases. In diagnosis, we're seeing the benefits of machine learning. But my goodness me, we're also seeing the societal harm that is caused by machine learning. A particularly poignant case in the UK was this lovely girl called Maury Russell, who took her own life at the age of 14. And in September, the coroner reported, and it was quite clear from the analysis of what was on her phone, that machine learning, through the big data companies, the social media companies, had been targeting her with news stories about teenage depression, teenage anxiety, and I'm sorry to say, how to take your own life as well. And so those of us who care about the use that's made of the technologies that we develop must engage with those who are well placed to consider the social responsibility, the social scientists, the policymakers, the legislators, the healthcare workers, so that we address the societal challenges. And because I care so much about these things, and I think it's right that some of us in technologies should engage with the issues, with our friend Michael Rice, I wrote a book on human flourishing, where we seek to identify, you know, how you think about what human flourishing consists of, and therefore what your criteria are for the deployment of, well, for coping with the changes that we're seeing in the world, one of which is the changes in the development of technologies. And in my own company, Qblocks, the first two tasks we undertook were the capitalization table, the cap table, the founder shares, in other words, and the company values. And we developed the company values. We originally developed 5, then it grew to 7, and then we were able to distill it down in the end to 3. But the overriding company value is that the company exists to promote human flourishing. It exists to solve problems without creating problems for society. And so the values are the values essentially the values internally to the employees, those who work in the company, the values to the people we interact with, the suppliers, the customers, and thirdly, but only thirdly, the values for the investors and creating long-term values for those who put their money into the company. So that's really my conclusion. This is such an exciting stage in the journey for India. I feel hugely privileged to be able to come and be part of discussing the journey with you. I think it's very exciting. I think it will best be promoted by open quantum architecture. And I hope that all the developments will be ones that promote and increase and enhance human flourishing.
Thank you, Professor. Sorry. So this was a very exciting talk. Thank you for enlightening us on the open architecture. You showed us what are the elements of the open architecture, why it is important in terms of innovation and cost optimization, perhaps energy optimization as well. And you also showed us that how the world, how it's trending. Like what are the companies focusing on closed environments, and what are the companies, proliferation of startups and people moving towards open architecture. I think the world is slowly going to adopt to this particular type. And we are wholeheartedly thankful and grateful to you, sir, for taking all the efforts and coming here in Pune, in C-DAC, to share your thoughts and for the technical discussions which are going to have. Thank you, sir. So now the floor is open for questions.
Professor, I would like to know the clarification. We have given a table, like RSA breaking in 30 years will be probability is 99% for 11 people. How this data is arrived, like subject to analysis, the crowdsourcing collection, or you have any methodology making a data this?
Sorry, was your question the methodology of collecting the data?
Yes. Okay. How you arrived the table, the probability of 99%, 95%,
so you're
70%.
thinking of
how you are,
for example, this table. So you can Google quantum threat timeline report, and there they will tell you about their methodology. I think it's very important to say that this is just an impression, okay? It's not what in the social sciences you would demand of proper randomized trials and so on and so forth. It's not meant to be that kind of rigorous social science. It's more to give you a sort of impression of what many of the leaders of the field think. So, people ask me, which do I think is the best candidate? People ask experts like Barry Saunders, what do they think is the best candidate? And you just, through the quantum threat timeline report, you get a broader spread of opinions from geographically, from people who've got different bias towards different kinds of technology, because you can imagine each manufacturer thinks that theirs is the best technology. So it's a way of getting a broader spread of opinion. But the key message is there's uncertainty. We don't actually know. We've just got to embark on the journey and discover as we go along, but drawing on the best wisdom we can from some of the best players in the field as to what it looks like to them.
Sir, you have a question?
I think she's fine.
Do you want to come and stand here and use this microphone? Or there's a microphone back there, if that's helpful. But you may have to lower it to be appropriate for you.
Thank you very much for very enlightening presentation. It's so interesting that we have started thinking about aspects of machine learning. We all are talking about trustworthy AI and all these negative aspects of this technology. So what do you think that how this your proposed open architecture could handle this kind of very complex problem of machine learning for?
Oh, thank you. Thank you for that wonderful question. One can think of it in two different directions. So I have colleagues in Oxford, but around the world, who are thinking how quantum technologies will accelerate machine learning. So there are ways we think of doing machine learning that may be accelerated by doing them on a quantum computer. It may be because of quantum superposition, so you can consider many different possibilities at the same time through quantum parallelism and entanglement. Or it may be, as Barry showed in his little diagram, that you do quantum annealing, not by thermal excitation over the energy barrier, but by quantum tunneling through the barrier to find a lower energy state. So that's one direction. That's quantum technologies enabling machine learning. The particular work that we do in my laboratory is in the other direction, and that's using classical machine learning to accelerate the development of quantum technologies. And you know, one of the big roadblocks to scalability is this issue of tuning and characterizing qubits. And what we found is that by deploying actually quite a rich and sophisticated combination of machine learning techniques, that process can be accelerated, so the machine is faster and better than a human at doing it. But also, of course, it's scalable, because if a machine learning can tune 1 qubit, it can tune 1,000,000 qubits, because you just replicate it. It's more difficult to replicate humans. The process takes longer. And so we think that the machine learning could accelerate, well, we know that the machine learning can accelerate the tuning and characterization of qubits. But there may be other aspects that are also amenable to machine learning. I would be fascinated to see whether machine learning could accelerate or to optimize the use of a quantum processing unit within high performance computing. So how do you optimize the jobs that you hand over to the quantum processing unit within a high performance computing environment? So I think that's an open question, that maybe people here have already made some progress in it, in which case, please tell me. Well, let me ask the question now. Is there anyone here who's been working on that problem? Anyone here? Anyone at C-DAC, for example? You have.
So I think we definitely started working on a...
That microphone's not working.
Can you hear me?
Yes.
Yeah. So in C-DAC, we definitely started working on the quantum part.
Yes.
Because that is what exactly in the near future visible target to be achieved.
Yes.
And this is the work which we are collaboratively trying to formulate and try to bring in another national supercomputing mission, which we are actually handling now.
Excellent. And are you deploying machine learning in that task?
Yep. Yeah.
Wonderful.
So I think that's an open question, as you are telling. There's
Yes.
a lot of work to be done.
Yes.
But that is what exactly I was constantly telling for past 2-3 years, that is the thing which can be, if achieved, can be a real good thing to happen in near future.
I find that very exciting. Do you think that's a topic in which India could lead the world?
Perfect. That's what exactly I'm trying to put up a full chapter into the National Supercomputing Mission, that how we can make this happen. And all of us have to come together to make it happen.
I love the vision.
Yeah.
Thank you for sharing it.
Thank you. Thank you.
Hello, sir. A quick question, philosophical question. You talked about the open architecture. So we come from the classical computing where we built on von Neumann architecture. So where we have CPU, memory, and different things. So all computing is about stacked architecture. I think I want to ask you, how do you bridge the gap? Like, the physicists build you showed the 3 layers there. The environment is built by the physicist, and then the control is done by the software combination of hardware and all the integrating that. So how do you engineer something that is useful? How do you make your physicist in your lab? You talked about all 3 things, right? Application software is there. So we are all tuned. Most of the people in the computing population in the planet, they are tuned to this stacked architecture where producers and consumers, like you produce a semiconductor, we produce chips, and then somebody given often an interface, and then the software people consume that interface and then build all that. So how do you, in your experience in your lab, how do you envision, what is the roadmap or playbook to strategy to connect all the scientists and different operating at working in different layers?
Oh, well, I love that question. I think it's a really central question. And I think there are so many lessons that can be learned from classical computing about how to make a success of this. And in one word, it's all about interfaces. Every business school says if you're going to have a successful business, you've got to have 2 effective interfaces. You've got to have an effective interface with your suppliers, and you've got to have an effective interface with your customers. And that's true in the computing, the information processing technologies, except there are rather more than just 2 interfaces. And you've got to have good interfaces between them. And it's something we're just beginning to develop in the lab, actually, so it's early stages for us. But we're developing good interfaces, for example, with the different manufacturers of control systems. So you've got various control systems manufacturers represented here, Quantum Machines, Qblocks, Zurich Instruments, and 2 or 3 others. And so in the lab, we're very keen to have a good interface that can work equally well with any of those pieces of hardware. At the moment, we're just doing it ad hoc. So we're just doing it de facto. But what I long to see happening is that as more and more people participate in that conversation and in that debate, so between us, we will develop interfaces which will enable the whole stack to work very flexibly with open architectures.
Hello. Yeah. Very informative talk, Andrew. Thanks for that. I have 2 points. I am from NVIDIA, so first about machine learning you talked about.
Oh, lovely. Glad you're here.
So we accelerating the existing frameworks on GPUs, and they are showing more than 100x performance, which includes your penny lane for AI kind of framework. Those are already implemented at various institutes in globe, and now the more algorithms are being developed. And the approach is what you said, classical through quantum. I mean, using classical approach for quantum. So that we are there, and we can discuss more offline on that. My one question about your open quantum side, and you said application side, is there any standardization for, or plan for standardization for compiler, or any library like QFT or TensorFlow or PyTorch or anything, like which one will use in open quantum side? So that will facilitate more users to develop their application and so on.
Isn't that a wonderful question? And I'd love to know what it looks like from NVIDIA's point of view. At the moment, the approach we're taking is to be versatile between those, because different people, as you say, do use them. And I don't know that any of them has yet arisen as a sort of completely dominant one. I'm not sure it's healthy that one does arise as dominant, actually. But what's your experience in NVIDIA?
For us, we are treating all the architecture equally, and we are trying to make a framework which is working on all kind of framework, like supercomputing, ion trap, and so on. So we have come up with a framework called CODA, QODA, which works on all these systems. And now we are going deeper into that.
I think that's marvelous. I think this is very important, and I love the approach you've just described.
Thank you.
Hello. Yeah.
Hello.
So I got a question about your machine learning can help to fine-tune these quantum-related issues. So how can we integrate this machine learning with this QPU, existing QPU systems? Either it runs on the classical machine, which can support as a controlled hardware to rectify this error correction and support the fine-tune these QPUs.
So how can you integrate it?
Yeah. So this basically, my understanding, this ML runs on the classical systems,
Yes.
which can help supports too.
Well, that's right. It runs on classical systems. I think for the foreseeable future, and possibly forever, quantum computers will be controlled by classical systems. We have one exception to that in my own laboratory, where we've built the world's first single qubit autonomous quantum learning machine. So that can actually work autonomously, entirely within a quantum world. But that's very fundamental research, and it'll be many, many years before that works its way out. We hope it will, because it may have the potential for greatly reducing the energy consumption of a learning machine if we can develop these autonomous quantum learning machines. But they're at a very, very early stage of development at the moment. For the practical implementation, my own company does have a method that we hope will be useful to many people, but there may be other methods of doing it as well. But one of the reasons we founded the company was because so many people were asking us exactly your question of how to implement this in the laboratory.
So one more follow-up with the question had with, because the open quantum architecture, where the application layer and the control layer and the quantum hardwares. Do you think this control and the quantum hardware is loosely coupled? That gives a lot of interfacing troubles. So we are in the physical world, the qubits are more of the physical qubits,
Yes.
wherein the control are loosely coupled. The control electronics and the quantum optics are
Yes.
loosely coupled.
Yes.
So do you think an integrated approach is required, rather we follow the conventional steps with electronics is a dedicated unit which can?
Well, I hope so. I hope so, because if you look at, the glamorous poster boy of all the quantum computing companies, at least the solid-state ones, is this chandelier that they show. And when we take people into the lab, usually it looks like a gray can. And we say, that's what we like to see, because then it's working. The only time you see it as the golden chandelier is when it's not working. And you've had to take the can off, but that's what looks photogenic. But you see that those cryostats, I'm talking now of the cryogenic implementations, the cryostats are getting bigger and bigger and bigger. And the reason they're getting bigger and bigger and bigger is because people are trying to put more and more and more lines down to the qubit. But we know from other information systems that you can use multiplexing. You can send a lot of information down one optical fiber. The technology's not happened yet, but I hope it will, because then you just need one optical fiber or whatever. But you won't need these gazillions of superconducting coaxial cables going down, which is what's so costly and so development intensive at the moment. So I hope that's a temporary phase. I hope more and more will be done at the cryogenic temperature as time goes by.
Yeah, thank you. I think because of interest of time, I think we have to close the session now. Thank you, Andrew. Thank you so much. Can we have a big round of applause, please? Thank you, sir.
Thank you very much. Thank you for participating in the discussion in such an interactive way. Really appreciate that.
Thank you so much, Professor, for your enlightening words. We are glad to have you here. I request Colonel Nath to felicitate Professor Andrew Briggs. We will now have a tea break and resume in 10 minutes for the next session at 12:10. Before that, we will have the formal inauguration of exhibition jointly by Mrs. Sunita Verma and Dr. Preeti Bansal. Tea will be served at the ground floor. Please follow the signage board for the direction. Thank you.
So these two talks you will manage, right?
We will manage.
Okay, okay, then.
And they will call, and then we will hand over session to you. Then you.
Yes.
I request everyone to kindly be seated. We'll begin shortly. Yes. Welcome back, everyone. We now move to the next part of our day today. For both the days of this symposium, our program is structured into different sessions. For each session, we will have the keynote address by the expert in the area, followed by panel discussion on different challenges, opportunities, and takeaways in the respective domain. You can find the detailed agenda of the program in the delegate kit provided at the time of registration. Participants can ask the question to the keynote speakers and panelists, which will be addressed at the end of the talk. There is a mic placed in the center for the participant to ask the questions. The first session focuses on superconducting and photonic-based quantum processor. The session is chaired by Mr. Haribapu Pasupaliti, AD, C-DAC, Bangalore. For this, we have Dr. R. Vijayan, TIFR, Mumbai, as our keynote speaker. He is connected with us virtually. I request him to deliver the keynote address.
Okay, good afternoon, everyone. It's good to be here. There were some excellent talks in the morning today. Thanks to C-DAC for putting this together and inviting me to give a talk here. Apologies that I couldn't be there in person, but I had some prior commitments. So what I'm going to try and tell you today is about one particular hardware platform, which is the superconducting quantum computer, and the challenges in building one. And then I'll keep it in the context of what's happening in India and what we may have to do to push this forward in the coming years. So just a brief revision, apologies to the experts here in the audience, but superconducting qubit can be just thought of as an electrical oscillator, in particular as a pendulum. This one type of qubit called the transmon qubit, which is the most popular one. And it's a pendulum because it's a nonlinear oscillator which allows you to have unequally spaced levels in the quantized level structure. And very simply speaking, we just use two different states of oscillation as our qubit states. So state 0 is the oscillator with 0 quanta, and state 1 is the oscillator with 1 quanta. Of course, there is always 0 point fluctuations on top of that. But that's a very simple picture. It's one of the simplest and the most popular qubits being used for building quantum processes today. And here you can see an image of a 3D transmon. These are much bigger in size, but almost millimeter in size. And they have this squid in the middle, which has two Josephson junctions if you want to tune the frequency of your energy levels, spacing, and some capacitors to give you the capacitor pads to give you the capacitance to shunt your Josephson junction. So the Josephson relations tells you that this has a cosine potential with unequally spaced levels. Here are some typical numbers of the effective inductance and capacitance, which puts the resonant frequency at about 5 gigahertz, which if you convert into temperature units is about 250 millikelvin. And that's the reason we have to operate at much lower temperatures of about 10 millikelvin in a dilution refrigerator, so that thermal energy doesn't really cause random excitations of your system. Because remember, what we are trying to do here is to precisely control the quantum state of these systems. And the fact that we have to use superconductors also gives us the advantage that you can build very low loss oscillators, because here the damping or the friction in the oscillator can be just thought of as the decoherence mechanism, which will cause the system to decay back to its ground state. So you would like to use superconducting materials and for your inductors and capacitors, and also do careful choice of other materials which participate in the electromagnetic excitation of this system. Then in order to control the system, you just need to apply microwave pulses of carefully tuned amplitude and length in time and phase, and that allows you to basically control the position of this single qubit state, as represented on a Bloch sphere completely. So you can control the amplitude to change the frequency of these oscillations, so how fast you can make these changes. The phase gives you the axis of rotation, and the time gives you the time of rotation. So this is sort of the technical part, that how you actually create or control the state of these qubits. But then controlling only single qubits is not good enough. That only buys you these so-called single qubit gates. Some examples are shown here. You can do a NOT gate, which takes 0 to 1 or 1 to 0, or a Hadamard gate, which takes 0 to 0 plus 1 and 1 to 0 minus 1. And these are all basically rotations about the Bloch sphere. So you can basically think of single qubit gates as rotations on this Bloch sphere. And in practice, they are implemented by applying microwave pulses of different length and phase and time. So that's essentially what needs to be done to control these systems at the single qubit level. But in order to really make a quantum processor, you need to be able to create the so-called entangling gates. And that requires the qubits to interact with each other, at least momentarily, so that this entanglement can be created. Now, since these are electrical oscillators for superconducting qubit technology, you can just simply connect two oscillators, say with a capacitor. And this, you can really think of this as a coupled oscillator problem. But of course, there are details about how the frequencies of these qubits are chosen, whether this coupling, which is shown here as a fixed coupler, is tunable or not. And there are various ways of doing that. You can replace the capacitor with actually a microwave resonator that allows you to space the qubits apart on a chip, as opposed to just doing a capacitor. But this is again a fixed coupling, but you also have other kinds of circuits like the one shown here. They use again Josephson junction or squid based circuits and use a flux control to turn the interactions on and off between two qubits. So these fixed frequency and tunable frequency approach are roughly being followed by the two big companies right now. IBM uses the fixed frequency architecture, fixed coupler architecture and fixed frequency, whereas Google uses the tunable coupler architecture. They both have pros and cons, and one really needs to see what one is trying to do to choose the right architecture. Personally, I feel going forward, tunable coupling will be needed because the fixed coupling always leaves some undesired interactions in this thing. So you need to be able to do this in some form to be able to build a quantum processor. And then, of course, you have to measure. And in this circuit QED architecture, you couple a microwave cavity, a linear cavity to your nonlinear qubit. And you couple them in such a way that they are detuned from each other because you don't want to exchange energy directly between them. But by choosing the coupling strength and the detuning appropriately, you can create a situation where the frequency of this cavity now depends on the state of the qubit. So that now becomes a way to measure this, and qubit state measurements are essentially implemented by microwave pulses to measure the phase of a signal which is scattered off this cavity. And that phase shift will change depending on the state of the qubit because the frequency is shifting as shown here with these sort of reflected phase resonance diagrams. And ultimately, these phases have to be resolved very quickly and very efficiently, and so one uses the so-called Josephson parametric amplifiers. So on the top graph here, you see these single-shot measurement histograms, which tells you where the results are lying. So this x-axis can be thought of as a phase, converted into a voltage in digital units. And you would ideally like that the distribution of the values for the 0 state and the 1 state are non-overlapping. And please note this is a log scale, so there's a very small overlap, but you do see these bumps where they shouldn't be there, and these are the errors. And in this particular example, you have about 98.8% fidelity, but this needs to be pushed higher. And of course, this is just an example result. People can now get beyond 99%, and this is very important to both read your results accurately, but also for quantum error correction, which I'll mention later on. So once you have these ingredients, at some level, a quantum computer is very simple to think of. It's just a collection of qubits. And you need to be able to do single qubit gates, and you need to be able to do entangling gates. Nearest neighbor is sufficient, but having extended connectivity is useful, which means that can you do gates between qubits which are not right next to you on a 2D grid, because that's typically how they are made. And here are two possible layouts, by Google and IBM here. And then you also need fast high fidelity measurement and quantum error correction. So, when you present it like this, it's very simple, straightforward, you know what to do. But, there are significant challenges, as all of you know. So what is this challenge? One most fundamental challenge is that these qubits are not stable. When we talk about qubits as a memory element, they are terrible compared to our modern day storage devices. When you like to copy your work from your office and you take it home, you would like that file to still remain on your USB drive. But qubits don't survive for very long, and the time scale depends on the particular hardware platform. For superconducting qubits is somewhere around the 50 to 100 microsecond range, which can be reproducibly made in the lab. And they are approaching a millisecond time scale as well in some state-of-the-art experiments. But this is a problem that they relax, and they also dephase in the sense that the phase information in the qubit also gets scrambled over time. So what this means is that you can only trust your calculations if you finish everything much on a time scale much shorter than these two time scales T1 and T5. So what really is the solution? Well, one solution, of course, is you have to keep making the qubits better, and that has happened. In 1999, the first demonstration had a coherence time of about a few nanoseconds, and now we are talking about approaching milliseconds. So there's been significant process. But really, once you push the coherence time to a certain level, the real thrust here is going to be quantum error correction. And that's the idea that you can take multiple qubits which can individually decay, but collectively they somehow retain the information. And this really comes from the magic of entanglement. And that's a whole detailed topic, but this is going to be a very crucial step going forward to make quantum computers useful in the near term. And I think there was some allusion to this in the earlier talks, that there seems to be now a shift from trying to build larger and larger processes which are prone to errors to maybe building smaller processes which have less errors, because they will probably be more useful going forward. And quantum error correction, even though lots of proof of principle demonstrations have happened, it's not been achieved in the practical sense that we have not been able to make a qubit which survives truly longer and one can use it. And there's the added complexity that these so-called logical qubits, how to do gates between logical qubits. So in how to do gates in the error correction regime as well. So this is going to be a big challenge for all platforms, not just superconducting platforms. So now let's look into the different elements of what it takes to do an experiment or develop a technology using the superconducting things. So the first thing is about device fabrication. I'm not going to talk about device design, assume that that is something you have to do anyway. Device fabrication requires, electron beam lithography, because typically the feature sizes of the Josephson junctions are of the order of 100 nanometers or so. You need electron beam evaporation to deposit these metals in a very pristine environment, devoid of contamination. You need the ability to make Josephson junctions to oxidize in different angles. But then lately there's been a lot of focus on choice of materials, not for the junction itself, that's still mostly aluminum oxide, aluminum junctions, but for all the other stuff surrounding it, the microwave circuitry, new materials seems to be giving better decoherence. And this is all about controlling the loss coming from interfaces, from oxides, and this is still an ongoing area of research where progress has been made and coherence times are being improved. And apart from just qubits, you also need to make these other auxiliary devices like parametric amplifiers, which are very crucial for achieving the high fidelity measurement. Though there is some recent work happening around where people are improving the qubit cavity measurement system in such a way that you might be able to avoid using a parametric amplifier, that there is enough signal to noise ratio. So that will actually simplify the complexity of the circuitry as one goes forward, and would be a welcome improvement. Then it comes to the control, which actually is very straightforward to describe. You need to be able to create a signal, a microwave frequency pulse with varying amplitude and phase, which you can write down in this general form. And then you have to use a few different elements to do that. So you use a microwave generator to create your carrier wave, and there are many options available. You use an arbitrary waveform generator to create these modulating signals I of t and Q of t. And then you use a mixer to do this modulation, to multiply the signals together and create the pulse you require. And the same process is done in reverse for demodulation. That is when you're down converting the information read out from the qubits. A very similar setup takes place. So this is what needs to happen, and this is how people have been doing for now more than a decade. But some new possibilities have emerged in the recent past that you can use these new kinds of boards where you can digitally directly create. Now, of course, one can use very, very fast DACs to directly create signals at 5 gigahertz and 7 gigahertz, which is sort of the typical range for superconducting qubits. But usually DACs with fast sampling tend to be very expensive. But a new technology which has actually been pushed because of 5G, because now 5G phones use frequencies in this similar range, is the use of low sampling frequency DACs, but they use multi-Nyquist zone techniques to create higher frequencies directly. And this has really become popular in the last few years. There are lots of open source projects and even commercial products are now coming which use this technology, including in India. One company recently showed at a conference something which is based on something similar. QPI AI, which is a startup. And so this is now becoming, and we have also been trying out this in our lab, and I know a lot of my colleagues are, and this is turning out to be really a promising alternative, both in terms of cost and scalability, because a small board like this could probably control 16 qubits. The flip side, of course, is you need to know VHDL programming, but a lot of help is being provided through these open source projects, which you can use to get started with a lot of the templates already built in. So, a typical wiring diagram, don't try to look into the details. The idea is slightly to show you that there's a lot of control electronics complexity. You have to combine various signals together, send them to the device, and bring it back here at, this is a room temperature electronics, which can probably, this is probably representing something which can control about 3 qubits or so. And then you need ultra low noise cryogenic setup. So of course you start with a dilution refrigerator. which is shown here on the left. You need to have your microwave wiring all done properly. Many of these are now available commercially. You have to do microwave packaging and shielding because these qubits have to be protected from all kinds of noise. Some of the non-experts here might be surprised that even the 4 Kelvin stage is too hot because it's radiating photons at 4 Kelvin, and those photons can actually destroy superconductivity. So you have to protect your sample inside of, in various levels of shielding. You have to make custom filters which kill all these high frequency radiation coming from all over the place. So it really requires a lot of careful engineering to get the environment quiet enough to be able to observe and witness the quantum phenomena in its full glory. And again, you don't have to look at the details here. The idea was to show you the level of complexity even for just a 4-qubit experiment. Shown here, each line is capable of measuring a qubit followed by a parametric amplifier. So you have lots of attenuators and filters and circulators and so on and so forth. So if you look into one of these things, you can see there's a bunch of attenuators which you have to do to suppress the room temperature noise from reaching the device. You need various circulators to isolate the noise coming from the output line and also to divert the signals in the right direction. You have your parametric amplifier, which then acts like your first stage amplifier, and then you go up and you have your cryogenic hemp amplifiers and many more amplification stages at room temperature. So there are lots of these things, and attenuators, reflective filters, lossy filters, which one has to either procure or make and then install and then thermalize everything properly at low temperatures. So there's a lot of different kinds of expertise which goes into building these systems. And then, of course, ultimately, once everything is put together, one can draw some algorithm. This is, of course, just a dummy algorithm with random blocks here. But the idea is that at the end of the day, if you just look at what happens when an algorithm runs on a quantum computer in superconducting architecture, and maybe in many others as well, is just a bunch of microwave pulses being fired at the device and a bunch of microwave pulses coming back, and you analyze it. So that's essentially what happens. So you have each gate is a microwave pulse with a specific characteristic, and you have to calibrate it to make sure that it is performing the operation you are doing. And this calibration has to be repeated periodically. And I think this was alluded to in the last talk as well, that this is something one has to keep doing it, and maybe one could use machine learning techniques to do that as well. Now, when you're doing experiments at the level of a few qubits, you don't need any specialized stat software to do that. You can just, your student can write your code for that. But in general, as you now scale up, you need some software at a higher level for entering your algorithms, and then some compiler which will translate to the relevant gate set. That's basically the elementary operations which are available for your specific hardware. And then translating those gates into the specific calibrated pulse sequence which needs to run, which needs to be sent to the device and then measured as well. So this is sort of what goes on in doing one of these experiments. And then when it comes to scaling up, here I've shown you a bunch of images. It's a 9-qubit chip from back in the day from UCSB and Google, a 16-qubit IBM chip, and then of course the Google's Bristlecone, and then this is IBM Washington 128-qubit chip layout. I think what I would say is that the basic building block in terms of the qubit and the other parts is fairly well understood, but it's not perfect yet, in the sense that there's room for improvement to push the coherence times and make them more robust over time as well. Like, sometimes these qubits stop working after a few days or a few months, and it's not always understood why. In order to scale, to make chips with larger number of qubits and to set up, you need resources. You need sophisticated fabrication facilities, you need lots of new electronics and engineering, and various problems to make these more robust, make the electronics scalable, and also some focus on the interconnectivity architecture. Currently, these qubits are all loosely coupled. It's difficult to make gates between distant qubits, even though you can go through the intermediate qubits to do that, but that increases the overhead and the number of operations and consequently the number of errors. And ultimately, of course, quantum error correction. And there are lots of different approaches being tried out, the surface code being one of the most popular ones that is being implemented in the superconducting architecture. And there is a whole parallel approach which I have not mentioned, which are these bosonic qubits, which actually use high Q cavities to encode the state of qubits. And that is also looking very promising, because in some sense in that architecture, error correction is very natural to the whole system, as opposed to having to do it in a slightly more artificial way in the conventional systems. Okay. Now, moving a little bit to what's happening in India, in academia, there are 3 faculty members spread across 2 institutes. I'm, of course, we started the first lab in 2012. I'm in a TI from Mumbai and been working on various kinds of new qubit designs and improving measurement techniques and things like that. Professor Vibhor Singh at IISc Bangalore, he's been there since 2015. He also comes from a background of superconducting devices and who also worked on optomechanical systems combining nanomechanical resonators as well. And the most recent, Dr. Baladitya Suri, who's actually there in Pune. He's been in IISc Bangalore since April 28. He has done some prior work on quantum acoustics, and he's now setting up his lab and has been doing experiments using lumped element resonators and others in the last few years. There's also DRDO Young Scientists Laboratory in Quantum Technologies, with whom I have been actively collaborating, which was recently set up under the Young Scientist scheme of DRDO, where several labs were introduced, and quantum technologies was one of them. And there's a new lab coming up in a private university in Kolkata called C-Quare TCG Quest. This is hopefully will get operational in later this year. But there are some new hires also being considered. There's at least one more person we know is going to join us soon. And some startups have also started emerging, though the numbers are still pretty small. This is actually probably the most ambitious quantum computing project happening in India. It's very modest, but it's still ambitious. It's a 7-qubit quantum computer project. It's really a technology demonstration project where we actually finally sit together and put everything and to see how it works. It uses a very non-traditional approach. We're using the 3D architecture to help with modularity and ease of fabrication, because our fabrication tools right now are not really there to make qubit chips reliably. So this was sort of an approach we took, and we are working together with the Young Scientist Laboratory of DRDO and also Tata Consultancy Services, which will help us put this system on the cloud. We all know 7 qubits don't really do much, but unless you build something first, you will not know what mistakes not to make as you try to scale beyond. And there is a parallel electronics development also using these FPGA modules, which I mentioned earlier. Okay, so in the last maybe 5 to 7 minutes, I just sort of wanted to talk about different aspects and put it in perspective in what's happening in India and what we maybe need to do. In terms of device fabrication, there are lots of clean rooms around the country. Most of them are fairly small, but there are a few big ones. But we still don't have like the most sophisticated e-beam tools, and I think the national mission which is coming up, which help us allow to do that. Again, there are a few people who have worked in the superconducting qubit area who understand the requirements for this, but there's a lot of work that needs to be done to understand materials and improve the coherence. Many of these things are actually secrets which labs developed, and unless you try it yourself, it's very difficult to reproduce it for ourselves. You can't just do it by looking at a paper. So there's a lot of work that needs to be done to improve the quality of our devices to be able to make large-scale chips reliably if you want to scale things up in the coming 5 to 7 years. Now, control electronics, so far everybody has been using commercial off-the-shelf systems, but there is actually a lot of control electronics development, especially FPGA-based systems expertise in India, in various government labs and even in industry. And I think this is an area where one could probably make a significant impact globally as well because of the prior availability of trained manpower. And that's why I put this point here, commercial versus indigenous. I know a lot of commercial providers are there, and I have spoken to some of them recently one-on-one, and I mentioned this aspect that going forward, there's also a lot of focus and emphasis in India to do things indigenously and not just buy things and put things together. This is actually an area where I think we can make an impact if we really invest and bring together the right set of people together. Even in cryogenic circuitry, you need specialized filters and attenuators, and many of these things can actually be made here. Currently we don't have the industry or companies which are providing these kind of tools to us and manufacture in India. So even though one can procure them relatively easily, it's actually slow and painful to do the importing as well. So here's some scope to do that as well. These are things which can all be addressed in this grand mission, where we make an effort to develop some of these things so that in the near future we can do the turnaround much faster and have a local source for many of these things. And then finally, software and algorithms. I think in the previous talk, there was this mention that the pace at which algorithm development was expected has not really happened, and that's even though it's surprising, it's not so much, because developing quantum algorithms is really challenging. It requires a very different kind of an intuition to do that, and I think there's not much of that going on in the Indian context right now. We need many more people who are not directly connected with the quantum computing ecosystem yet need to come in and contribute to this area as well. And we have the tools here. It's just people have to start working on that. So to summarize here, the core expertise, and I define this as people with prior training in superconducting qubits, who have gone to a superconducting lab elsewhere and trained, is very small, it's limited. So it's actually critical to attract experts from allied areas, your colleagues who have the technical know-how for the kind of experiments that are required. We need to find out a way to attract them to come and join the team, because we will not be able to hire such a large number of people with prior training, because many of them are, of course, taken up by a lot of companies and universities internationally. So this is going to be challenging. And this whole array of classical engineering that needs to be done to get quantum computers to work. And we do have the people here, they're just not working in quantum computing right now. So we have to tell them, first of all, that they don't need to know quantum mechanics to do this, and then bring them in and explain the problem to them and get them to contribute. So there's chip design, microwave engineering, high-speed electronics, process control for fabrication, computer scientists to come in and think about algorithms, and theorists, physicists who are thinking about device theory, coming up with new ways of making qubits. We would really need to push this in a big way if we want to start making a significant impact. So to sort of end, there are some administrative and logistical challenges in India as well as we embark on this mission. As I already mentioned, the expertise is sort of small and concentrated in academia. As of now, there's very little industry participation. It also affects the kind of projects one can take. Now, since we are kind of playing catch up, often many of these projects are just repeating things and learning it for yourself. They don't often lead to new papers or thesis. So it becomes a little bit tricky to do this in academia, and you have to find the right kind of people to do this. We're going to need a lot of new state-of-the-art infrastructure. There's going to be money for it, but we have to set it up very rapidly, because it takes time to procure these things and set it up and get it going. So this has to be done very efficiently and quickly, and we have to also train large number of people to work on these massive projects. And now, when the national mission is not just about superconducting quantum computer, it's the full gamut of quantum technologies, from communication, computing, sensors, and materials. So we have to find a way to do this efficiently, where the training and the work is happening in parallel. This is kind of a strange thing, but I thought I would mention is that because the community is small, there is sort of a problem between who's going to do the research and who's going to do the administration. And it's because somehow it comes to the same set of people who have to do both, and it's actually getting quite challenging for the relatively small community here at. So this is also going to be, I think, an interesting challenge to overcome as we set up this mission. And there are some, other challenges which some of them are unique to India, but the pandemic after effects are still there, even though we are now more or less out of it in India and things are moving. But the global supply chain issue is still a problem. Products cannot be bought so easily and so quickly, so things are taking much longer. So when we embark on this big mission, we have to factor that in. And more recently, we have had to deal with some new restrictions on importing goods. The thought is very noble that, we want to become self-reliant, but this cannot happen overnight. We want to develop indigenous quantum technology, but for that we need lots of tools, and we cannot build those tools. That's a whole other mission. We cannot start manufacturing dilution refrigerators now and to say that we would build the quantum computer once we have our own dilution refrigerator. I mean, I'm giving an exaggerated example here, but we need to find a way to work around these restrictions and make it easy to need the to get the tools we need in order to make quantum technology happen in India. So to summarize, superconducting electrical circuits as qubits is a very promising architecture. It's a scalable technology and has achieved major milestones already around the world. There's a lot of activity happening in this area in India as well, at TIFR Mumbai, where I am, at IISc Bangalore, the DRDO lab as well. And we have received funding from various agencies, DST, MeitY, DRDO, and DAE. And there's this big $1 billion mission expected to be launched soon, which is the National Mission on Quantum Technology and Application. And even though there are these administrative and logistical challenges which we have to overcome, this is really an unparalleled and unique opportunity for India in particular, of course, for the world as well. But given the scale of the problem, I think Andrew Briggs had commented that for the size of the country, this program seems very small. But compared to other programs, this program is still very ambitious and big. So I think in that sense, this is really a fantastic opportunity. We have to be very clever and careful about how we plan this and execute this. But I think it's going to be a lot of fun and a lot of hard work. So on that note, I'll end and I'll take any questions. Thank you.
Thank you so much, sir. I now request Mr. Matthijs Rijlastam, Quantware, Netherlands, for the expert talk.
Questions? Questions. So
I request if anyone has questions to ask.
Colonel Nath wants to take.
Yes.
Yes,
please.
there is one question. I think Gyan has one question from C-DAC Patta. Come.
Hello, sir. Would you please discuss the advantages of and limitations of transmon qubits in terms of coherence, stability, and readout?
Okay. Well, I mean, this is not a very quick answer to give. The transmon qubits actually were not the first qubits to be developed, but they turned out to be a good compromise, around mid-2000, where the coherence was easy and the size of the junctions were not too small that you could make them reliably. Back in the day when I was doing my PhD, you would make, some 10 samples and maybe one of them will fall in the right range and you'll do your experiment and you quickly move on. But, to make a processor, you need that process to be a lot more reliable. So transmon qubits in that sense have been quite good, but they do suffer from the fact that, they have this weak unharmonicity. It's not really a true two-level system. There are other levels close by. I mean, there is always other levels, but they are too close by in transmon. And even though it's sufficiently far enough to do fast enough single qubit gates, they always play an indirect role. For example, when you're doing measurements, when you're talking about leftover coupling, this so-called Krosker error and ZZ errors. So there are some disadvantages there. Currently, the only other alternative which is out there seems like the fluxonium qubit, but that has its own specific challenges. It requires a magnetic flux as well. It has many more junctions, but at least at the level of a few, 1 or 2 qubits, it has looked quite promising. And even we are looking at fluxonium as a possible alternative. The issue would really be is that if at some point we are not able to increase the coherence time of the transmon qubits. But unpublished reports say that those numbers are already approaching half a microsecond to a microsecond, millisecond in some experiments. So I don't see any fundamental reason for that, and the readout fidelity is also high. We just have to keep innovating. But I think there is scope for a completely new qubit system to come in as well.
Thank you, sir.
I'll take it.
Yes, sir. Hello, sir. So, I have one question with respect to the cooling system. Actually, what will be the best feasible cooling system, which can be implemented in case of quantum computer? As we know, we have a Doppler cooling, we have a freezing at the mid-air kind of thing, we have laser cooling also, just to know which will be the best to actually take up if possible.
Right. So, see, for superconducting qubits, there is only one option right now, which is the dilution refrigerant. The other techniques you're mentioning are mostly applied for ions and atoms, where you have, where you're really talking about the temperature of a small cloud of atoms or ions. Here, we need bulk cooling, and currently, dilution and maybe adiabatic demagnetization is together with dilution is the only technology which is available. And that's why, they are trying to build larger and larger dilution refrigerators. I think the previous talk, Andrew Briggs also commented on that. And, I've seen some of these prototypes. They are massive. You can literally walk into them. And I think there's nothing fundamental which prevents you from making those things bigger. And often, this question often gets asked that, you need such complicated cooling systems for superconducting qubits. Is this really a technology which is going to survive in the future? And I think the answer is that that's not really the main stumbling block. I never imagine, at least in any time in the near future, and I don't think we need it to have quantum computers in your pocket. And I like to give the example of your voice recognition systems like Alexa and Google Home and Siri, where the unit in your home is very small and it has a very basic functionality. It's just transmitting information back and forth. But the real power lies in the supercomputer, which is sitting somewhere in a data center. So I see that quantum computers will be mostly of that form, and you will be able to access the power they have to provide from anywhere in the world using the ability of fast communication over the internet.
Good afternoon, sir. This is Jitesh. Thank you very much for your wonderful talk. Sir, I have a question on your second last slide where you are trying to discuss about the administrative and policies issue. So I just want to understand, sir, what is the ROI of investing on quantum computing, and especially in the perspective of India? Just to elaborate, like whatever the amount we are going to invest on the quantum computing, which is so much sophistication involves, and the same amount if I invest into the existing technologies. So where we see where the technology reaches in the quantum and what will be our ROI, and if the same amount if I invest into the existing thing, where I will reach. Just a quick comment, sir. Thank you very much.
Okay, I mean, I'm not really the expert to say things about ROI here specifically, but if one is talking about the kind of things a quantum computer can do, assuming we build one in the future, there is no other alternative as of now. So it's not that you can invest in some other area and ultimately reach the same place where quantum computers would allow you to reach. At least we don't know till now. So in that sense, if you don't do it, then you just never get there. Of course, we will be able to procure some of these technologies developed elsewhere, but we have been trying to there was a comment about being technology creators and not just technology consumers. So it's always a tricky question, and especially in the context of India, where one should invest. But this is an opportunity where we are not starting too late, and I think we should be able to play a significant role going forward. So I think whether the program is successful or not, and this is not just a 5-year story. This is going to go on for the next several decades. This is just the first step we are taking. So I think it's very important and crucial that we do and take an ambitious step like this now. It will also set a sort of a template for future projects of this scale, and when to get in and how to get in. And so I think in that sense, it's very important to do it.
I am from TCS Mumbai in the Quantum Computing Incubation Unit. So I had one question, like you mentioned a couple of devices that you are designing with 7 qubits. So one thing is that are we also looking into back calculating the quantum resources that will be required, or the quality of resources for some specific, let's say, problem dependent algorithm? Let's say you have for a given set of algorithms, because the variation algorithms are very prone to noise and also are difficult to implement. On the other hand, fault-tolerant algorithms cannot be implemented with just for any usable system for small number of qubits. So is there also we are also looking into the number of qubits and the gate requirements for some specific problems, if we can back calculate that and use that to understand what kind of hardware we need to design for them. So are we looking into?
So, I mean, this first 7-qubit project is, it's really, as I said, it's a technology demonstration project for us to get our hands dirty and do everything that is need to be done to put together a full system. This is, what's called the gate-based architecture. It's not being designed for a particular problem. Any 7-qubit algorithm, you'll be able to run it with the quality it will offer depending on the gate fidelities we are able to get. But in the future, it might be possible, and maybe there might be an advantage of building very specialized systems. Usually, sometimes these are also called as quantum simulators, where you build a hardware which is dedicated for doing one particular type of problem, as opposed to a general purpose computer. I mean, people have done these kind of estimates around the world. We have specifically not looked into other such special purpose architecture in our own group, but this will definitely be part of some project, in the national mission. We will have to look into these specialized cases and see if some innovation can be done there.
Thank you.
Hello, sir. Thanks for covering a lot of vast amount of topics in such a short duration. And I had a two-part question. So first one was about quantum error correction. So can you briefly explain what is the current procedure you follow at TIFR to do this? And the second part was, as you know, you spoke about a lot of skill sets required in this kind of quantum technology. You spoke about microwave knowledge, and there is design knowledge, and there is fabrication, the material science knowledge. So coming from a amateur or a very enthusiast. So what is the barrier of entry to such fields? So, and considering it is considered a very complex topic, so if you have a part of that skill set, how do you enter and get scaled up in the other skill sets? Is it possible to do it?
Okay, let me see if I can answer. The first part is very easy. We are not doing any error correction so far in our lab in TIFR. So what we are trying to do, we are not following the surface code, but one of the projects we are trying to do is to create a highly connected network. So a network of qubits where most qubits are connected to other qubits in the network. And we think that might allow us to make some kind of a module where you can do error correction. We don't have very clear methods yet, but that's sort of what this is slightly into the future. For the second part of your question, you see, if you join a quantum computing lab for your PhD, like I did, back in 2001, you learn all of these different things. That's at the level needed to carry out those things. So, in terms of standardization of the training of these things, now there are programs, and even in India, IISc has started a master's program in quantum technologies in general. So there you can hope to get some knowledge of all these things. But what I was trying to say there in my slides is not about one person necessarily learning everything. As a PhD student, you have to do that in order to achieve. But even there, depending on the kind of projects you're working on, some other student might make the device. For example, during my PhD, I hardly made a device. I designed the device, I carried out simulations, but somebody else was doing the fabrication for me. I learned fabrication during my PhD, but I applied it during my postdoc. But what I was trying to say is that there is a lot of existing expertise in all these allied areas, microwave engineers who probably know way more than people like me who have done a little bit of microwave engineering. We have to explain to them the challenges which are connected to building a superconducting quantum processor and get those people involved into them and give them the relevant training for them to understand the basics. Same to do with control electronics. If you explain what needs to be done, then they can deliver for you.
Thank you, Professor Vijayan. I'm Colonel Nath, Executive Director, C-DAC Pune. My personal thanks to you for coming online and giving us a very, very informative thought. And your talk was just tailor-made for the objectives of this symposium. And we have circulated a questionnaire, very pertinent questions you brought out regarding, R&D versus administration and the whole mechanism. That's what exactly we are trying to put in place here with the help of this symposium. So I would greatly appreciate if you attend the valedictory tomorrow if you have time, or just give us the answers, your opinions on those questions which we have circulated. If you've not got them, I'll ask Anindita to circulate them to you.
Yeah, sure. I'll try to attend tomorrow and send you the answers.
Thank you so much. Thank you.
Thank you. Thank you for having me.
Thank you, sir.
Thanks.
Now I request Mr. Mati. Yeah, sir. Thank you. Now I request Mr. MeitY Srijlastam, Quantware, Netherlands, for the expert talk.
See if this works. Right. Thank you very much for having me here. It's a great honor to be here today. I'd like to give a short overview of what our company does. And I'd like to give a short overview of our business model, which is the open architecture model. So my name is MeitY Srijlastam. I'm co-founder and CEO of a company called Quantware. We are a Dutch quantum hardware company. And we make superconducting quantum processors, and we sell those. So maybe starting with the idea behind our company. When you look at the superconducting quantum market today, and you look at the stack on the left over there, there's a bunch of components, and for each of these components there exists what is basically a quite mature supply chain, right? If you want to get, control hardware, there are probably, about 4 or 5 providers. If you want to get a dilution refrigerator, there are quite a few. And that's great. That's good for innovation because it makes it, much easier, much quicker to get going with building quantum computers. Except for that, the heart of a quantum computer, the quantum processor, is missing from this supply chain. That's only available to very large vertically integrated players, such as usual suspects, Google, Rigetti, IQM, IBM. And while they do great work that really advances the field, it really limits, the amount of people that can work on quantum computers because it's slow, it's expensive, it's unreproducible. And maybe today, if you get, for instance, an E-beam and you get going, you can still get, to a 5-qubit level, and you can get somewhere. But as the devices scale and become more complex, this moat around building quantum processors will only get bigger, and so this problem will get bigger. And so that's the reason our company was founded. That's about 2 years ago. So we are, at least as far as we know, the world's first supplier of superconducting quantum hardware. And we were able to do that at a price point that is about an order of magnitude lower than competing solutions. And I'll explain why that is. In short, we do that we pride ourselves on short lead times. It's about 30 days, depending on how much you want to customize of our chips. We do that, of course, with excellent specs and customizability. We're spin out from the TU Delft, so we have a really strong technology base. And again, we're quite affordable. This allows our customers to basically get going. If they have a fridge, they can basically get going with building a quantum computer in about 30 days. And so that means that we lower the cost of building quantum computers by orders of magnitude, because you don't need to build your own foundry first. It also allows our customers to reproduce setups. So if they read a paper done on a particular Quantware processor, they can buy that same processor and build that same setup. And this is more relevant for our more commercial customers. It really reduces setup downtime, right? A dilution refrigerator is quite expensive, a few thousand euros a week on depreciation alone. So if you need to wait 3 months for your device and you can also wait a couple of weeks, that makes a big difference. maybe some more background. So we are what's called an integrated device manufacturer, which means we do both design and fabrication in-house. And what that usually looks like is a customer comes to us with a certain application. That can be an actual algorithm to, I want to build a technology demonstrator, or something else they want to do. And from that we derive design parameters. So we try to translate that into qubit frequencies, for instance. And this then feeds into what we've internally developed, which is a completely automated layout generation software platform built on top of Qiskit Metal, which allows us to then automatically generate an optimized layout. And that the input for that layout is our library of chip components. So that that features transmon qubits, obviously, but also things like Purcell filters, tunable couplers, asymmetric junctions, and that is constantly expanding and improving. And so then from these design parameters, we generate a fully optimized chip design in about a day. So it's extremely short. And this then goes to our fabrication facilities. And because we are constantly fabricating, this whole pipeline takes about 30 days. I mean, of course, if you want something really exotic, it will take us a bit longer. But it really extremely amplifies the amount of R&D throughput people can do. And so I just want to emphasize, this is not some pitch deck we made for investors to then raise money and then go actually do it. This is a reality today. So we're selling currently parametric amplifiers, was just talked about. They are important for readout. We launched with a 5-qubit Soprano QPU. Last March, we released the 25-qubit QPU Contralto, of which I actually have one here, and there are a few more sprinkled around the exhibition lounge over there. And so all of these are fully customizable, and they're quite affordable. So maybe for reference, a 25-qubit QPU, our Contralto QPU is about 300 €. We also recently launched foundry services. So we see that there is a segment of customers that wants to actually develop their own design expertise, but doesn't have their own fabrication expertise. And so for that, they can send us their design, which we then fabricate. And our view on this is that later we can then add things on top that are in our design library, right? So you can get to really scalable mixed IP processors. And I'll get to that a little bit further. So the reason that we can do this is that we are a TU Delft spinout. And so these are just some highlights of the things that were achieved on QPUs made by our team when they were still at the TU Delft. In particular, we're a spinout of the DiCarlo lab. They've done various NISQ-era demonstrations, error correction milestones, some pretty big ones, record 2-qubit gates, first quantum computer in the cloud in Europe, et cetera, et cetera, et cetera. And by now we have QPUs in about 4 different continents, so we expect that there will be future exciting publications. Of course, it takes a little bit longer than the 1.5 years that we've been shipping chips, but we will get there. We do this with a team from people from excellent places like Q-Tech and Microsoft. We're supported by, I think, some big names in the industry as well. So our first angel investor and our scientific advisor is Professor Ramer Barens, one of the authors of the Google Quantum Supremacy paper, as well as Professor Charlie Marcus, who's a former director of Microsoft Quantum. So maybe to get a little bit into why we chose this particular business model, where we don't build a black box full stack quantum computer, because you can sell those for, let's say, 30 million or so, and we only charge 300K for our chips. And it gets a lot to what Professor Briggs talked about as well. Maybe first, we believe that this is the winning business model in our industry. And that is because specialization will occur in quantum, as it has in the semiconductor business. So what you see here on the left is a graph that basically shows a little bit of history on the semicon business, where for the first 20 years or so from the 1950s to the 1970s, everyone was vertically integrated. And that was because the barrier of entry was still quite low. You could build your own fab and then build your own processors. And then in the 1970s, Intel was founded that only did fabrication. And 10 years later, everyone used Intel. And now actually Intel is a little bit in trouble because TSMC has specialized further, and so their business model has become more efficient. And the reason that this happens is that as the devices scale in complexity, the capital requirements to build a foundry increase exponentially. And on top of that, chip making is a fixed cost business. You need to spend a lot of money on very expensive machines, and then whether you build one chip with those machines or 100, that doesn't really matter. The marginal costs are negligible. And that means that if you can sell 100 chips versus, and your competitor can sell only one, you can be approximately 100 times cheaper. And so this scale advantage is here today. As far as we know, and this is not entirely public information, of course, we're now 1.5 years on the market, and we think we sold about an order of magnitude more than our closest competitor in Europe. And so therefore we can be this affordable. And then the second part for us is that this open architecture approach develops local ecosystems. So on the left there is a very early stage example of something we did when we were still about 4 people in a tiny room. But we built an 8-qubit quantum computer in about 3 months with various partners in the ecosystem. So that's a Dutch ecosystem. And now there will be some very exciting developments in the Dutch ecosystem coming up later. But later we, together with our great partners from Quantum Machines that are also here somewhere in the room, I think, we're going to supply chips to build a quantum computer in Israel. And so there you see that we can partner up with an excellent partner in the local ecosystem to really build expertise there and enable that ecosystem to build technology on top of our platform. Of course, Quantrolox we partner with, and there are various others that are currently not public yet, but what you'll see hopefully in the next couple of months is a few announcements with various local projects where we partner up with local partners that can then build state-of-the-art setups. So maybe I'd like to round off with a little view of what is next, because if you start thinking about these open architecture approaches and these parallels to the semicon industry, a whole field opens up, and I'd like to elaborate a little bit on that. So first, I mean, the previous speakers talked about this as well. We think, obviously, that superconducting is a front leader to be one of the leading technologies later, but it does need to scale. So when you look at, when you map, gate speeds versus operations per second, it's pretty clear that trapped ions and superconducting qubits have the most operations before an error. And superconducting qubits are very fast, but they need to get less errors, and trapped ions need to get faster. We're pretty optimistic about that because coherence times have been increasing exponentially for the last few decades, and we expect that will continue to happen. But what is really missing here is scaling the number of qubits in superconducting qubits, and that has to do with connectivity, that has to do with the fabrication challenges that are there. And so this is something that we as a company uniquely solve, because it's great to sell 25 qubit chips, but if we want our customers to truly be competitive, they need to get to the level that the big American players are at. And so that is what we are working on. So our platform is very scalable. It's a little bit blurred still. I can't really announce what we're making yet, but it will be announced pretty soon. And so our customers are able, over the long term, to be competitive and upgrade actually quite aggressively. And what we think that this will enable is, as these devices get bigger, when there's a 25 qubit GPU, there isn't a lot of design to happen, right? You could probably still do that by hand, but as these will get bigger, what you'll see is that on the qubit plane, there might be qubits designed by party A and let's say Purcell filters designed by party B, fabricated by party C. And so this is really what we're aiming for with this new platform. And that will also allow, these, for instance, these players that were mentioned in the previous talk that develop more error resilient qubits to scale, because they don't focus on the scalability, but we can put their qubits on our qubit plane and scale them to very large counts. And then on the other side of our platform, we connect to various excellent upstack providers Some examples there are Qblocks, Delft Circuits, and CQC. There are many others, also some that aren't public yet. And so we also allow these parties that don't have an interface to, for instance, the optical transduction of Qblocks yet, to immediately, add that to their technology as well. And so we think that this is the next big paradigm in quantum over the next couple of years, that you'll start seeing these mixed IP processors popping up. And that's another, flywheel effect of this open quantum approach, because the people that don't focus on developing the whole thing, but focus on making one thing the best, will be better than the rest. That's the point I just made, but written out, so I'll skip this slide. Well, maybe actually one interesting point about this slide is, so what we believe is that this will lead to new business models as well for our clients. So you could imagine fabless quantum companies, which currently don't really exist because you can't really send a chip design somewhere. Smaller vertically integrated players, or maybe even like the Dells of quantum that build quantum computers but don't design their own and fabricate their own chips. Or NISQ algorithm developers that want to create application-specific hardware, and because they can iterate extremely quickly at low cost, they're able to gain competitive advantage there. And so this push to specialization will lead to higher R&D efficiency and will create a resilient quantum ecosystem. And with that, I'm happy to take any questions.
Hello. Yeah, thank you, Mathies, for this interesting talk. This is becoming more and more interesting now. But for the interest of time, I think Colonel Nat will take one question, but then I think we need to move on to the panel discussion.
Yeah, Mathies, thank you. Very quick question from my side. It's good, we can get prefabricated quantum processors from you, but what happens when you start integrating them with the dilution refrigerators and the control and measurement electronics? What do you do for taking care of the error correction and things like that? And how do you help customers in integration part of it? Mike.
Yeah, thanks. That's an excellent question. So we usually help with the whole, layout and the integration of the cold part of the fridge. So that we provide sample wiring layouts. We can also provide the shielding, the amplifiers, of course. And of course, the layout is made in conjunction with the customer. And if they don't have that expertise, then our standard layout has fully controllable qubits, so dedicated flux and dedicated drive lines, which are very suitable for surface codes. Again, coming from our heritage from the DiCarlo lab that did, the first proper surface code demonstrations.
What about the, on-site integration expertise?
Yeah, so we
so system integrator kind of a part, do you play that role also?
So we often send over engineers to actually place the equipment in the fridge, and then when you talk about system integration, as in tuning up the system and maintaining that, that's usually a partner of ours, and there are various examples there.
So that can be a part of the deal.
Absolutely, okay. Yeah.
Thank you.
Yeah, thank you. So we'll move on to the panel discussion, and I'll request you to take the seat. And after the discussion, we'll have questions for you. Then we'll get it diverted to you.
All right.
Thank you. So can we have a round of applause, please? Thanks.
Thank you so much, sir. Now I request Colonel Ekinat to felicitate Mr. Mataish.
So good afternoon, everybody. We are running behind about 40 minutes from the schedule. due to the lot of interest that the audience have in the technical talks that we had. So in the interest of time, currently the panel discussion is scheduled about 1 hour 10 minutes. We'll try to keep it for 45 minutes so that the lunch, we can break for lunch about 2:15. So in this regard, I request Dr. Baladitya Suri, IISc Bangalore, to please come on to the dais and occupy your seat. And also Dr. C.M. Chandrasekhar from IISc Bangalore, please. And then we have Dr. Professor Gopalan Raghavan, Director, SQT Diet, Pune. Please come on to the dais, please. Professor B.K. Das, IIT Madras. Sir, please come on to the dais. Dr. Anuj Bhatnakar, Samir, Mumbai. Please come on to the dais, please. Dr. Ranjit Avaldar, CMET, Pune. Please come on to the dais, please. Mr. Sujay Chakravarti, Quanfluence, please come on to the dais, please. And we have Dr. Joey Ghosh from IIT Delhi virtually presenting as part of this panel discussion.
Yeah, Mr. Hari Babu is being a rather strict session chair.
Yes.
I would like to tell you that, I cannot promise you a very elaborate lunch, so you can, increase the session time a little bit.
Okay.
I can assure you that lunch will keep you sufficiently satiated, but sufficiently hungry for the,
yes,
next knowledge sessions which are ensuing.
Yes,
so yeah, I think you can give them a little more time, yeah.
Yes, yes. So this is a quite interesting topic that we are going to discuss as part of this panel discussion. And the topic that we have selected is basically on looking at the advantages and also the differences between superconducting qubits and also the photonic qubits. And the discussion could be on which technology is going to take forefront in the future, or which technology is actually more suitable with respect to the environment that is being operated. And I request each panelist to take about 6 to 7 minutes to explain, and also after all the panelists completed their talk, we'll go for a question and answer sessions. And we start with Professor Baladitya, please.
Hello everyone. Firstly, thank you C-DAC Pune for inviting us all here. Can you all hear me? Okay. I don't know if people on that side can. Maybe I'll just stand up. That's better. So as the topic of this suggests, we are discussing superconducting and photonic processors. But at the very outset, let me give you the rather, not bad news, but the sort of overall picture is that we don't know what the end game is. So we need to actually invest in all the various directions that people have been pursuing across the world. But of course, superconducting circuits and photonic devices have progressed rapidly over the last few years. So I will talk about superconducting circuits from my experience. And when Anindita invited me, I told her that I won't be making any presentation because I was sure that Vijay would be presenting all the necessary information. So, and thank you Vijay for doing that. So I can just rely on the slides that he presented and reiterate a few points just for your benefit. And of course, I'll be very happy to answer questions later. So superconducting circuits is a very aggressively pursued technology across the world, and it is currently the leader in terms of the number of qubits. And we have fundamental, you can say, there has been a lot of progress in the coherence of these qubits, starting from about 4 nanoseconds about 22 years back. And now we are about 400 microseconds, which is about a millisecond. So we have come 1 million times in terms of coherence. So this allows for better and better implementation of quantum computing algorithms on these systems. And people have not attempted error correction, which is of course the holy grail of quantum computation. But this is the one platform which in principle ushered in the NISQ era, because it made the NISQ era viable in some sense. And so this is the global setting in which we are living currently. I don't want to go into the technical details of how these qubits are made and all that, but in the Indian context, I'll give you a very quick repeat of what Vijay said. We are 3 groups, 3 PIs, and a sum total of 20 people, roughly, give or take 1 or 2, working in the country. All of us doing superconducting circuits, 2 labs in IISc and 1 lab in TIFR. And we are pursuing both the 3D architectures, like Vijay showed, and the groups at IISc are doing the planar architectures primarily. And the goal is, and we are all part of, projects together. For example, the project by Quest is, we are all in it together. And IISc has the project by MeitY, where we are building a 4-qubit processor to, deliver probably at the end of this summer. So this is the state of the art. We are anywhere between 2 and 7 qubits, depending on which lab you look at currently, and promising a deliverable of about 4 qubits at the end of this summer. So that's the current state of the art for this architecture in India. And the challenges that we are, so I have been asked to also talk about what's the current state of the art and what are the challenges going forward. It's quite straightforward. The challenges are in the infrastructure. So we have issues with the basic infrastructure, both on the research side as well as on the policy side. So we need to address both these going forward. As Vijay pointed out, if you look at the policy side, we need to have, if we are going into a mission mode sooner than later, we need to have policies which help people accelerate their research, and that needs to be looked at. And one of the things is about imports. We currently import a lot of technology from abroad. We do not have the in-house indigenous capabilities right now, so that needs to be addressed. And we also need, on the manpower side, to come up with policies which incentivize people to come to India and work. And that is where I want to emphasize that we run, if we want to accelerate this, we cannot run just with PhD students. While as academic institutes, we have the mandate to train PhD students, what is happening right now is we train PhD students, but we don't have the ecosystem to support them as postdocs, so they end up going abroad. And then we hire new PhD students, and it's like 2 steps forward, 1 step back. So this is not going to be a sustainable approach. So we need to have people come in as postdocs or at the level of research scientists. Postdocs require publications, and Vijay also brought this point, which I want to emphasize, that you cannot have a system where postdocs come in but then can't publish, and then they are evaluated on the same metrics as all other academic institutions. So this mission, if it wants to run at full speed, we need to have a mechanism to incentivize people to come back and rework this whole postdoc publication model so that we don't penalize people for building technology ground up. So these are some of the points I wanted to make. I'll hand over in the interest of time to my colleagues here.
Okay, so good afternoon. I think there's been a lot of talk on different hardwares. I would like to make a small presentation on photonic. It would be like 3-4 minutes because that's something important platform we have to look into. Yeah. Can I have my slides? No, this is not the. Okay. Oh. No, not this one. There is a presentation So I currently work on photonic platforms. So I use single photons to build qubits and then do some operations, control operations. And a priori, I'd also worked on cold atoms at Oxford initially, and then I worked in collaboration with ion traps. So we have implemented some of our algorithms in different platforms. I have some, ways or like a comparison between the hardwares which exist. And I think what Vijay pointed out in one of his slides is that it's not just the hardwares or it's not just about engineering problems. Scientifically also we have to come out with new ways of building qubits or thinking of new ways of building qubits and integrating. And over last few years we had looked at different ways of building qubit itself. And then we did have a proposal of new way of building qubit and doing operations. And that's what we are trying to convert it into a photonic system and building qubits at IAC. If my slides are out, I think probably I can. Yeah, sure. Yeah. So, in fact, this is a new lab at IAC. It's just been 2 years, but a priori that I was at the Institute of Mathematical Sciences. We are building algorithms and then trying to come up with new schemes for quantum computation. And next slides, please. Yeah. So, I think, yeah, next slide. Okay. So there are a lot of advantages with photonics, and again, I'll also touch on disadvantages. So they work at room temperature, and this is the only system which currently works at room temperature. You take cold atoms, or you take ions or superconducting, they do have to be operated at a very low temperature, and they are more robust about external environment, from external environment. Photons don't interact easily. So you can actually control them for long, I mean, in fact, an external environment don't affect them. And then photons have multiple internal degrees of freedom. I can think of polarization, or I can think of time-bend degree of freedom, or I can think of part degrees of freedom. So in fact, there has been experimental demonstrations where people have just used 6 photons and then shown 18 quantum bits built out of it. So because you can actually access internal degrees of freedom simultaneously. So that's one of the advantages. And most of the hardware and fabrication techniques are common to both classical and quantum optics. Like the devices which we are trying to build, photonic systems are common to classical optics, which people use on a regular basis, and quantum. It's the source and the way you control are a bit of difference. And then the next part. But there are, again, a big challenge is that the designing control operations between multiple photons. In fact, photonics was one of the first candidates which people thought is the way to go with quantum computers. Like Professor Andrew mentioned in the morning, KLM model with linear optics, and Laflamme was one of my thesis advisor in that model. But the biggest challenge there was how do you make photons interact? Because photons have the specific characteristics. We can't do control operations. And then they thought you can do some post-selections and that became a probabilistic. So the success rate was very low of gates. And that's when the superconducting came over and started looking at it. But then there are ways this question remained. Like how do you overcome this issue and start building? So you can go for the next slide. But that challenge was something which was ready. But now, over time, there has been multiple different approaches. I think there's a broader 3 different ways people are looking at photonic devices. A discrete variable approach where you're controlling single photons, their internal degrees of freedom. That's where Psi-Quantum is trying to focus on. They're trying to address the million qubits over the next few years. And then this continuous variable approach where you're not looking photon at single photon level. You are looking at the Gaussian quantum states and then you're doing measurements on them. And then there is a specific kind of simulators where quantum advantages were shown, which is called photonic simulator, where about 74 qubits are solving one specific problem, which mathematically equates to finding permanent of a matrix, and which is a reasonably useful problem. And that showed a quantum advantage with the photonic system. So this is with this as a background. As I mentioned, there is an issue of photon interactions and how do you overcome, and there were some proposals in 2009, 10, 13, but it also involved different way of building qubits. I'm not going to the detail. It's a quantum walk approach where you have some operations and then you can try to overcome this interactions issue a little bit, but how do you realize them physically was a challenge, and these were mathematical proposals, and then we were also working for many years on trying to see how it can be done. So next slide, please. And then the issue here is the main approach for this is you take a single photon with multiple degrees of freedom, and then you also take a position space where you kind of try to entangle or create single photon entangled in multiple position space or other degrees of freedom and realize multi-qubits using single photons. And how, and the main crux of that is in the way you map the position space into qubit states. So we developed the architecture for that. It's a mathematical model, and where you can take position space, treat them as qubits, and you can scale it up to multi-qubits. So you can just move to the next slide. I'm quickly running over it. And then like the gate operations, we can control polarizations. I think mathematical details I can skip, probably next, yeah, okay. So these are just as operations, you can skip this also in the interest of time. The next, yeah, so yeah, you can actually run them all quick. There are the ways we have designed the whole scheme of how you can build a multi-qubits using single photons, like controlling the way photons propagate in different directions in geometries, and how you can realize 1 and 2 qubits, 2, 3 qubit gates, and even some of the algorithms. In fact, this is a published work. It's available in public domain in a research paper in 2001. So you can take the next slide. In fact, we also came up with some architectures of scaling it to multi-qubits. This is only one. We have multiple approaches of how one can scale, and this remain a mathematical model. And next slide. So what we did was we have tried to convert that into a physical system at IISc laboratory, where we take a single photon, and this is just a generation of polarization and path entangled single photons. You can go to the next slide. Yeah. So what we are trying to do is control single photon in a multiple path degrees of freedom. This is just a cartoon picture. And this we can realize 2 qubit. Use single photon in multiple path, we realize qubit, you can do some kind of operations, we do get an output out of it, and we can say that there is some rough density matrix. So what is the usefulness of 2 qubit which we generate? So as a sum test model, what we did was, this is a schematic of it, like you have a single photon in multiple path. So you can see on the right side, you can actually realize the 2 computational qubits and detect them in a detector. The next slide. So making use of it, we have, next slide. Yes, back, a little bit, Okay. This is also a test of entanglement, which says that they are really realizable 2 qubits, which can be used for quantum computation. The theoretical expectations and experimental, this is more of characterizing the 2 qubit system. And the next slide. Using this, we kind of have built, next slide, please. Yeah, next. Again, I'll just, so we kind of build a 2 qubit quantum random number generator. Is one of the most useful things for the cryptography, or where people are trying to look at how you can build a random numbers from a genuine quantum mechanical system. Using a single photon, by controlling operations, we could build 2 qubit system, and then test some of the operations, like you can actually go from, when we take it to write a 2 qubit system, we have coefficients of them, we can control over them and generate all possible states. So this only to test the workability of the 2 qubits. And now we are at the task of scaling up to the 3 qubits. The next slide. You can just, this is the architecture which we are working on. How do you prepare a 3 qubit system? And then start some measurement procedures. You can just skip next slide, next slide. And how do we realize the gates? So more architecture has now been developed, and we are trying to test some of the gates. And this is actually the background of our work. But this experiments have been done in a bulk optical setting, which there are, being very optimistic as a researcher, there are a lot of challenges here when we're dealing with path degrees of freedom, because there is limited way we can keep the photons in superposition, both the paths when you're doing operations. But there are experimental reports from across the world where, not in terms of quantum computation, you can actually do up to some 40 controlled operations between multiple paths, which means that we can actually try our level best to use 3 qubits and do some 40 gates operations in this kind of system. But a way forward would be to convert this bulk optical experiments which you are doing into an integrated photonics. Of course, when we integrate, we again have some losses and the coherence would go down. But there are multiple labs in the country which are working, and we have here also representative BK Das who work on integrated photonics IIT Madras, and then we have Samir. At some point, I had some discussions of the integrated photonic setups they have, and how we can try to see the conversion of it. Because as Vijay mentioned, or what Bala mentioned, it's not about reading some research papers and trying to reproduce. There are a lot of things which we learn when we are doing experiments which we don't get in any literature, and that knowledge is what is an asset which we have to carry forward in building technology or for future Indian, in Indian context. I think with this, I think I've actually taken a lot more time than this, so we can go.
and friends from the quantum community. Really a pleasure to be here with you again to meet up and discuss shop. As one who has been involved in the quantum technology kickoff since the early announcement by the government and the early announcements and funding, and also being a part of writing roadmaps, I think it's now time to step back a little bit and look at what is now unrolling. This is necessary in the larger interest of what exactly we are trying to achieve in the country. This title, Forever, came out of the same door through which I went, is from the Rubaiyat of Umar Khayyam, or if you have to believe another thing from Google search, it is from Alice in the Wonderland. But I have read it from the Rubaiyat. Maybe after I go through it, it will be clear what exactly I mean by this. This country has seen huge funding in a variety of things, from room temperature, promise of room temperature superconductors, to fullerenes, to nanotechnology, now graphene and many other things. But ultimately there is a gap between the promise of technology and what is done was science, but material science never ever came up to device technology, and that is the greatest weakness in this country. We don't have a single super fab or any fabrication things at an industrial scale in this country. And we are now talking about extreme machines, machines that work at a single photon, single atom level, where the demands are very great. And therefore, keeping in mind with that, I will make some statement, but I think I need first to tell a little about our own program at the School of Quantum Computing at the Defense Institute of Advanced Technology, which comes under a university under the Ministry of Defense. We started in 2019 the first MTech program in quantum technology. This is based on a realization that a lot of people were doing science, but what we required were actually engineers who can build systems, deliver technologies. And we are now running the third batch, and I'm happy to say that even before we can fully bake our students, our market is already taking them and absorbing them. And this is a good news for us. Now, our own activity in terms of research we are invested in quantum communication, both free space and optic fiber, quantum sensing with atom interferometry, quantum simulation. And what we are now planning to get into is photonic integrated circuits for optical quantum computing and quantum communication. So that gives my bias as to what I would like to bet on. So we work on the philosophy that engineers need to build things. So all our MTech students, by the end of their course, actually come up with small devices, which we hope will go into our industrial ecosystem. There are already a lot of people asking for them. Okay. Now, before I go on with a few slides I have, quantum technology in India, food for thought. Yeah, thank you. I need to make some statutory declarations and make my reasons for giving this type of talk very clear. This is a personal opinion, introspection, without claims to any truth value. It is genuinely well-intentioned that this country should see genuine growth in technology. No disrespect, even remotely intended, with the interest of the nation and the broader community in mind as to what this promise that we make to the funding agency and how we should really go about this serious business. Well, wherever I have gone, whichever agency, be they governmental, defense, intelligence, wherever, there is a tendency there are many funding agencies now, DST, MeitY, DRDO, DIE, most of them coming to the small community, the same people, but the seemingly same low-hanging fruit. Can you do a QKD over 50 kilometers? No, I can do it for 100, and so on. Now, these things are dated. We should recognize that we are 2 decades behind most advanced countries, and we need to catch up, as the earlier speakers have very forcefully conveyed. So we should get past thinking only about low-hanging fruit with immediate deliverables. This is a very, very wrong approach in my opinion, and not in the interest of the long-term requirements. Then there is a tendency to rush to the press with claims that are not really quite sustainable. This again, I can understand this enthusiasm, but this muddies the waters, and hence I think this is not a good thing. We should also not set unreasonable targets, especially where individual groups are concerned, and timelines, because there's a huge pressure. Can you do it in 3 years? Can you do it in 3 years? 50 qubits in 3 years, and so on. We should recognize very clearly where we are and what is the type of learning curve, very steep learning curve that we are faced with. Then there is, because of the other thing to buy, install, and use. I think this is something that we should totally abjure, in the sense that we would not really progress in our technological competence, and we will never reach the level of competitiveness in the international stage. This is not an approach we should take, even if we have to do it. I'm originally from the Department of Atomic Energy, where we lived under technology denial by most of the world, but we have now mastered end-to-end every aspect of nuclear technology that we can do. Same holds good for rocketry and other things. So we should take this, in some sense, in the same spirit. Then there is a tendency, because in the early time of DST, there are hardly a handful of groups that were involved in this process. Now, within 3-4 years, almost every major institute is now invested in this. That's a good thing in capacity building, but we are spreading resources thin, and that will not lead to technology. Now, among the do's, long-term strategies for targeted technological development should be made. Materials research should eventually go towards the fabrication of devices and from devices to technology. This is not an easy path, and good fabrication facilities are therefore required. Then develop gap technologies, and most importantly, already start putting in certifying agencies or processes, so that the claims can be well audited and we can move forward in the right direction. So active auditing and course correction are necessary even in the early days, and as Vijayan and others emphasize, ease of the purchase process. This is a major impediment, especially when you are trying to develop cutting-edge technologies. How do I go to the next one?
Enter.
Yep.
Sir, sir, 2 more minutes, sir. If
yeah, please. I will finish quickly. I am just, it's not moving. Can you go to the next slide? Yeah. कोई बात नहीं ऐसे जाएंगे. So we have this problem, what I call an entangled band gap problem, that material science research has always been well funded, but we are very poor in device fabrication and fabrication to technology solutions. And therefore the other band gap, when we compare our country with elsewhere, advanced world, there's a huge technology gap that has been growing and growing and growing. Very soon, it will be impossible for us to catch up even. So this, I think fundamentally, part of the problem is that we go for the assembly approach of, say, for instance, here buying control electronics processes, algorithms, and put together. But one should ask oneself whether this will lead to long-term strengths in technology development here. Regarding quantum computing, of course, there are different solutions: superconducting qubits, ion traps, NMR, purified silicon, diamond photonic quantum computation, and the last one has been a dark horse, and we should, I think, also invest in this, which shows a lot of promise, and that's where I is my approach to quantum computing. Of course, major impediment in all that is realizing on-chip devices. So with photonic quantum computation, photons, of course, are not gregarious creatures. So therefore, we have the positive thing that there are no decoherence issues, but they are difficult to engineer, two-photon gates, C-naught gates, and so on. But we have different approaches, as in other qubit realizations, like circuit-based models, cluster states, GKP encoding, coherent state encoding, or infinitely squeezed coherent states, maybe with a finite width. Last but one slide. So we should invest in photonic integrated circuit, not only with respect to quantum computation, but also that many components like Mach-Zehnder interferometers, Fabry-Perot modulators, ring resonators, stable interferometers, etc. have been devised, and a complete integration of high-speed optical communication solutions are also being worked out. And therefore, it makes eminent sense to do quantum computation with photonics, because these flying qubits anyway would be useful, necessary in other realizations as well. So for this, to succeed here, we have to focus on device fabrication, silica and silicon, silicon nitride, and possibly even hybrid technologies for realizing optical quantum computers. Last slide, wish to summarize. Explore new materials, focus on device fabrication, do not buy complete quantum computers. It may be a good revenue model for developers elsewhere, but we would never get anything of value by taking this approach. Be patient, accept there is a huge learning curve, focus on chip-level devices, choose the most promising qubit technology. Of course, the leading contenders are superconducting ion trap, and I wish to add photonic qubits as well. Thank you very much for your kind attention. Is there any questions?
Thank you very much. Thank you, Anindita and C-DAC specifically for hosting this type of wonderful symposium and inviting me to share my thoughts. And particularly, I think enough has been said that photonics is going to play a major role in quantum computation. So I'm glad to share with you that I have been involved in silicon photonics research since 2006 and continuing slowly but steadily. And I'll be, instead of, I think enough don'ts and do's already mentioned by Raghavan and others, Chandrasekhar also mentioned whatever can be done with photonics. So I'll be just sharing what we are doing at IIT Madras, how we are mitigating a lot of problems. So in 2012, we got Center for DEMS and Nanophotonics funded by MeitY. And from there onward, we could develop many fundamental building blocks like what Raghavan was saying, micro-ring resonator, Mach-Zehnder interferometer, and some modulator, all those type of things, design and fabricated. On all those design based on CMOS, foundry compatible. Because you know, silicon photonics is blessed by CMOS technology. So you can just entirely exploit the CMOS foundry infrastructures. And as a R&D center in IIT or university level, what we have done, we have developed some 4-inch wafer level PDK developed, and all the small scale devices and circuits we demonstrated, particularly the 1 qubit, 2 qubit, all those generated, and also on chip we have the device designed and demonstrated some noise suppression up to 75 dB. We have to reach up to 100 dB and so on. And very recently in 2021, again, MeitY came forward with our work, and they funded us with a Center of Excellence for programmable photonic integrated circuits. And with that, we have now we are focusing more on testing facility. Testing facility, as well as you know that 4-inch wafer, you can make small scale device circuits, all those type of things. But whenever you are thinking about thousands of qubits, millions of qubits can be done with photonics, and that is the ultimate solution. So we need to take advantage of CMOS foundry infrastructure. So what we have done, we have collaborated with Silterra Malaysia. So you know, Silterra Malaysia, they have actually 8-inch wafer foundry, and they have all the process, photonic device process they developed, and they are also offering, and many company startups, they are actually using Silterra, but they do not have their own PDK. So since our expertise for last 15, 16 years, we know how to design devices, how they work, how to characterize things, and we are developing wafer scale, fully automated testing facility. So we come together, we offer them that, hey, we can jointly develop PDK, and you can do all the circuit design by us, fabricated in your foundry, and we can test and we can develop model, compact model, etc., and we can go for large scale integrated circuits. And that worked out, and we have started working, and first design layout already given to them for their internal tape out, and that is going to come. And with the help of COE funding, we are developing all the testing facility, wafer scale testing facility, up to 8-inch wafer. And we have also collaborated with, because you know, ultimately photonics chip you design, you fabricate, you test, it works, but ultimately you have to package it. It needs your DC interfacing, RF interfacing, as well as your optical interfacing. So we collaborated with SI2 Microsystem Bangalore. They are expert in IC packaging. So they have all sorts of packaging, advanced level packaging facilities. And they also came forward very happily with us. And also in kind, they are collaborating with us. And 2 of their engineers dedicated for helping us to develop design rule for the packaging, fiber attachment, and also IC, DC interfacing, RF interfacing, all those type of things. And prototype level design already done, first level thermo-optic evaluation already done. So with this, we are going, as usual, we are just thinking that how to go for everything in the line of product, research, development, and manufacturing model. So we just try to see all the specific available which can be fabricated in CMOS foundry, which can be demonstrated in-house here. And hopefully by 2026, we will be able to develop or deliver first prototype of our silicon photonic processor with few qubits operating. Thank you very much.
Hello. First of all, I wanted to thank Colonel Nath and Dr. Anandita, as well as the C-DAC team for inviting me and share my thoughts here. I am working in the area of integrated optics as well as some... Hello? You are able to share? Okay. So actually, I am working in the area of integrated optics, and for my past almost 20 years or so, I have developed different kind of devices based on optical waveguides. And in today's context, actually, I thought, you know, for quantum computing application, this is one of the most appropriate technology as far as I feel. It is almost as competing as the superconducting qubits-based approach. And in fact, some of the things I thought I will share in the form of presentation, but time is not there, so I will just give an overview. Since morning, I have been, you know, listening to all the talks by Professor Barry as well as Professor Andrew. They have covered very nicely. They have given a broad overview about various competing technologies which are evolving, I will say. Not some are commercially available, but ultimately 10 years down the line, we will come to know which technology is the best one. But already there are indications. If we look at how the electronics industry has evolved, as we have seen in the previous, you know, talk by Mr. Matthijs, I think. So that trend itself shows what are the directions. And there are whenever a technology is evolving, there are 2 components of it. One is the scientific, you know, way of looking at the technology, which means the scientists work deeply on the theoretical aspects or the technological aspects. And another one is the economics side of it. Means which technology will be ultimately viable, that is ultimately decided by the cost factors. And I think in Professor Andrew's talk, he has given nice, statistical overview based on some responses collected. And that time I was just thinking, what are the factors actually? One is, of course, the technology which will be coming up or surviving in the market is the size, weight, energy consumption, cost. And this is like if we can, quantify in terms of cost per qubit, not just in terms of manufacturing cost, but also the running cost. Suppose we make a 500 qubit computer. What is the cost of that computer in terms of one-time cost investment for buying or making it, and also in running? Today's, whatever the researchers are developing, they are all lab prototypes, or they require huge investment, capital investment, as well as the technologically, they are very intensive. I mean, one cannot think of developing it overnight. It requires researchers' effort, continuous effort for past 5 years or 10 years to develop, and in the form of a technology which one can use efficiently, actually, reliably, I will say. So coming up to that level, it requires lot of effort and consistent effort. And that is where I feel the integrated optics approach is going to be playing a key role. In fact, Professor Berry has mentioned, when we are thinking in terms of billions of qubits based computer, that is where the optical technology is going to be one of the front runners, I will say. I will not say this is going to be the only technology. There may be many more competing technologies, or some more technologies may evolve over the period of time. But this is most likely because the light-based technologies have evolved very rapidly because of the quantum revolution, not quantum, the communication revolution, I will say, IT revolution, and things are available at much cheaper cost. All the components are easily manufacturable. In fact, semiconductor industry has helped in making those components at reasonable cost. And silicon-based, photonics is one of the possible, way of looking forward. And in fact, other than this, one more thing which came to my mind is that even for superconducting based qubits thing, one of the major requirement is the microwave-based components control electronics. And since I come from Samir, which is basically a microwave-based organization, I feel Samir can play a major role there. In fact, very recently, we have demonstrated 5G testbed, where we are working with other IITs in collaboration. And I think Madam is there, Madam Sunita Verma. She will agree with me that, Samir as a whole can contribute, not only for that, even for when you are talking about, the superconducting system to run. Basically, it needs to be encapsulated to protect it from outside environmental conditions. That is where EMI, EMC, we can provide lot of consultancy or ideas or support, even in terms of the packaging of that, this quantum computer. So in multiple fronts, probably Samir can contribute, or I will say MeitY can contribute as part of, C-DAC, Samir and CMET combination. So that's all I think I will say. Thank you very much.
So I am the odd man out. These are all measurement guys, and I am the only material scientist here. So from morning, I think we are all hearing that to increase the efficiency of systems, there has to be a lot of things that have to be done in materials research. So this was first spotted out by our secretary, previous secretary, Ajay Prakash Sawani, and he wrote to CMET that CMET has to look into this area. We spent out 3 years looking into what kind of materials exactly are needed for the country to become self-reliant, and what technologies we can contribute. So what we have done is that we have taken up 3 major technologies that are needed for the country. First is, as everybody is telling, that photonics is a promise. So in context of photonics and quantum sensors, we have taken up making diamonds. diamond NV center diamonds and setting up a whole fab lab to make NV center diamonds here in Pune. We are also looking at SNSPDs because these single photon detectors are very important for photonic quantum computing. So we are looking at them. At presently, all SNSPDs work at 4 Kelvin, but down the line, we are trying to scale them up at least to liquid nitrogen temperatures so that this photonics can go ahead. And the third thing, what we are looking, it is a little out of order, but it is hexagonal boron nitride, which is very much required for low power electronics based on two-dimensional materials. So these are the three main areas that we are looking into. We are a sister cousin of C-DAC and Samir, and we are just adjacent to this place. And maybe like in next 6 months, we'll be having this whole quantum materials lab. We are very thankful to our parent organization, MeitY. MeitY has funded us generously to establish this materials lab. And we hope that we contribute. I mean, we are the only organization in this country who is developing high purity materials for strategic sector as well as other applications. And we hope that we have taken up this mandate of contributing in the area of quantum materials. I mean, for computing. There are two major aspects why we took diamond. Diamond we have taken because diamond, there is a huge industry of diamond there in India, which is into the diamond manufacturing. So we feel that if we make this breakthrough of making doping very, what you call this, deterministically doping the NV centers in diamond, then we can directly, we have the know-how to translate this into a big technology. So this is from our material side. And we are also had a talk with Confluence to collaborate. Yeah.
Yeah, so my name is Sujay Chakravarti, and I'm an odd man out in many, many ways. So it's actually humbling to be here where the entire quantum ecosystem of India is assembled. And the first way I'm an odd man out is I represent industry on this panel. Everybody else is...
that completes ecosystem.
Everybody else is well funded. We have zero funding. So, quick story of our backgrounds. So, I'm an engineer. That's another odd thing. I did not learn physics, did not do a PhD in physics. But when we successfully exited our last startup, we, as a group, got very interested in quantum. And we spent a few years understanding what's going on, trying to study physics, etc. And decided that this is interesting. And this is a game changer. Like someone put it right, you cannot do what a quantum computer can do by building a better machine, by building a better traditional machine. So we said, okay, let's go and do it. As we went about this, right, we went into this belief that a quantum computer will not be built qubit by qubit, which is what we thought the superconducting guys are doing. Okay, we have 30, 40, 100, 200, 500. What we need is 1 million, right? And that's where we thought, okay, what can get us to 1 million? Photonics. So, okay, let's build a photonics quantum computer. Well, the good news is no one has built it in the world. I mean, all these experiments are there, but no one has a computer. Well, that's also the bad news, right? If it was easy, people would have built it. It's also interesting what happened when we said this. We said, okay, we're going to do this. And the first thing people told us, don't do it. Because, you know, as an industry, it's difficult. And in India, nobody will support you. You're not going to be successful. You're just going to waste money. Then we said, no, we are still going to do it. When we did that, people said, you know, there are people in the Netherlands. You can go to them. You can buy chips from them. And you can build a quantum computer in 3 months, 6 months, whatever, right? So we said no to that as well because we still believe in the million qubit era. And that's how Confluence started. We incubated out of IIT Madras with our friends here. And one of our founders is also from IIT Madras. He's not here today. Yeah. So Anil Prabhakar is pretty well known. He's one of our co-founders. I think he could not travel here. So the stage is for me to do this talk. The good thing is everybody has talked about photonics. Everybody has talked about the benefits, what can and cannot be done, right? So our lab is in Bangalore. We have offices in Bangalore, Pune. Anil is in Chennai. IIT Chennai, we have a JDA with IIT Chennai, so they help us a lot. We have a JDA with IISER Mohali, so a lot of the theoretical physics happens there. So our belief is that out of India, we will be able to build this computer. Our belief also is that we need a lot of money to do this. And this lot of money has to come from somewhere. I mean, people tell us go to government agencies. People tell us go to VCs. You know, both of them are interested, but we don't know where the money will come from. And our approach is show some results, get the money. Don't go out there with PPTs and get the money. So we are hoping that everybody in this room is going to help us out, and we are going to help each other out, and eventually be sitting here with the computer, you know, room temperature, right? So we can sit with the computer right here. Okay, that's all I had. Thank you very much.
Thank you very much. And now I request Dr. Joy Ghosh to give your views, madam. About 5 minutes time you have.
Is my screen visible? Hello?
Yes, ma'am. You are audible. Please go ahead.
And is the screen visible?
Yes, yes.
So, I am visible, but maybe at the end of the talk when I unshare the screen. So, I'm Joy Ghosh from the Department of Physics in IIT Delhi. First of all, thanks to all the organizers of this symposium for giving me this opportunity, and a special thanks to Anandita for this invite. The symposium is called as Quantum Computing Ecosystem Building Blocks. And so I thought I'd start from a very basic level, and I don't do hardcore quantum computation as such, but I'm interested in the building blocks. So we are a small lab based in IIT Delhi, and there we have our experiment. But just to start with, I wanted to show this famous figure, courtesy from the group of Kimball. This is a picture of a quantum network. Is the slide visible? I mean, like I'm changing the slide. Is it visible?
Yeah, it's visible, madam. Please.
Yeah. Okay. Okay. Thank you. I go on. So this is a famous picture that talks about a quantum network, and the quantum network is at the heart of any quantum computation. So any quantum computer will, have its one of its building blocks at the heart of it as the quantum network. And this quantum network, as people can imagine, they are formed of quantum nodes and quantum channels. It's a very popular picture. So nodes are where information is generated, processed, and stored. And typically atomic qubits, or any stationary nodes for that matter, superconducting qubits, atomic qubits, all these systems, NV centers in diamonds, quantum dots, these can act as very good nodes, quantum nodes. On the other hand, these nodes are interconnected by quantum channels, which are basically fulfilled by flying qubits, and so they are responsible for a quantum state transfer between the different nodes. So, since we are talking about flying qubits, photons is the first thing that comes to our mind, and so this has to be this particular qubit has to be mobile. So these two together can form what is known as a quantum network. So typically this shows a very simplistic picture. So I just given my previous experience, so this is just a picture. This is a set of 8 calcium atoms that are trapped, calcium ions rather, that are trapped in a single trap. And let's say these are 4 different traps, so they form 4 different nodes. So the internodal interaction can take place either by a direct transfer of photons, or there was a novel idea that if you have an entangled source of photons, something like this in this lower corner, and the signal and the idler go to different nodes and they get absorbed, then thereby they transfer their entanglement to the atom. And so starting from a photon-photon entanglement, you can go to an atom-atom entanglement, and you can have these two nodes talk to each other or interact. And this is how you would, start realizing the basic interaction that is required. So the key task is to interface atoms and photons, control their interaction, and also establish entanglements between each. So with that motivation, actually you can, so the first thing would be to have efficient sources of entangled photons, and these entangled photons could travel across space as flying qubits. So flying qubits are again moving carriers of information, and there are different kinds of properties of photons or any other mobile entities such as electrons whose property we can use to encode a qubit. The stationary qubits, on the other hand, are localized in space, as I mentioned, and this could be several kinds. Now, when we are talking about the photonic qubit or the flying qubits, there are properties that can manifest a qubit. For example, the polarization is typically something that we work with. Also, orbital angular momentum is another physical property of the photon that we work with. And these also, by the way, help in generating high-dimensional states, which are also lucrative for high-dimensional information transfer. So, with that, I would like to go on to this slide, which is really a dense slide, but this, in a nutshell, it talks about the several things that our group is currently involved in, several activities that our group is currently involved in, and all of them actually involve photons or light. So basically, utilizing down conversion, which is spontaneous parametric down conversion, we are interested in generating pairs of photons. And these pairs of photons could be in different wavelengths. So we have projects which are on fiber-based quantum communication. We also have projects for free space quantum communication. So these two involve generating photons, but they are at very different. So this is for visible to free space. So the wavelengths that are interesting for free space quantum communication. And the fiber-based ones are those that are involved in generation of 1550 or telecom photons. So we also have interest in the detection of squeeze light. We also explore another process which is spontaneous four-wave mixing. This also generates two photons which are correlated and entangled, called as signal and idler, just like your SPDC. But the technique is slightly different. It is a third-order nonlinear interaction. It's type-free and it's four-wave mixing. And silicon is very lucrative material for realizing this particular operation. So we are involved in that, and apart from that, we are also involved in semi-classical properties of light, exploring EIT and so and so. So for today's exploration, I just wanted to base on this fiber-based source. So this is a source of entangled photons that we are trying to build in the lab, and we have some results. This is also pertaining to a DST Quest project that we have, and this is also pertaining to a DST Quest project that we have. And behind this is you start with an entangled photon source, and you channel it into multi-channels, and the application is towards a multi-user QPD. But this source is actually very, very efficient, and it can be used also it can be utilized in terms of a quantum network as well. So this is a fully fiber integrated, WDM integrated source of photons, and here are some of the characteristics that we have. So it generates degenerate photon pairs, signal and idler, both at telecom. So the center is at telecom, but these are ultra broadband, as you can see. So these are real photon counts, the normalized counts versus wavelength, and this is versus temperature. And this is highly broadband, ranging from 1520 to about 1580 nanometers. So it's like around 40 nanometers broadband source. And the spectral brightness of this source is about 2.5 × 10⁻⁷ frames per second per milliwatt per nanometer. So we also explored the cars for this. So as a characteristic of SPDC and how good your source is, spectral brightness is one parameter that has to be explored, and how well your photons are correlated with each other, that is determined also by the coincidence to accidental ratio of the car, which also is another way of putting the G20 or the second order correlation. And for our source, this is about 1300 for the broadband photons, which is a very big number, and it competes with the international sources of photons that we have at telecom. So this is an experimental joint spectral intensity that we encountered, that we measured with our photon source. This side is the idler wavelength, this is the signal wavelength on the axis, and these are actually, these yellow dots are actually the coincidence peaks. Measurements are done for the entire regime for this entire area, for this entire region. And this negatively inclined JSI shows a highly correlated, temporarily correlated source of photon pairs. So with that, with our highly correlated source, we went on to the measurement of polarization entanglement. So for that, here is your source, which is the type 0 PPL and waveguide. We put it in a SINAC interferometer form, and we try to measure the coincidences. And so we did initially we tried to play in only the linear basis, which is HV and diagonal anti-diagonal basis. And the four different sinusoids shows the so these every point on the sinusoid is actually a coincidence which is collected over 20 seconds of time, and this kind of a sinusoidal pattern shifted with the correct amount tells you that okay, we can go forward and try to measure our entire state, which is the state of the biphotons basically. And with that, we went forward to quantum state tomography. And this is the kind of tomography result that we have. This is real rho, and this is the imaginary rho being your density matrix. And if we want to find what is the fidelity with the 5+ state, because this is what we were expecting from this type 0 source after after doing the SINAC interferometer. And the fidelity is not great as of, it hasn't crossed 90% yet. We are still trying to improve our data, but nevertheless, this is like 84.4% without any background subtraction or anything. This is just from the raw data, and this is where our source stands. So with this, actually, this can be applied for a quantum network scenario or several other applications. Currently, the project is for multi-user QKD, but this has the potential of being also utilized in a quantum network. So apart from that, actually, we also look into several kinds of designs which are possible in lithium niobate and in KTP. So these are nonlinear optical, second order nonlinear optical crystals. And we, last 2 years, actually, we explored a lot in, looking at different kinds of designs that can generate entangled as well as hyperentangled photons. And these are some of our results, where we have shown the generation of hyperentangled photon pairs in a PPLS rich waveguide. And this is everything is based on spontaneous parametric down conversion and utilizing quasi-phase match crystals. So in the country, actually, I would like to mention, since there are many people in the panel from material sciences, maybe it's one more problem that could be interesting for the materials people in our country is because our country lacks in producing or fabricating such materials, be it KTP, be it lithium niobate, which can be, quasi-phase match. Basically, we would like to periodically pole, and if possible, also have them bi-periodically pole. So more than one particular kind of polling period, as you can see in the designs here. So it would be really nice because right now there are many users of SPDC generating such photon sources, and even for linear optical quantum computation, if it is to be based on Chi2, not silicon, because silicon is based on Chi3, but even for silicon we need foundry in our country. But even for Chi2 processors, we don't have very, in fact, we
sorry
don't have
for the interruption, madam. In the interest of time, can you please conclude in 1 or 2 minutes? Yeah.
Yes, sure. So maybe it will be an interesting problem for materials research people also to take up the same in order to fabricate such crystals and have them, such waveguides on a waveguide geometry. So we looked at several kinds of such designs as well, and yeah, so these are just some of our recent publications because we explored both silicon as well as Chi2 nonlinear crystals, and yeah, I would like to end.
Yeah, thank you very much, ma'am. Thank you very much. And now we are open for questions. About 3 to 4 we can take.
Yeah, quick question from the panel. We have heard about the superconducting quantum computer being realized in some sort of a actionable, programmable form. But can anybody give us the example where a photonics-based processor has been realized in this form with entirely all the subsystems in place, and how is it functioning?
Hello. Yeah. So I think currently one of the practical advantages, or what we call quantum supremacy, if it has been shown, it has been shown with photonics, where the Chinese group which...
no, I'm talking about India, where in India have we been able to realize a photonics-based machine?
So when,
and
okay, so in a lab, like for example, my lab, we have 2 qubits. So, and we are scaling up to 3 qubits.
So it is complete, the entire ecosystem is there with the...
So when you say, yeah, okay, so like in a lab, what we try to have is an optical component, so you have an electronic setup, and it's not like a one package, it can be moved out.
Yeah.
But it is still there, which can actually be put in a package, and probably even what Joy Ghosh presented, where she has 2 photons and she has been able to control the whole states where that's also a 2 qubit system which exists in her lab. So 2 qubit system and electronics associated with it exist, and scaling up where again the issues were there, how people are going to do a control NOT gates, and there are
is this programmable, the machine you have?
So
can you put it on a cloud, or people can access it or something like
no,
that?
right now not at that stage. So that is where I think one has to have most of this gate operations we talk about. We have to use wave plates where they have to be electronically controlled. So that integration part has not been done.
Right.
So these are like, we to decide certain operations, we have to go manually and then do the setup for that, and then we get an output. So at that stage, and probably that's where we have to see how we take it.
So what is the roadmap? How many months down the line will we be able to realize such a thing in our country?
This is actually a tough question because like for example, detectors when we talk about, right? So I have ordered detectors to realize 3 qubits, I need 8 detectors, and there's been a waiting time for it, and then we don't get any efficient detectors. So there are a lot of other logistics involved with it. So might be like, even to see a 6 qubits to something like that, it would still be 1.5 year down the line.
Thank you.
To look at it.
So superconducting, can anybody say that when do we go up to 20? Any timelines or roadmaps? Yeah.
Yeah, so it's very hard to put a timeline because it all depends on laying a good foundation. So as part of the MeitY project, we have promised 4 qubits, but of course COVID happened and we got delayed a little, but I think in the near future we will be demonstrating 4 qubits fully programmable processor in about 6 months time. By this summer, that's my prediction.
Okay.
But to go to 20 qubits is a whole different game. And for that we need to not rush. I think we cannot, have the timelines unrealistically short. So we should spend the time, do the basics right, and then once we have a strong terra firma, we can spring on upward. Yeah.
I think we should try to develop the subcomponents of this system, maybe for superconducting or maybe for photonics. We should try to develop most of the components in the country because that will reduce the lead times, and that will lead to a very fast practical realization. Because if you look at superconducting qubits, we all see that now IBM has put its own web, but we all don't see that IBM has put like 20, 30 years behind that Josephson junction. So they have 30 years of research that has gone into practical application. So if we want to really look at the Indian context, we should list out what all we can do. I mean, many different organizations, academics and all other organizations should come together and depending on their expertise, they should propose that, okay, this component will take the mandate to develop this component. And if everyone takes a share of the mandate, I think maybe 5-6 years down the line, we should have...
Or maybe whatever open architecture was being propagated, we have something in place and keep replacing the various components with our developments as and when they take place. Would that be a better thing to do?
That may also be a practical option.
Thank you. Confluence, you were trying to... Okay. Yeah.
Yeah, so you asked the question of when do you think a photonics processor will be built out of India? My response to that is, I don't know when one will be built in the world. So it's okay to take a photon and manipulate it. Okay, everyone's demonstrated that. There are no real photonic-based quantum computers. And when one comes, yeah, I know. So.
Lunch is going to finish at 3.
I think we both have to share the same mic.
Yeah, this is fine. I think, when we, so what is a photonic processor is what we have to again go back to. If you are doing if you are talking about the demonstrating gates, the researcher's IQ we started 20 years back, he has laid down all the gates operations, the gate success rate, and they're all publishable results, right? So now putting them together, like where is that confidence when he says he's going to do a million qubits? So they have results, so they know how to do the gates operations and they're building. Now when we talk about supremacy, either with a photonic or a superconducting qubits, so there are two ways we try to talk about supremacy. Any quantum advantages you build either for sensing or various other communications, if quantum physics is giving you an advantage, that is one form of supremacy. In computation, when you're talking about supremacy, we are trying to look at the computational process which no other classical computers can do in the existing architecture. So academicians over years have tried to figure out or have some proper scale, why is this 50 qubits looks important? It's because 50 qubits can generate a quantum states which no classical computers, supercomputers can do. So now what is the usefulness of that? Like how much operations can you do? A good estimate of number of operations, like for example, if you are doing some 300 quantum gates operations, which means that you have reached a quantum supremacy. So now if you are talking about like either photonic or superconducting, none of them might have demonstrated at that level of doing 300 or 400 gates within that coherence time. And that's where the challenge exists when you say whether a ready quantum processor exists or not. IBM might be doing 400 or 500 qubits, but have they been able to realize for 300 gates within that coherence time? No, that is a challenge which they are working on. In the morning talk, we saw they have to go back. So I actually disagree with the processor exists or not. A commercial one may not exist, but the labs have demonstrated few qubits. In fact, the 16 qubit, the real 3 degrees of freedom, it's one of the most example paper, or like, most of the photonic community do look at it as an example where they're using 6 photons and have demonstrated a clear 18 qubit operations, a controllability of this. So which means that you do have an 18 qubit demonstrated codability. There is an issue here where having photons simultaneously generated is a challenge. Like in our lab, we can have 2 photons simultaneously generated. It might be in Joey Ghosh lab. But to do a more than that, simultaneously controlled single photon generation is an issue. With people who have worked for decades, like 2 Chinese labs, and they have kind of mastered it and they've found some ways to have multi-photon simultaneously generate and get to that level.
No,
so
I'm in no way, we are not here to undermine anybody. We are here to sit together and see.
Maybe.
Yeah. No, it's okay. Yeah.
No.
So thank you.
I should have said a universe.
Yeah, I think we. You want to ask something?
Yeah.
One more
just
question. One more quick question, and then I think we wrap up.
Just quick comments. So I completely agree with Chandrasekhar. So in the lab level, it is demonstrated all the processors, but commercially not available. And in India, I think all of them are doing just bulk optics. So anything you go for a real processor, you have to use integrated photonics, so CMOS foundry. So we are hoping that we can do it at least few qubit processor by 2026 in IIT Madras. Yes. From their know-how, everything will be useful, yeah.
Very short comment to your question. See, this overmuch emphasis on the number of qubits is wrong, because a qubit certainly, or a few qubits do not a gate make, and that's not the way to say that we'll develop all circuit-based universal quantum computer. So this is a wrong thing to emphasize. Now the question with photonics, there were obvious difficulties in making photons talk to each other, and therefore making a universal set of gates, like a C-naught gate where a 2-photon gate is necessary. But now we have gone past that stage, as Chandrasekhar has said, and there are alternate approaches. For instance, the approach Zanardo took, where there is a huge exponential increase in the number of detectors, is obviously not the way forward. Not even perhaps the qubit way of doing it. I would rather emphasize that alternate methods of doing it with continuous variable photonics in terms of squeezed, infinitely squeezed states, coherent states, and so on. So there are, like as in other qubits, different ways of doing it, and these are still early days. Thank you.
Thank you, sir. Last question before break.
Thank you all for this informative and discussion. So my question is towards the photonic processor. I just want to know, if we talk about the bulk optics, and now we are talking about the integrated photonics, but most of the discussion at present, like whatever information we have got, is all the photonic processor is based on the polarization state of the photon. Means information is encoded in the polarization of the photon, even with the photonic processor. So I just want to know, all this processor needs to be interfaced with the optical fiber. So as we know that polarization is going to be tempered if we pass through the polarization, if we pass through the optical fiber. So how are we going to address this issue if the information is encoded in the polarization?
Now the first assumption that it is all polarization qubits is fundamentally incorrect. There are many other degrees of freedom, like path entanglement, phase, and so on, that the photon offers that can be used in qubits.
See, you have to make the best use of everything. Like polarization, if you are sending it in optical fiber or in a free space, the degree is maintained for a longer, you have a better coherence time. That's why it has been used with communications. They do remain coherent for a long time. So you can't ignore that. There is an advantage which polarization degree comes. So you have to combine with other degrees of freedom, like path and then time bin. So people are thinking of even orbital angular momentum degree of freedom. So there are various degrees of freedom you can bring in along with them. So at the end, you have to convert them into a computational basis. I can actually treat one qubit as polarization, other qubit is path, and other qubit might be another degree of freedom. Using a single photon, I can generate a 3 qubit. So it's how you integrate or how you combine these degrees of freedom of photon and how you can control them. Where still a lot of science is going on. It's not that every week we do have papers of how you can combine these degrees of freedom and how you can control independently them or together in a combined effort. So it's like, the jury is not out. So everything exists.
Thank you, sir. And I think the next of the questions can be taken offline during lunch session. Thank you very much for all the panelists for.
Hello. Now I request the session chair to kindly felicitate the panelists and speakers. Thank you all. With this, we conclude our first session. Now I request the Colonel Ekinath to felicitate our session chair. With this, we now break for lunch. The next section will begin at 3:10. Meanwhile, the participants are requested to visit the stall exhibits from our industry partners, where various work in the area of quantum computing is showcased. Thank you.
Check. Hello.
Hello. Please be seated. We're going to start the next session soon. Hello. Good afternoon, everyone. I will take you through the next session, which is on dilution, refrigerators, and SNSPD. This session is chaired by Mr. Amit Saxena, JD, C-DAC, Pune. I request Professor Gregory N. Goldsman, Moscow State Pedagogical University's Kontal, to share his thoughts. He is connected with us virtually. Over to you, sir.
Thank you, Professor Gregory. We would like to request you to please share your slides.
We are live now.
You are on mute. Please unmute yourself. Yeah. We welcome you, sir.
Yes. Do you see my slides or not?
We can hear you, but slide still we are not able to see. You can just share it, sir.
Okay, I will do it once again.
Yes.
Yeah.
Yes, sir. We are able to see the slide. You can start, sir.
Thank you very much.
Thank you.
Yeah, hello to everybody. My name is Gregory Goldsman. I am a professor of Moscow State Pedagogical University, and also I am a founder of a company, Moscow State Pedagogical University, and also founder of technology. So in my talk, I would like to tell you about superconducting nanowire single photon detectors and photonic integrated circuits for quantum computing based on photons and ions. So in my talk, I will start from the very first papers about this technology. And now we have 20 years of that. So 20 years ago, we published 2 papers. First, idea of device physics, and second one, this is about device. And next, I will tell you a few words about unique material, our course material for this technology. This is ultra-thin superconducting niobium nitride film. After that, a bit historical introduction about a precursor of this technology. This is superconducting hot electron bolometer. And I will show you a few slides about application in the terahertz radio astronomy. So we switched that time from radio astronomy to quantum physics, to quantum optics. And then in few years, we switched from SNSPD physics to commercially available devices and systems. And Scantel company And then one slide about first implementation of NBN SNSPD technology for silicon CMOS IC device debug. Then main part of my talk, breakthrough in single photon detection from nanowire to microwire superconducting single photon detector. This is our last interesting result. And for this result, it is interesting to see how can a small hot spot in superconducting film turn a white strip into a resistive state. This is few words about physics. Then next important technology, traveling wave single photon detector with near unity quantum efficiency. This is superconducting stripe on optical waveguide. We started with that 10 years ago. And then silicon nitride on silicon about several devices and quantum photonic integrated circuits. And then I came to my conclusions. So first about 20 years from the first observation of this device and first idea of device physics. So that time we calculated how we can respond for a photon from superconducting stripe. And that time in our observation, we see this superconducting nanowire with in superconducting state, in supercurrent, and a photon on it, and hotspot, and then critical current is not enough, and we have switching to normal state, and then we have a click from the device. So 20 years ago, we started with this new technology. And again, this technology based on the unique material. This is niobium nitride as a superconductor on a substrate. And here you see two devices or two films. One of that niobium nitride on silicon carbide and second one on silicon. And this is two different, how would say, objects. On silicon carbide, we have monocrystalline, very perfect film. But on silicon, we have polycrystalline and disordered film. And that time, it was a question, which object is good or better for our technology? And then we started with physics and technology, and we see the second one. So polycrystalline and disordered film is much better. So second object is our horse material. What we need from this material, we need critical temperature, superconducting transition temperature, about 10 Kelvin. For 4 nanometer thick film, we have critical current density like 10 million amperes per centimeter square. We don't have centimeter square, of course, because this is nanowire, but still this critical current density is very high, and this is actually a record for such a device. But then 10 years before that, it was a different device, but also very interesting. This is hot electron bolometer mixer for terahertz astronomy. Again, it was interesting physics inside the device and behind the device. And this is two-terminal device, like two contacts and substrate. And what we can do with that, this is very small nano device, two contacts and antenna for terahertz electromagnetic radiation. And then we switch through space qualification of our device and started it with Herschel Space Observatory launch on May 2009. For our device, it was bands 6 and 7 hi-fi instrument for 1.9 terahertz. And up to now, it was very interesting results from space from this observatory. But when we that time saw that our fast terahertz detector can be fast and sensitive, and energy it can detect about 1 attojoule, we saw that time that we can switch to quantum optics, but because 1 attojoule, it is exactly the energy of optical photon. So it was our motivation to switch from terahertz radio astronomy to quantum optics. And in few years, we see that this device is very interesting for practical applications. And now Scantel company has practical receivers based on SNSPD with quantum efficiency for commercial devices like 85 up to 90% efficiency at telecommunication wavelengths, and very small jitter, maximum count rate, and very small dark count. What is interesting here, that even in the middle infrared, we have good enough devices, and this superconducting single photon detector is the only technology for count photons in the middle infrared. So for this technology, we of course need very good facilities like e-beam lithography, reactive ion etching, and so on. And a real device looks like very long nanowire made like meander type device, because it is nanowire and photon is much larger than the wire. So we need to fill our area with this nanowire. So this device is still mandatory for applications. And the first application we started with that again about 20 years ago. This is silicon CMOS IC device debug. In this technology, what is interesting that it is possible to see every couple of transistors in integration circuits through silicon substrate. And then in real time, we can see how NMOS transistor emits near infrared photons, and also P-type transistor, when current gets through both transistors when this couple switched from one position to another position. So it was very interesting and useful technology that we installed in several companies in the United States and also in Taiwan that time. Then I switched to 15 years to now, to interesting results that were published actually 4 years ago. And this technology started from nanowire detectors to microwire detectors. And that is very important for fabrication and also for application. The very first idea came from a theoretical paper, our theoretician Vodolazov. And in this theoretical paper, he predicts that if critical current can be very close to the pairing current, then we can use microwire to detect photons. And then in a year, we published experimental paper about that. In this paper, we use this depairing current for our device. And here I would like to show what does it mean, depairing current. This is a plot from superconducting electrons, Cooper pairs, versus super velocity. And this Cooper pair density goes down when velocity is high enough. And then this critical current density has a maximum in this plot, and this is the pairing current. So our film should be good enough to have this critical current close to the pairing current. In our first paper about microwire device, it looks like that, like constriction type microbridge. But this W, this width of device was, how to say, much much wider than nanowire, from 0.5 micron to 5 micron, and we see that yes, we have critical current close to the parent current, and then we see the device works as a good detector. I can explain a bit, if I have a minute for that, how small hotspot in superconducting microwire can turn a wide strip into a resistive state. So it looks like a hotspot has gradually changed superconducting electrons, and if current is high enough, we have a couple pairs of vortices start to nucleate in the center of hotspot, and then one of them goes to one direction and another one to opposite direction, and then we have a resistance and click of our device. Next part of my talk is about quantum photonic integration circuits, and the only technology to detect photons on it. This is traveling wave single photon detector. We started again 10 years ago with that in collaboration with a group of Professor Tang in Yale University. And then we see that if our nanowire goes at the same direction as a light in the waveguide, then we have very good absorption of photons and close to 90% quantum efficiency. So at the very first paper, we see that this is very good technology for quantum photonic integration circuits. And during this 10 years, we see that, again, this is the only technology for that. So then, on our devices, we can fabricate grating coupler, Y splitter, waveguides, and the device with different widths, and can optimize our detector on a weight, and then device detector looks like that. This is a waveguide with a light and nanowires and two contacts outside of waveguide, so we can detect photons that come to via waveguide to our device. And on the chip, we have a lot of devices, and then we calculate absorption, and then device output response. And we see that maximum of response, so detector efficiency, on-chip detector efficiency has a maximum at 80 nanometer wide device, and it is about 90%. So probably I don't have enough time to show you how we can optimize our devices with fabrication a lot of devices on chip, and then use devices with different parameters. Then we can calculate every device and measure these properties and compare them. So this optimization. At this time, this optimization of grating coupler. What we need for quantum computing on chip a lot of different devices like interferometers, O-ring resonators, directional couplers, grating couplers, beam splitters, and arrayed waveguide gratings. So we can fabricate different devices like that. And the last slide and the last point of my topic is an example of quantum photonic integration circuits for entangled photons generation by 4-wave mixing, then filtering, and detection using O-ring resonator, Bragg waveguides, and SNSPDs. So on chip we have all such a device, so we can start with entangled photons source and finish with detectors. This is just one of our devices and products. And now I can say thank you for your attention. So I have no time left. Thank you.
Thank you, Professor Goldsman. Now the house is open for the questions.
Okay.
Sure. So once again, thank you, Professor Goldsman, for your enlightening talk. Thank you for your virtual presence. Thanks a lot, sir.
Okay.
Now I request Mr. Brian Chu, founder, Mabel Quantum Industries USA, to deliver his views.
Это следующий. Я так и не сумел посмотреть на время, уложился или нет. Нет, вот. Ну, у меня 21 слайд.
Hi, everyone. Thanks again for the organizers for inviting Mabel to this conference. I think we're very happy to be here, very excited to be in person again with the Indian ecosystem, and very excited to be part of this journey. I think it's most exciting when it's during the brainstorming phase as people think about what solutions could be put into kind of their roadmap and their ecosystem, and we really love to be a part of these discussions as we think these are some of the most rewarding conversations that we can have. So today I'm going to talk a little bit about cryogenics. We have heard from the superconducting folks kind of mentioning, alluding to cryogenics, and cryogenics I think is really kind of, when you think about a superconducting quantum computer, 99.9% of the physical footprint is the cryogenics because it's just so big. If you think about the QPU as the brain of the computer, then the cryogenics is the heart because it really gets the QPU down to the code temperatures it needs to operate. So I want to begin with a brief introduction. I'm Brian. I'm one of the co-founders of Mabel. We are a company based in Denver, Colorado. We are a startup. We were in stealth for a while, and we came out of stealth at the American Physical Society March meeting last year. We are venture-backed, and we have support from the US government to scale. And I'll tell you a little bit about what our company does. But we build enabling hardware for quantum computers, and our two products right now are dilution refrigerators as well as ultra-high density wiring cabling. And I think those kind of go hand in hand when we think about kind of the problems that we face in scaling quantum computing. So dilution refrigerators are really the foundational hardware for quantum computing research, especially when it comes to superconducting. Other kind of qubits, such as photonics, also require dilution refrigerators when it comes to readouts. But for superconducting, having dilution refrigerators is the core to the operations. And these fridges go down to about 10 millikelvin. And on this page, I show a number of our kind of competitors who have been in business for many years and the systems that they have built. Dilution refrigerators actually came out of Nobel Prize winning research in the 70s, and it hasn't really changed that much over the past few decades. If you have ever been to a facility with a dilution refrigerator, you have seen these equipment, and you know that they are pretty complex in terms of kind of the footprint they take up, but also in terms of operations. Most of the time you have a PhD student kind of like whose full-time job is there to like operate a dilution refrigerator. And many people who are in superconducting kind of quantum research have had like the horror stories of their dilution refrigerator not working because there's a leak and someone is spending a year of their PhD trying to find and repair that leak. So as we think about kind of the quantum future, and I think a lot of us are here today to kind of brainstorm where quantum is going, both in the world, but also in India today. I think there are a few core things that I like to talk about in terms of cryogenics. I think the first is really qubit fidelity and trying to identify and reduce kind of the factors that affect this. One part of this, and I'll talk a little bit more when I talk about the technical kind of details of our systems, is really related to the mechanical and electrical noise that kind of affects the sample and trying to reduce that. And I think our other speakers have alluded to that today as well. But the second piece of this is really kind of thinking ahead when qubits become more stable. How do you have your fridges stay cold for years instead of months? Because right now, people are operating in a mode where they're switching kind of their samples pretty often, and they're not really thinking about how do I have a fridge that is just cold forever and accessible through the cloud. The second thing, I think, which Andrew talked a little bit about in terms of wiring count, is that there's a notion that you need more cooling power as the qubit count increases because there are more wires to kind of support that. We think that there's two parts to this. There is the concept of, in philosophy, of more is more. But as I like to say, we want to do more with less in Mabel, and we want to try to promote scalable systems without necessarily linearly increasing kind of the cryogenic systems. The third point, I think also Andrew touched upon and Matthias touched upon as well, is really this open quantum architecture. As quantum progresses, I think there's a need to be interoperable with kind of the different systems out there. And Andrew really talked a lot about interfaces with other parts of the stack. So for us, it will be the control electronics and then the software on top of the control electronics. We have invested very heavily as a company kind of to build those interfaces, because as the industry matures, we think less and less users should be spending time buying these separate systems and spending a year integrating them. What we really focus on wanting to deliver is these like full stack solutions that come customized to your kind of research needs, but also start working once it's here, so that you can focus on the hard quantum research that you need to do. So I think that's the fourth point really, which is we want to, as quantum computing progresses, and I think many of you have like thought about this in terms of ordering systems from around the world to kind of build a quantum computing research facility here in India. The thought that you have to both deal with the lead times of all of the vendors and then come here and make sure that it all works together, I think is a very daunting one. And I think this is something that people shouldn't have to deal with in the future. It's like really, how do you move as quickly as possible to experimentation and to research, and I think particularly as you guys thinking about the programs here, like what is the stack that you guys want to start with so that you can quickly get to your validation experiments, and I think that's really key. Like and this comes back to kind of the investments in the interfaces that we'll talk about. And lastly, I think improving ease of use is something that we really want to focus on. PhD students are kind of the core users, or postdocs or professors are core users of quantum cryogenic devices today. But as quantum computing grows, you can imagine master students, or in the US, like when they want to deploy it to kind of a military base, a field technician being able to operate these systems, because it's important as these mature. I mean, going back to classical computing, when the first IBM computers were kind of invented, they were large systems, but then there was both the miniaturization, but also ease of use kind of as the industry progresses. And we really think that that's where, at least for cryogenics, where the industry is going to start moving towards, because I like to say that we want to build things that you don't have to worry about. Basically things that it's like a battery, like that's just there powering kind of your research, and you don't have to worry about it working. And I think that's really key, because the problems on the kind of qubit side are many, as our different speakers shared with us today. So I'm going to tell you a little bit about our solutions and how we have kind of taken into account what I've just talked about as we kind of design for a quantum future. So this right here is kind of our first product, the Icebox, which is a dilution refrigerator. Everything fits in two 19-inch racks, and so footprint-wise is about 10% of that of competing systems today. But it does have the same amount of cooling power, so it's 500 microwatts at 100 millikelvin compared to kind of like the industry-leading systems today. But what we've really focused on is kind of ease of use, from the software interface to like changing the sample, and I'll talk more about this in the next few slides, and also focusing on reliability and scalability. As you think about quantum being kind of the core of like India's growth in the future, you think about quantum data centers, and you think about having 20 or 30 cryogenic systems and how they operate together. And that's really kind of the future we're envisioning as we design our systems. They're not necessarily problems people think about day to day today, but from a government perspective, from a policy perspective, from a usability perspective, like we think all of those factors are super important. So I'm going to skip past this, and we can talk about this offline. These are just some of our system specs. As I mentioned, like we are a 10 millikelvin system. It gets to 500 microwatts at 100 millikelvin. A little bit on the wiring capacity, but I will talk more later, is that we can support more than 3 times the amount of qubits compared to competitor systems because of some of the novel innovations that we're focused on. So, as I mentioned, one of the things that we really kind of, as we thought ahead of what a quantum future means, is like thinking about code decades versus code months, because you want these systems to be really running very smoothly, either to house your, so that you don't have to worry about it when you're doing your experiments, or when you have a working quantum chip, just like accessing it through the cloud and making sure that the uptime is maximal. And that's really what we are focused on in terms of eliminating a lot of the common failure modes. Anyone who has worked with these systems before have dealt with leaks, as I mentioned. So these leaks cause like helium to leak from a certain point in the system, and they're very hard to find these leaks. And a big failure point of this is that some systems use like acid flux and solder, which basically degrade over time, and therefore introduce these leaks, and it makes it very hard to find them. But we have also eliminated things that other things like rubber in the system that kind of are points of degradation. We have swapped out kind of the score pump for a micro roots blower, which allows for as maximal time without needing to kind of service the system. If you are familiar with this system, most systems today require you to top up the kind of nitrogen in the system every 2 weeks, kind of for the nitrogen traps, which are things to use to clean helium. But for us, we have thought differently about that as well, because we don't want to have these common points of failure where human error can cause your fridge to either be damaged or like spoil the experiment that is in there. So we have these like infinite life cycle helium traps where we basically have 2 traps in every system, and if one gets clogged, you can switch to the other one, and all the while staying cold, like vent the clogged trap. And that's kind of important, because when someone forgets to top up your nitrogen tank, then your experiment is done, and you do introduce a lot of issues with your fridge. Again, Andrew mentioned like you don't really see the chandelier unless you're trying to fix something in the fridge. We have tried to make it as easy as possible. So in our system, we have like integrated lifts for someone to remove kind of the vacuum chambers when it's necessary. And this really kind of reduces the common pain point that people damage the radiation shields, or when they're kind of removing these vacuum chambers as well. I'll mention briefly, and I'm happy to also dive in deep offline on this point, but we have thought a lot about vibration isolation in the system because a lot of these samples are very sensitive to vibration. So both from a room temperature kind of isolation, we have used mechanical isolators that really help reduce the noise from the exterior world. And these are kind of, the isolators we use are used in optics tables, and so they really significantly reduce kind of external noise in the system without requiring that your facility has like specific kind of location requirements. And I think that's kind of to our point of creating deployable systems. We want to reduce the need of infrastructure, or specially created infrastructure on the user's end. And internally, we have kind of focused on isolating the sample from kind of the noise from the pulse tube, which is, I think, probably the biggest source of noise inside the dilution refrigerator, by hanging the bottom tree plates separately from the top tree plates. And here, this is really coming out of research from CERN. We are in the process of gathering kind of the apples to apples comparison of how much better this performs, but a lot of our customers are super excited about this feature because it really does promise an improvement in kind of vibration isolation, which again comes down to like the qubit fidelity and trying reducing that. So I mentioned earlier kind of doing more with less. Andrew mentioned that a point that I think is very important, which is like as qubit count increases, wiring count increases, how do you support that? And I think some people think about having more cooling power, more pulse tubes, and I think that at some point is necessary, but we also want to do more with the same amount of cooling power. And what we've done here really is to take advantage of cooling power that hasn't necessarily been used by others in the industry. So typically in the dilution refrigerator, you have two plates, like the 50 Kelvin plate and the 4 Kelvin plate. We have added a plate at 9 Kelvin in between these two plates. And the reason we have added that is because there's been research coming out of NIST that shows that there's a lot of excess cooling power at 9 Kelvin that you can take advantage of to thermalize your wires without sacrificing any of the cooling power at 4 Kelvin. And what this means is really that we can support, with the same amount of cooling power, more number of wires. And that's important as you start thinking about like scalable quantum computing. And the other advantage of having that additional 9 Kelvin plate is that you can start transitioning to superconducting quicker, because we use niobium titanium in our systems, wires in our systems like most people do, and the transition point is around 10 Kelvin. The other way we do this is between kind of like the 1 Kelvin or it's like the 0.7 Kelvin plate and the sample plate. There usually is kind of an intermediate cooling plate that for most people exists at 100 to 50 millikelvin. The reason the kind of transition point is there is, I think, it's the natural transition point between the continuous and the discrete heat exchanger. We have kind of moved that intermediate cooling plate from 100 or 50 to 200 millikelvin, and this creates a lot more passive cooling power that you can use in your system. In kind of today's quantum computing applications in dilution refrigerators, electrical signal kind of noise is like something that people are actively concerned about. And really, how you kind of reduce that is by having larger attenuators at higher temperatures, and that creates a lot of like heat dissipation. The difference is that we can support that kind of heat dissipation because you do have 4 to 8 times more cooling power by having kind of the intermediate cooling plate at a higher temperature. What we have then done is that we have done more engineering so that instead of just having kind of continuous plate then discrete, we have a continuous plate, continuous, then discrete heat exchanger. And that's a little bit more engineering on our part, but to make your lives better and to make your lives easier. Again, to this point of doing more of less, with the same amount of cooling power, we can support more number of traces. Because we have these proprietary ribbon cables that we have developed in conjunction with kind of the researchers at UCSB, And these wires have much lower thermal load compared to regular semi-rigid coax. Our system, our 500 microwatt system, can support over 4,000 traces of this, which is really hundreds of qubits when you're thinking about it. And we think that ribbon cables are really the future of the industry. We think ours are a little better because of the technology we use to make them, but this is another part of like the miniaturization that I talked about as the industry grows and scales. So I'm gonna just skip over this, but basically what this means is we have technology that helps make it easier to kind of load high qubit count wiring, and in terms of like wiring space, like our system does have a lot more wiring space because it's square versus I think most pictures you see of the chandelier are circular. Being a square system actually allows us to have better kind of use of the available like wiring space and therefore support kind of more wires for the same amount of cooling power. One thing that we like to joke a little bit about in our company is that this thing is called a dilution refrigerator, but we are the first ones who have added a door to kind of the fridge. We think that the door access makes the sample changes much quicker, and so everyone is thinking about reducing the amount of time it takes to cool down the system, but what we really have, we are also thinking about that, but what we've also focused on is like how do we reduce the amount of time the system stays warm, and so we have really kind of focused on promoting like quick sample exchanges through the fridge's door, and I'm happy to talk more about this in detail, but I know don't have that much time here. In terms of user centricity, I think this is something that as a company is very important to us, thinking about kind of back to the open architecture that Andrew discussed, like having open software that can interact freely with whatever software that you might be using, but also that of our kind of partners as we deliver systems is very important to us. So everything that our entire software program is like open source and therefore compatible kind of with whichever way you like to process the data, but also it makes it easier for us to integrate with kind of our partners. And I want to spend a little bit of time talking about this because I think back to kind of the open architecture that we have heard multiple people talk about, I think this becomes like a very important point as we focus on the future and in terms of what we deliver. So I think traditionally it's been thought like each company in quantum computing is like its own hardware company, and we deliver you hardware and you guys get like take it and integrate it and kind of do your own experiments. As the industry matures, we are really investing, and I think our partners, many of them whom are in the room today, are investing heavily in kind of the interfaces to promote kind of the interoperability so that we can deliver to you a full stack solution. So that when you order something from us, from us and from our partners, we can ensure that everything works well together so that when it arrives on your doorstep, you can start experiments out of the box. And I think this is really important because it does reduce a lot of time to experimentation. And I think if you ask anyone who has tried to integrate a fridge, it easily is a year or 2 years of work. Particularly, I think we are also investing very heavily to make sure those interfaces can support kind of the next generation of hardware as well, and working with our partners to make sure that we move towards kind of a standardization, such as like with your classical computing, kind of the USB-A, USB-C standards. So I'm just going to wrap up here. I think we have really kind of focused on designing for a quantum future in terms of a world where you have many of these systems staying cold for decades and not months. We think that we want to focus on doing more with less, but at some point you need to do more and more. I think that comes to kind of like how we scale, but I think it's important for us to be very smart about the ways we use the cryogenic capacity today and how we think about systems and systems operating together as we think about multiplexing and all of that. This is a nuanced point if you haven't used a dilution refrigerator before, but if you have used a dilution refrigerator before, I think the systems that we're offering are very different from the systems that you're used to today. I like to say that we are really like launching an iPhone in an era of BlackBerries. And we think that it's a new way of thinking and a new way of kind of like interacting with the fridge, and it will take some time to get used to. But as you think about building kind of for the future, it's better to buy an iPhone than to buy a BlackBerry and have to keep it for 10 years. And lastly, we really want to work very closely to cater to your needs, and we are able to offer kind of full stack quantum computing hardware solutions, kind of cater to the needs of you, and we will take the kind of brunt of the work in terms of the integration, in terms of making everything work, so that when it arrives, it's completely functional. You can start your experiments, and that's something that we have dedicated like a lot of time to making sure that it's easy for us to do, but also to make sure that the lives of our customers are easier too. So, and open to any questions. Thank you.
Hello.
Thanks, Ryan. You said that you are supplying full stack systems. So does the customer have the freedom to choose the components of the stack? Can I say that I want a QPU from such and such company, and a control and measurement stack from such and such company, and of course the dilution refrigerator from you, and you integrate it and give it to us? Because as I see that you're not only manufacturing dilution refrigerators, you're acting as a system integrator.
So, yeah, I wouldn't go so far as to say we become a system integrator in some ways, but we are building the interfaces with all of the companies that exist in each of those categories that you talk about, so that if you can choose like what is the combination that you want. Of course, I think with the companies that have further developed kind of integrations with us, then your experience will maybe be a little bit easier, but it's entirely on the customer. I don't think we are saying that we are dictating kind of the stack to the customer. And a part of that is kind of the beauty of the open architecture, right? It's like maybe you want one system with quantum machines and you want one system with Qblocks, and we can deliver two systems, one with each, right? I think that's completely part of the concept that we're trying to focus on here, which is like, how do we make our system and work with our partners to make the lives of our customers easier.
Right. Thank you.
So I just have one question from the financial support perspective. So how much funding, how much percentage of funding did you get from the government? How much did you put on your own? And how much time did you take to come out with this technology?
So I'll share what I can share, which is we have to date received about $5 to $10 million in that range of funding total. We started as a company in 2021, so we have been in stealth for like about a year plus, and then our first systems shipped to customers at the end of this quarter. So we have been a company for about like 2 years now. In terms of government support, we work very closely with the Department of Defense and in the US, and we both have contracts with them for systems, but also we are kind of a recipient of kind of the National Security Innovation Capital Fund from them and also kind of the Colorado government is supporting. So there are multiple different kind of entities that have backed us from the federal government in the US.
Okay. So the concept was actually with you when you went for the funding, or you started from scratch and then after you got the funding?
No, the concept was with us for the funding. The one thing I would say is that I know there's some talk, I heard some talks about kind of building indigenous systems today. As a founder of a DR company, I would not recommend you build your own dilution refrigerator because it is a very complex piece of equipment that we're trying to make easier for everyone else. But yes, my co-founder, Kyle, has been building these quantum dilution refrigerators for decades. So he was originally with Janus, which is one of the original US manufacturers of the dilution refrigerators. Then he was at MIT Lincoln Lab where he was doing a lot of this research, and now he started Mabel with us, yeah.
Okay, so the patent of the technology must be with them, and then you...
Yeah, so we hold a number of patents and have a number of patent pending technologies that are specifically applicable to both our wiring technology, but also kind of the fridge.
Okay.
So what's the turnaround time for you to maybe deliver a system up here if we require it here?
So, sorry.
What is the turnaround time?
Oh, the lead time. So the lead time for us is around 6 months, and we think we can comfortably meet it if the kind of requirements become more complex, and depending on what exactly the system you want is, it may be a little bit longer, and some things like optics and magnets take longer as well, but the basic system is 6 months.
I have a question here. Really nice to listen to your presentation. Whether this cooling system, particularly dilution refrigerations, can be used in a shared service model? I mean, like, can it be built in a shared service so that it can be used for the multiple computer systems?
Do you mean that what do you mean by self-service?
Yeah, I'll tell you my problem statement. I'm actually trying to build up a quantum computing park in Gujarat in India. So I'm trying to build the cooling, trying to look the common cooling aspects also. So whether, how the common utilities should be evolved. Suppose if we are trying to build up some competency center, right? Whether each machine is required it to be separately mounted, or we can have a shared services model. We can have a common cooling facility built up in the competency center.
That's a great question. I think the common cooling facility is the future, in my opinion. When you have different companies who have qubits that are ready to be cooled, then you can imagine having a central facility where an IBM and a Google both have their chips living in dilution refrigerators next to each other because everyone accesses it through the cloud. I think they're and in fact, in Colorado, we're moving to a new facility at the moment, and we are going to offer kind of this what we call a quantum lab facility where anyone can come in to rent time on our fridges and just do their experiments or just put their experiments there and access it remotely through the cloud. The trickiness comes, I think, sometimes when the people doing the experiments need actual access to the hardware, and so it's like if there's a natural point in India where it's close to a lot of the quantum research, then I think such a facility actually does make a lot of sense, because then you are sharing the infrastructure costs and particularly the maintenance of it with a lot of people, and you can have, for example, and this is something that Mabel has been will do in the Colorado facility, but also potentially for other facilities. You have a Mabel technician who operates the lab and makes sure all of the experiments run smoothly, because then you take precious kind of time, you return that to the researcher, because then they can focus on just like doing the experiments and really not worry about installing and cooling and all of that.
Yeah, appreciate your, thank you.
Basically, you are working with defense. The environment is very stringent many places. Does it every place, do they use the same cryogenic based processor, or you have any other solutions for defense?
Sorry, I don't understand your question.
For a defense, you are providing solution to the defense, US defense. Do the cryogenic based systems are working every place, or do you have any other alternative systems for them?
So I think your question is whether our systems for the defense kind of Department of Defense changes from
you can fulfill for a defense requirement completely these solutions, or any alternative solution. That's what I mean to say.
So our systems are designed to kind of be modular, and you can kind of customize to a certain extent. Most of us, like 95% of the systems that we ship are going to look like the systems you see on the screen. There are certain, like some modifications, for example, if you want to do a lot of photonics research and you want optics access ports, we can add that to the fridge. But I think to answer your question is that the system that we're shipping is not going to be that much different from the system we're shipping to our regular customers for defense. The only thing that I would say for defense is that our software system becomes a lot more closed. It's like air-gapped just because of the security requirements. We don't allow, I think they don't allow people to access it remotely as easily in defense. Thank you.
Answer directly.
Thank you so much, Mr. Bryan. Now, I would like to call Mr. Amit Saxena to felicitate Mr. Bryan. Moving on, I would like to call upon Dr. J. Pradhan, Scientist G, Variable Energy Cyclotron Center, Kolkata, to share his views.
Hello. So good afternoon, everybody. Hello. So first of all, thank you to the organizer for letting me to talk about the development of millikelvin technology, relevant to millikelvin technology at VECC Kolkata. This is the dilution refrigerator. We have helium-3, helium-4 dilution refrigerator is a cryogenic device that provides continuous cooling to ultra-low temperature of the order of millikelvin. And this is the cooling power provided by the heat of mixing of the helium-3 and helium-3 isotopes. And continuous refrigeration below about 300 millikelvin with substantial cooling power. There is no magnetic effect. The basic physics is the helium isotopic mixer undergoes phase transition, phase separation when cooled below about 800 millikelvin, giving two phases. These are the basic physics, how the dilution refrigerator works. there is a finite solubility of helium-3 in helium-4 even as the temperature approaches 0 Kelvin. This makes the dilution refrigerator possible. And the heat of mixing, because the specific heat of helium-3 atom is higher than the dilute phase, than in the concentrated phase. Then if the atom goes from the concentrated to the dilute phase, it results to the cooling. And the vapor pressure of helium-3 is very much higher than the helium-4. That's why that circulation is possible. So this property, we can use it to produce millikelvin range. And this is the working principle basically. We have this circulation from then liquid nitrogen cooling it down to liquid helium temperature 4 Kelvin. Then we have a 1K port around 1 Kelvin temperature, and you have a flow impedance and steel with about 600 millikelvin, and there is a heat exchanger, and we have a mixing chamber. These are the basic components of the dilution refrigerator. And we have developed a process simulation design for designing this, dilution refrigerator. This is numerical simulation code SITFO, simulation for integrated dilution refrigerator for optimization, is formulated for design and optimization of dilution refrigerator. This comprehensive code is available for a complete closed system for the design and optimization. This is we have used to conceptualize and design a complete dilution refrigerator system at VECC Kolkata. And we have collected all the property data because we read property data till millikelvin range, and for all concentration and temperatures, for enthalpies, osmotic pressure, molar volume, chemical component. These are all the data are very difficult to compile this millikelvin data. So we have compiled the data scattered in different literature as a part of the work. And we have this publication, thermodynamic process simulation of dilution refrigerator. And we have this transient phenomena, initiating phase transition in dilution refrigerator. This study has not been carried out before, and we have published this. And this is the components of dilution refrigerator. The dilution consists of mainly bath cryostat, dilution insert, pumping system for outer vacuum and inner vacuum chamber, and helium-3 circulation. And we have a dilution insert. The dilution insert basically major component is evaporator, which is 1K pot, and heat exchanger, distillation chamber, and mixing chamber. And this is the dilution setup. We have to VECC. We can see from here that we have this cryostat, gas handling system, GHS. This top plate is showing there. And we have that air spring to reduce the vibration. This circulation pump, internal vacuum chamber pump, and you have the dilution insert inside the cryostat. And you can see here the dilution insert is this IVC. These are all indigenously made. This IVC flange, 1K pot condenser, steel, heat exchanger, and you have a mixing chamber. The dilution refrigerator was successfully built, and temperature down to below 50 millikelvin have been achieved. And this is this top plate. There is a helium evaporator line. This is basically the weight system. We have used the liquid helium. And this is the steel line, and you have a top plate and air spring for reduce the vibration. And we have this is the anatomy of the system. You have IVC, OVC, this dilution insert. There is an IVC which is immersed into the liquid helium, and that liquid helium is surrounded by liquid nitrogen. These are all the steps, standard procedure in cryogenics. And difficulty in realizing dilution refrigerator, what you found is this is a convective instability in dilute side, improper pressure distribution, presence of helium-4 in the concentrated side, improper composition of helium mixer, optimum flow impedance, and residual load. And this is the component of the dilution refrigerator. This is the helium evaporator, 1K pot. This is our, we have made indigenously inside, our indigenously made. And this is, we have reached around 1 Kelvin and continuously. And we have a paper in cryogenics also designed for helium evaporator 1K. And this is the impedance measurement. We have this impedance, very important to control the pressure distribution. And we have in-house developed the measurement system to find out the impedance, because line sizes are very, very small. And this is the steel helium distillation chamber where you distill this helium-3 and helium-4. This is around 600 to 700 millikelvin. You have a small, this volume is 40 cc, 2.5 meter exit path. These are all the things we have. And this is we have the heat exchanger. This is the continuous tube and tube heat exchanger. We have this helically coiled cryogenic heat exchanger made of thin wall, 250 micron German silver capillary tubes with outer diameter, inner diameter, and outer tubes are 3 millimeter and 5 millimeter respectively. This is a very critical component. And we have a mixing chamber finally. which is 10 cc volume, made of OFE copper. And we have used ruthenium oxides, which is calibrated ruthenium oxide 10 millikelvin to 40 Kelvin, which is used, and spray races also we have used. And these are the gas handling systems. Whereas in the room temperature gas handling is very complicated because we have a different process like cleaning, gas cleaning, condensation, normal circulation, which consists of passive, active condensations, and recovery of helium-3 are facility. So, and this is the data equations and control. And we have the in operations, filling of liquid helium, all these things. And we have cooled down the mixing chamber under 4 different steel temperature. This is theoretically that with our code, and we have achieved finally around 40 millikelvin, less than 50 millikelvin around this time. And our conclusion is thermal model for steady state and transient process is formulated. We have this code SIT4. And we have successfully designed, built and tested the technologies relevant to dilution refrigerator. The dilution refrigerator successfully cooled and obtained below 50 millikelvin. This is the publication and thesis. Thank you for your attention.
The house is open for questions, if any.
May I? Yeah. I think out of all the chandeliers we have seen, yours is the most fancy looking one. I'm very happy about that. Yeah. I just wanted to ask you, what was the end use application for this dilution refrigerator? And how will you customize it for use for the quantum computers?
This is basically what we have started is to develop technologies relevant to the dilution refrigerator, millikelvin.
Okay.
We don't have any purpose as such because the system is, we have put the system in IBC inside. There's no, we have not provided any sample. There's no provision to remove and all. We can just demonstrate whether we can achieve it or not, or all the complexity, to know the complexity. And to designing this thermal model, which we have SIT4, the code we have developed.
No,
so basic idea is to develop the technology relevant to the millikelvin technology.
So what I want to ask you is that, if we want to modify it and put those wires which are carrying the RF microwaves and all inside the, and we have a chip placed inside the thing, like we'll have to do a lot of customization and modification.
Yeah, so that increases the residual load.
Yeah.
Because we have this small, I think we have, how much we have 20-30 microwatt power at 100 millikelvin. Very small unit. So we have to redesign it. We have to design it accordingly so that we can.
Very happy that actually such an initiative exists here in our country, and I'm sure you will be able to, in a quick time frame, convert it for use of the superconductor. But have you been approached by any institution where this kind of fabrication of superconducting processes is going on?
No,
maybe TIFR or
something? No.
No. Okay. Yeah, thank you.
Thank you.
So what's the next move?
Actually, this next move we can.
We belong to some R&D institution. So our target is to develop a technology and pass it on to the users. So far we have done the R&D and we have prototyping it. But for application part, there is some refinements needed and customizations required. That is not done in our case.
So what is the team size?
Sorry?
What is the team size of your whole? Yeah.
Actually, with 3 officers, 2 assistants, and 3 technicians is our group.
Excellent, excellent work done. A big round of applause. So I think now is the time to come to the real applications and real people who work together.
You can think of SNSPD development for this is
No. So I think Bark. So this is also part of DAE, right? I mean, Bark is actually having this indigenous quantum computation program, which has started. I think many things have been put together, including cryogenic. I don't know why, because I also am part of Institute of Mathematical Sciences under Department of Atomic Energy, and Bark Mumbai is actually has a full program on that under one of this Bark program of indigenous quantum computing, where they are trying to get. So I was surprised that VLCC and the Bark Mumbai, it's the same department. So because cryogenic, the system which you have can actually be there, they are also trying to build. That's what I heard recently. Last week, we had a meeting in IIT Madras. Ranjan, yes. Yeah? So yeah, Sudhir, yes. Sudhir is heading that project under Bark. No, whole indigenous quantum computing program under Bark, which has been there, but where dilution refrigerator is also part of it. Yeah, so I think, yeah.
That is east and west. One is Calcutta, other is Bombay.
Looking into this, I would like to request C-DAC that after the symposium, they try to do the mapping of existing capabilities of the institutes, and that could be passed on to all those potential beneficiaries so that we do not need not to work in silos and do the reinventing of the wheels. Yeah. So.
Acceleration is the major part. I think so much of work is done. So if we can accelerate the thing, it will be a very good thing to happen, because country needs it.
I think yes, so we have an ideal platform, and I think C-DAC, the purpose of this symposium is to bring together everyone. And in fact, this is the first time I came to know about the dilution refrigerator being developed by you. So I think the scaling up and all the capabilities which are required for any other production, and applications, for some applications. I think that can be looked at by even industry partnership. Yes, that is very important. So for that, I think we can work together, more discussions can be done, and along with C-DAC, or you can come, and I think we'll welcome this move, because this is something which we really require in our country. Yeah. Thank you.
Thank you, sir. Now I request Mr. Amit Saxena to felicitate Dr. Pradhan. Thank you. I also request Colonel Lekinath to felicitate Mr. Amit Saxena, the session chair. Thank you, sir. Now, let us begin with the next session, which focuses on control and measurement electronics and calibration. This session is chaired by Dr. S.D. Sudarshan, ED, C-DAC, Bangalore. I request Dr. Itamar Sivan, Quantum Machines Tel Aviv Yafo, Israel, to toss his ideas regarding the session.
Hey. All right. First of all, I'd like to thank you all for being here. And I'd like to, first and foremost, thank the organizers for inviting me, Nat and Anindita, and the rest of the C-DAC team. So this is great to be here. In fact, it's wonderful to be here in India once again. So thank you for giving me this opportunity. It's been quite some time since I've been here last time. It's been since 2015, in fact, since I've been in India last time, 8 years ago. And then as well, it was for a quantum reason. I was invited back then to give a series of lectures at the HRI, Harish Chandra Research Institute in Allahabad in the winter school. And today, this is 2023. So we're here at C-DAC to have this quantum symposium. And you see that there's one thing missing on the screen, so we have someone to take care of that, so that's wonderful to be here. Now, a lot have changed since 2015, in fact, quite a lot, especially in quantum computing. And what has changed? Basically, in 2015, we had all the, what you would say, the rudimentary, fundamental building blocks working for quantum computers, but we had none really working back then. Okay. Today, in 2023, what we have is actually a first working version of a quantum computer. And people very often ask me, so, do we already have working quantum computers in the world? Right, this is a question I get a lot, all the time. And I always like the analogy to a car because it goes as follows. In fact, we have a working quantum computer. Okay, just like a working car. You can log in today to IBM on Amazon Web Services, you will find a working quantum computer. However, this quantum computer is, excuse me, useless. Okay, to date, quantum computers remain useless. They're still not good enough. So it's as if you had the first car operational. It really drives. It has the wheels, it has the engine, it has everything, but it drives 5 kilometers an hour. So you still better use your old horse or a rickshaw. Okay, not an auto rickshaw even, just a rickshaw. Okay, maybe with the pedals, right? So, however, quantum computers have a big promise. Right? They have a promise for incredible computing power. And this is why, even though they do not work yet, we have so many resources invested into making it work, into realizing the potential of quantum computers. And we see that all across the globe. We see that with universities. We see that with companies developing quantum computers, cloud providers, and HPC providers. Okay, and today we will focus a bit on that because C-DAC is, of course, a leading player in high-performance computing, right? And before we take a deeper dive into that, just a few steps backwards to talk about Quantum Machines, our company. So in a few words, Quantum Machines, who are we? So we are a team of quantum physicists and engineers on a mission to revolutionize quantum control and unlock a new era in quantum computing. Now, at the core of the company, we actually have many quantum physicists that worked on pretty much all quantum platforms out there. We have our Indian representative, Satya Baid. He's actually based in France. However, this is not enough, and we're hiring. So if you know of anyone who could be relevant, we actually hire everywhere in the world. We're not limiting ourselves geographically, and we're very open to hiring in India as well. Now, beyond all the physicists, we actually need a lot of people to have working products. At Quantum Machines, we are already over 140 people. I believe that we are the biggest quantum control company in the world by far, a company that is solely devoted to quantum control. We employ people over 7 countries. We have raised thus far $120 million, most of which is from private funding, over $100 million from private funding and about 20 from government funding in Israel and Europe. We have an M&A strategy, so we have recently acquired a company in Denmark called Qblocks, and this is something that we plan to pursue in the future as well. Most importantly, we have a very large customer base. So we have over 250 customers by now in 23 countries, of course, India included. And we work with universities, HPC centers, some of the biggest enterprises in computing in the world, cloud vendors in general computing, as well as startup companies, mostly in Europe and the US. We have 9 product lines, okay, so this is what we're selling to these folks. And beyond our products, we're also highly involved in large-scale projects. And an example for that I will talk about briefly today is that we got the mandate from the Israeli government to establish the Israeli Quantum Computing Center. Okay, and we're highly involved in such large-scale projects globally. And the question that you may ask is, how did we manage to grow so fast? We started the company only in 2018, right? And it's not just because we work hard, it's due to some fundamental question. It's related to the topic of this session, okay? It's related to the following question, which is, why do we care so much about control and measurement electronics? Okay, so why do we care so much about control and measurement electronics? I will cover this question first at high level, and then I will break it down into smaller questions, because this is a big question, okay? At a high level, let's have a look at it. So at the end of the day, we're interested in quantum systems, quantum devices, right? This is where all the magic is going to happen. This is where the computing power will come from. Right? Now, in order to do anything with a quantum system, what we really need, what we have to have, is an ability to send it pulses and also get pulses from it, right? And in order to do that, we actually need classical systems, okay? In order to operate a quantum system, we need other classical systems, okay? Now, obviously, no institute in the world has an orchestra playing classical music, right? But what we used to use for many, many years is actually the following. So it's what we call general purpose test equipment. So arbitrary waveform generators and lock-ins and digitizers. And these are actually amazing instruments, okay? Great instruments that I also use myself for many years. And they are great. However, they're only great until a certain point. And that is the point that you actually want to run some cutting-edge algorithms and cutting-edge sequences, quantum sequences. And when you want to do that, when you want to make the leap from simple quantum experiments to complex and advanced quantum algorithms, what you will find yourself doing is actually working really hard on repurposing this general purpose test equipment that you would buy, okay? Or otherwise developing the entire thing from scratch, right? And this is why we addressed such a big problem in how we could scale up the company so quickly. Now let me still break this down into more fundamental questions. Again, why do we care about control and measurement electronics so much? Okay, so I'm breaking this down into a few questions. The first is, what span of algorithms can be run? Okay, C-DAC is an HPC organization, so it has users. The question is, how complex will the algorithms, or advanced will the algorithms that the users of C-DAC will be able to run, right? The other question is, how scalable is the infrastructure, right? The control electronics that we place will either limit or unleash, enable scaling up the number of qubits, right? The scale of the quantum processor. The third question is, how fast do sequences and calibrations run? Again, the control system that we place in the infrastructure will either limit or unleash the speed, okay? And this translates in terms of HPC to uptime. Okay, if we spend so much time on calibrations, then basically this comes on the expense of the users, right? Now let me add a tweak to this question. So here we have why do we care about control and measurement electronics, and specifically when setting up a world-class HPC QC infrastructure. So high performance computing coupled to a quantum computing infrastructure, right? That's a bit different, right? And then I'm adding for two questions that one could ask. So the first is, how tightly integrated is the HPC infrastructure that we have here would be coupled to the quantum accelerators that we add to it? How tightly coupled are they? Right? The following question is, how well adopted is the infrastructure to accommodate a diversity of quantum platforms, right? Only today I heard more than discussions about more than one type of qubits, right? So we had superconducting qubits, we had photonics, and so on and so forth, right? And these are all questions that I'd like to kind of give you a small glimpse into. Of course, I won't have enough time to deep dive into even one of them, right? So let's begin with what span of algorithms can be run, okay? So on the face of it, this is actually very simple. So you get Dilfridges, whether it is from Mabel or from the new team emerging in India. You place the qubits within them. Then you place the control electronics above it. These folks, they will have some processors, classical processors, analog front end up to 18 gigahertz, and so on and so forth. And then you connect it to whatever, Ethernet, PCIe, however you choose to connect it, and you let the users program. But the question is whether this is enough, right? I have a big processor, and let's say I have all the channels I need in order to control it. And the answer is that no, because the fact that you have a quantum processor and the control electronics does not mean that your users will be able to run advanced algorithms, right? So what I want to show you is how easy it is with our platform to actually run very simple algorithms, but also very complex, very advanced algorithms, cutting-edge algorithms. I will do this with two examples. One is very familiar to all the quantum experts of you, right? So this is a simple Ramsey. Maybe for some of you this means nothing, but this is a very standard quantum sequence, right? We do it on a daily basis, okay, just to calibrate the frequency of a qubit. And what you can see here is that it's really, you write it as you think about it. It's just 3 loops over parameters of the computer, and then you play 2 pulses to the qubit, you wait some time between them, you measure the qubit, and you do active reset on the qubit. That's it. It's very easy, okay? Very easy here, right? But I also want to show you an advanced example, non-trivial example that I believe no machine allows you to do out of the box, okay? And this is a very advanced example of quantum error correction. This is based on a paper that was published by Amazon Web Services in 2020, in which they proposed some technique for magic state preparation for quantum error correction. And what we did is we took the entire sequence that they published in this paper and we implemented it. Okay, so it didn't take an hour, coding never takes an hour, but it took a week or 2. Okay, so this is one of the most advanced algorithms you can think of running these days in quantum computing, and we have implemented it A to Z. Okay, and it will not just kind of be programmed nicely, but it will actually run on the hardware once you have the hardware, the quantum hardware at hand. Okay, so until now you had to believe me. You had to believe me that I'm saying good things about our company and about our product. So let me just flash one quote from a dear customer of ours, Vijay Rajamani, who already spoke today. It is a pleasure to work with QM, which results in enjoyable interactions. That's great. We're fun people. And a fast pace to getting actual results. The quantum orchestration platform has been easy to use and very powerful, but we're still just scratching the surface of its full capabilities. And this is what I'm talking about, of being able to actually run the most advanced algorithms possible. Now let's move along to the next part, right? So how scalable is the infrastructure? Because if we set up some infrastructure in an HPC today with 25 qubits, the question is, will it be able to accommodate the 250 qubits that we'll have in a few years' time, right? This is the question we should be asking. And I would like to convey to you that if we do this right, then yes, of course. And I would like to do it again with an example of error correction, bit flip code of error correction. Some of you may say I'm obsessed about error correction. I don't disagree. Now, what you do in error correction, you actually take some bit of information, let's say a single bit of information, and you encode it in multiple bits of information, physical bits of information. So here, the blue arrows are supposed to be encoding the same information, so they're supposed to be the same. You can see that the right-hand side one flipped. So this is an error, and we need to figure it out. What we do is, I'm really kind of simplifying it, but what we do is we measure it via its neighbors, neighboring qubits. Okay, so here we employ some operations, we call it controlled knots. Then we measure this red qubit, and it lets us know that the blue qubit flipped, and we correct it. Now, why am I showing you this, this example? Because I want to show you that this is just another example of a quantum error correction sequence that we have implemented, okay? So I want to show you that we didn't cherry pick a single one. I already showed you 2, and we can think of more, right? But specifically, it's all implemented here, and I want to kind of draw your attention to very specific 2 lines of code. So you see here, what I'm doing in these 2 lines of code in square is actually I'm resetting the entire QPU, quantum processing unit. I'm resetting it to 0, okay? But the nice thing is that it doesn't say if I have 5 qubits, 25 qubits, or 250 qubits, right? It will work for regardless of the number of qubits, let's say in the scale of up to 1,000, in the same fashion, right? And it's not just about the software. Software is easy. I know it's not easy, especially not for HPC, but it's easy. Even the hardware will operate it regardless of the number even of boxes that are used. Okay, just like if you have, you know, petaflops or exaflops or whatever, you would want to have the same software operating for all of them, right? So this is what I'm demonstrating here. So this is how scalable this really is. The third question is how fast sequences and calibrations would run. Again, this goes to the uptime of the service, because if we have 3 computers here, we want them to have the highest uptime possible. Now, what I'd like to show you is that actually, in some circumstances, we can get orders of magnitude speedups for different reasons. I won't have time to elaborate on all of them, but this is just an example. So this is from Caltech. So from Oscar Painter's lab at Caltech. So for those who don't know, Oscar Painter is also the head of quantum computing hardware at AWS, Amazon Web Services. And these folks are heavy users of our machines. And what they showed us that with a simple routine, they could save up to 180 factor on what they did previously with their old machines, right? This is on a 10 qubit machine. So we generally speaking, what we do is we do some analysis. We decompose the sequence into its different elements, and then we say how much speed up can we gain on each. And this is the overall runtime that we would then save for the computer and for the users of the quantum computer that is potentially part of the HPC. Now, the fourth question I wanted to raise is how tightly integrated is the HPC infrastructure to the quantum accelerators? Okay, so this is a big question. And I'd like to tell you the following thing. This is not, in my opinion, it's not super obvious. So we'd always talk about integrating quantum computers into HPCs because it is to be expected that the HPC users would want to use quantum computers. But here is another angle on that. In fact, the quantum computers themselves, they need the HPC by their side in order to scale up. Right? In order to get practical quantum computers, we need massive classical computing. And where do you find massive classical computing? In HPC centers, right? So this is actually a necessity, I would say, for scale up, right? So at the end of the day, we will want them to coexist and be part of the same machine. Now, there are many tasks that we will use, we will leverage the HPC power for the quantum computer. So we name here a few: error correction, state preparation, dynamic circuits, pulse optimizations, embedded calibrations. At the bottom is like kind of the use cases, so variational quantum algorithms. So all of these rely on classical processing, right? And at the end of the day, we will have to bake them into complex workflows. Okay, workflows that combine the QPUs and various classical processing units. Okay, moving from one thing to the other, calibration, algorithm, another calibration, and so on and so forth. And this has to be done in a careful design of the quantum classical machine, in which at the end of the day, the QPU will be just another node in the whole system, right? So we've got here the CPUs, the GPUs, and the QPUs, but it's easy to make the slide, right? Just boxes, and I write a letter and then PUs, right? But it's hard to actually make it this way, right? And in fact, just like in any domain of engineering, there is a lot of compromises to be made, and these compromises have to take into account the different time scales of the system, right? Because there are certain things that have to happen very fast, and therefore, I'm not sure this is self-explanatory, so I'll try to explain further. So, where's the cursor? Yeah. So some things have to happen very fast, so they will have to happen here in the box that's directly connected to the quantum processor. Some at the HPC level, right? So this is what we call real time. So for example, dynamic circuits and some of the error correction, state preparation, and so on and so forth. But some is not very, very demanding. So it's still demanding, maybe not in latency, but in bandwidth, right? So we will do it farther from the QPU here at this level. And still there are many, many use cases for that level of computation. And the limiting the limiting timescale between these two regimes is the QPU lifetime. So this is QPU lifetime, for those of you who are not familiar, is, I could say in simple terms, it's how long from the moment I load the data into a QPU until it dies. Okay, very roughly speaking, not getting too technical, right? So then we actually need to design the system, and this is, again, this is not obvious. And one of the things that we've been introducing recently is the idea of taking some of the core actions of the quantum computer, like the hardware-aware software, and moving it from what people define as, okay, the animation doesn't work. So this box of hardware-aware software should be moving to the left. Okay, it should be actually running in the HPC system, right? So this is the vision that we believe in for integrating tightly a quantum processor into an HPC infrastructure. Now, the last question that I'd like to raise, again, a topic for deeper dives, is again, how adopted will the infrastructure be to accommodate a diversity of quantum platforms? So as we're all convinced, superconducting qubits are leaders today in the quantum arena, but actually there is a diverse range of QPUs. Right? And maybe today you would like to set up multiple superconducting qubits quantum processors, but at a later stage, maybe some other type. So we already here see the diversity. These years don't, there's nothing very exact in this axis. They denote just very particular cases. 2013 was the first startup doing superconducting qubits that was founded, and so on and so forth. And no one really knows what will come in the future. And we want to keep the infrastructure to a good extent agnostic to the underlying processing. So this is well integrated in what we call in HPC heterogeneous computing. It could be heterogeneous also relative to the multiple types of quantum processors. So at QM, we focus on bringing out the best of any QPU. So we actually have many, many customers that develop quantum bits based on all different platforms. So here I have a bunch of papers. Each one of them is a completely different realization of qubits. So superconducting qubits, spin qubits, NV centers, nanomechanical resonators, photons, and there are more. Okay, we'll work with ions and atoms and so on and so forth. So going back to who we are, after touching upon all of these many complex questions, so we are quantum machines, and we have many products. I didn't talk about all of them today because it's not a sales pitch. We have multiple products. I'd love to elaborate about each and every one of them with each and every one of you. But we're also very busy helping corporates and national centers to pave the path to useful quantum computers. Right? So as I mentioned in the beginning, we were selected by the Israeli government to set up the Israeli Quantum Computing Center, which I believe will be a world's first service that will span 5 types of platforms, all very tightly integrated. So we will have their superconducting qubits QPU with our partners Quantware, as well as a neutral atoms QPU, a photonics QPU with our partners Orca in the United Kingdom, high performance computing cluster that we will bring into this center, and an open test bed, simply fridges that would be for use of the center's users. Based on that, we will provide a variety of services, so what we call the Quantum Academy, the Quantum Lab, and the Quantum Cloud Services, all that to be established in the coming years. So with that, I'd like to thank you all for your attention.
Thank you, sir. The house is open for the questions, if any.
Yeah, thanks, Tabor. Can I ask you a question? Yeah. Sure. So we are particularly interested in this HPC quantum integration, and I see that your stack is all geared up to do that. I just wanted to ask you, at what level do you do that? The physical layer, or the you have any software above that, or any software stack? And can you do that with any kind of, as you said, agnostic technology?
So quantum computing is emerging, right? So I think that a project at such scale will have to be customized to a good extent, right? So we cannot do it for any type of qubit, we cannot now bring, for example, any number of qubits of any type of qubit, but we can definitely work, one, to bring multiple types of qubits, and two, make the infrastructure to a good extent agnostic to accommodating in the future more types of qubits. Right? So this is one. And for your question about software, I believe, so we are mostly a hardware company, right? And we collaborate with other companies that provide a lot of software. We have a project with a European company to develop software for integrating quantum computers into high-performance computing centers. But in a project at this scale, we can definitely redevelop software as needed based on the needs.
Have you done this integration with any other HPC?
It is a work in progress, yes.
Okay.
Yes, it is work in progress.
So, would it just entail change in the job scheduler and that would be the end of it, or would it entail something else?
Say again?
Would it entail just changes in the job schedulers of an HPC machine, or would it entail...
Changes in? Say again? Sorry?
You have the job scheduler in an HPC machine. So only those jobs meant for the quantum computer will be thrown towards that, and then the measurements received back and then assembled.
So there's more to that. There's more to that because it's not like you can just kind of send jobs now to a QPU because it gets a completely different, it has a different API. Moreover, you need some of the quantum processors calibrations and other processing to run themselves on the HPC. So you need to deploy some elements into the HPC and then also have the QPU integrated into it. So I'm not saying that this is the most complex thing in quantum computing. It's definitely doable, but I don't think it's trivial.
Right, right. So as you say, it's a work in progress. So
it's work in progress.
A lot to learn from that. Yeah.
Yes, we have a couple of projects now ongoing.
Anything published on this in the open domain?
No, but I can disclose privately.
We'll meet offline on that.
Yes.
Thank you.
With pleasure.
Right.
Hi. Will the same control hardware work for different type of qubits?
Yes. So we currently have customers that operate, for example, superconducting qubits, trapped ions, neutral atoms, NV centers, silicon qubits, and other more, I would say, esoteric, unless I forgot something, platforms. Yes. It is actually our almost sheer luck, I would say.
Now you talked about heterogeneity. If I have two different type of qubits in the same system, integrated with HPC, same control hardware will work?
Yes.
Okay.
Yeah. Yeah. That's the idea.
Hello. Hi, I'm Samrit. Quite excited to listen to you. Your approach kind of quite similar to the co-processor computing or early days of accelerator computing. The source code part that you have demonstrated where you are resetting the devices as per your requirement and controlling the whole control systems before resetting the systems also quite exciting, and it gives a glimpse of hybrid HPC and quantum computing. My questions to you is, do you have any real case studies where at minimal level at least you have tweaked the driver part or the kernel part of existing operating system in order to divert the instructions to the quantum processor side?
Great question. So basically, the case studies, the public case studies, we will be able to release them during 2023. These are a work in progress now. We have a couple of them that are ongoing in a good stage.
One more question, please.
Sure.
So, and the software system ecosystems that you have shown today, does it support simulation platform? Which I mean that if you don't simulated platform, that means if you don't have a real quantum computer integrated with the HPC as at this point of a time because of any reason, does the whole software systems also still work in a simulated mode?
So This is not something that we offer. We are not, this is not our expertise to provide quantum simulators. For our customers, we provide a simulator of our classical hardware, okay, which is cycle accurate. But we do not have quantum simulators. This is an expertise by itself, which may even be, maybe there are others experts in that here in C-DAC, but we are not.
One more question, please. How do you explain the transitions between from the bit to qubit and qubit to bit in real-time form? As you have mentioned the term called real-time, the transitions, how it happens, can you explain a little bit more about it? Thank you.
Sure. So the transition, so this is actually quite simple. So this is just sending pulses, electromagnetic pulses, to the qubits. So if I may have, like, let's say, a classical processor in the digital domain, it would send a pulse digitally, then it would be converted with a DAC, right, digital analog converter, and then the pulse will go towards the qubits and hit them, right? When you send the pulse, it is classical. When it hits the qubits, it is quantum. It is regarded as quantum, and each such pulse would represent what you know from the maths of quantum computing, a unitary transformation, which is the quantum operation. I hope that answers the question.
Hello. Yeah. You talk about the HPC-QC interface and the advantage of your approach, but can you touch on the architecture, like whatever is your control electronics architecture, like whether it is FPGA kind of thing where you have a logic fabrics, or it is more towards processors. So means basically to meet the delays, na? Like you said that there is a real-time transaction. So what kind of architecture you have?
So if I understand the question correctly, then the answer is that currently our systems are FPGA based. Our core technology is a processor architecture. This is how we view it. It is a classical processor architecture. And what we do is we take this processor architecture and we embed it on FPGAs, right? So the architecture itself of our processor is obviously, or not obviously, it's proprietary, and it is embedded into FPGAs.
Okay, means basically how do you partition your work? Like basically, do you have any, like you said that some pulse characterization and you have some algorithm. So how do partition among these things?
So our processor is a multi-core processor. So each processor has, to date, I believe 18 cores. Each core can do everything, let's call it. It can generate the pulses that would be sent to the qubits. It can also get signals from the qubits and do heavy classical processing. Then between these cores, there is communication, which is nanosecond timescales, right? And then you also have communication between many such processors. So if you need more than 18 cores, you stack many boxes, one on top of the other. And the communication between two processors is on the order of 100 nanoseconds.
Okay, thank you.
You have mentioned the test bed is one of the solution. Test bed. Do you have ready-made test procedures for to perform the test bed, followed by NIST standards, or you have any other standards adopting in your test bed?
So to the extent of my knowledge, there aren't yet established standards in the field.
Except NIST, I don't think so. Yeah.
Right, so there aren't yet established standards in the field. So so the answer is
some procedure may be there. The NIST procedure, NIST already is there. Some procedure is the test procedure. Do you follow the NIST procedure, or you have one procedure?
So
do you have developed any test procedure for use the test bed, or is open system?
Oh, I see. It's an open system. So you can get a processor. You can either use a processor that we would provide you, for example, might be a quantware processor, or you can bring your own processor in the test bed, if that's what you're asking.
And you make a customize as per user requirement.
So we could do that with Quantware, who are partners of our center.
Okay.
Yes.
You have, do you establish a test facility, test lab anywhere?
Yes, so this is a test bed lab, but again, we do not develop the quantum processors, right? We develop the infrastructure that can accommodate all types of quantum processors, right?
Yeah, I think in the interest of time, I think let's move forward. Thanks a lot. It was a wonderful presentation, and you got many people excited when you said HPC and QC integration. I think Samrit was, and there are many more questions. We can take it offline. Sure. Thank you.
Thank you very much.
Thank you.
Thank you, sir. I now request Dr. S.D. Sudarshan to felicitate Dr. Sivan. Moving on, I request Professor Andrew Briggs, Oxford University and Chair Quantrologs UK, to share his thoughts.
Thank you very much. Well, it's me. So this morning I talked to you. Is this working? Is this working? Yep, yep. Everybody hear me? Anybody who'd prefer not to hear me is welcome to leave. This morning I talked about creating Quantum 2.0, and I want to talk about accelerating Quantum 2.0. And that's going to be achieved by combining the progress that is being made in quantum computing with the progress that is being made in machine learning. And many people ask this, they say, look, if you take the chips in your phone, those chips are designed, and the design is sent to TSMC or whoever, and they make the chips, and the chips come back and they're put in the phone, and the chips keep working stably and reliably for the lifetime of the phone. Could we have a dream that quantum chips would be similarly reproducible and reliable, just like CMOS chips? And it's a wonderful dream, and it's a dream for the foreseeable future. What machine learning enables you to do is to make the quantum chips feel like that to the user, to feel as if they were as stable and reproducible as the CMOS chips in your phone. I don't know if anyone here, hands up anyone who is a sailor. Anyone here who's a sailor in boats? One, two, oh, not so many. Well, that's good. We'll go sailing together one day. If you look at people sailing in a big keelboat yacht, as long as the wind's steady and the sails are set correctly and the helmsman keeps a steady course, the boat is just pretty stable and you don't need to do anything. By contrast, if you try windsurfing, it's not stable by itself. And the windsurfer is constantly having to give feedback to control the sail in order to keep the windsurf upright and sailing correctly. If you watch an expert windsurfer from a distance, they make it look as if the windsurfing is stable, like a big yacht. But it's because they're dynamically controlling it the whole time. And the machine learning that I want to tell you about has this effect. It makes the qubits look as though they're stable and reproducible. and feel to the user like a conventional classical CMOS chip. So let's dive into it a bit. What we want to do is to have machine learning that will take us from the fabricated device all the way through to an optimized qubit. And that can be applied to a whole range of quantum devices, semiconducting devices, ion traps, semiconductor devices, and others too, photonic chips as well. The particular ones that I'm going to talk about today are the workhorse in my laboratory at Oxford, which are double dot qubits, where you want to have one and only one electron in each spin, and the quantum information is encoded according to whether the two spins form a singlet or a triplet state. And we divide the process up into two stages. The first one is trying to get the structure right so that we've got one and only one electron in each dot. And then the second stage is optimizing that for the sort of parameters that you care about for quantum information processing. So here's a semiconductor device. It's highly stylized, but you can think of two electron spins, and we're going to determine whether they're in a singlet or a triplet state. And in this highly stylized picture, you've only got three different parameters under your control: the bias voltage and two gate voltages. In fact, you actually have about 8 different voltages under your control, because you've got 3 tunneling barriers that you're trying to control as well. And that's just for one qubit. And of course, you want to scale this up to a much larger number of qubits. And what you're trying to do to start with is to get this into a regime where you've got one and only one electron in each dot, with the right amount of coupling that you can embody the quantum information in a singlet or a triplet state, and then good behavior so that in step 5 in that diagram, you can optimize the Rabi oscillations so that you get the maximum number of operations you can perform within the coherence time of the qubit. And when you want going to extend this to a large number of qubits, what you then want to have is a map that shows how you're tuning it up, and once you've tuned it up, you can see that it's stable and the whole thing is good to go and good to continue going. This is a picture from the user interface of the Qblocks software, which I'll come to right at the end. But most of what I'm going to tell you about now is the science that we've done in my laboratory at Oxford. And then right at the end, I'll tell you how it can be more widely available. Now, lots of people automate the tuning, or sometimes it's called the calibration of qubits. Here are just some of the publications that have been made. But I want you to get the idea that there is a whole range of different degrees of automation. So if we have a simple thermostat controlling the air conditioning in this room, basically that's got one input, which is what's the temperature of the room, and how does that compare with the temperature that's been set by the user, and one output, which is turning the air conditioning on or off. That's the sort of simplest kind of automation that you can have. If you're trying to control temperatures in an experiment in the lab, you'd use a more sophisticated kind of temperature control system, probably a PID control system. So there are degrees of automation, and there are increasing degrees of sophistication all the way through to the most advanced machine learning techniques at our disposal and beyond. And if you look at those papers that are up there, they all say that they're doing automation, but there are different points across that scale of automation. And what I'm talking about is the real cutting edge, using the most advanced, well, combinations of the most advanced machine learning techniques that there are. So where are we at? Well, we can divide this up into different stages where, first of all, you're just trying to get the feel of the device and where the probable combinations of gate potentials are in order to get it to behave like a qubit. And then right at the end, you're trying to optimize it. And there's no one technique called machine learning. Machine learning is a whole discipline with a whole range of techniques in it. And as we've sort of shown diagrammatically there, to start with, we use machine learning techniques that are not deep learning, things like Bayesian optimization and Gaussian processors. And then for some of the stages, we use deep learning techniques, and then actually we come back to the Bayes-Opt kind of techniques. And the changes that are taking place in machine learning are that the early deep neural networks thrived on data that were plentiful and cheap and were excellent at classification. And the sort of moves that are taking place and that we're harnessing here are the move to techniques that work well with data that is sparse and costly to acquire, and where the machine is not simply classifying, but is deciding what the settings in the experiment or in the device should be next. And roughly speaking, in looking at this, even for the single qubit, we're in sort of 8-dimensional space. And roughly speaking, for each of those dimensions, the working place is about 1,000th of the total range. So we're trying to find a volume in hyperspace that's 1,000th of 1,000th of 1,000th of in other words, 1/10 to the 24, if we've got 8 different voltages. So we start off, and I can only represent it in 3D here, but think of it really as being in 8 dimensions, as some sort of guess as to what the hypersurface might be, and we're particularly looking for the hypersurface that marks, on the one hand, you've got lots of electrons in each dot, so the thing just conducts all the time. And on the other hand, you've got no electrons, so it's complete no current flowing at all. We're trying to get the range where there's the current that flows depends on the quantum states. So we make a guess, and then we do some Bayesian optimization, which is basically saying, where should we make the next measurement for the maximum gain in information? And that's what that little animation is illustrating there. So the Bayes-Opt decides where to measure the next data points. In the light of that, it revises the hypersurface, and then it makes some more data measurements, again following the Bayes-Opt. So one of the things that we can do is to use this not only for tuning devices, but also for characterizing them. So there's a big speed up in characterization. Here are 2 devices. Actually, it was the same device, but it was thermally cycled, so you get a movement of the trapped charges, so it behaves differently. And in the little animation there, the red was the first device, and the blue was the second device after the thermal cycling. And then what we try to do is to say what matrix will map that second device onto the first one, because that tells us about device variability. There's the matrix. And you can see that in this particular case, it could be different, but in this particular case, the matrix is diagonal, which indicates that what we've sort of done is to scale one device onto the other, but with rather similar properties. But it could be different from that. And we've extended that study of device variability to various other silicon germanium devices. And we did an experiment on 3 different geometries of silicon germanium devices, each of them double dot, but as you can see, one's a FinFET, one's a heterostructured nanowire, and the third one is simple gate-defined quantum dots. And then we gave ourselves a constraint, which was we wanted to see whether the machine could learn how to tune these different devices without being reprogrammed at all. So we said we're not going to touch the algorithm. We're just going to get it to learn on each kind of device and see how well it can do. And the answer is it did extremely well indeed. And if you look at the tables at the bottom, we can compare the tuning times of the algorithm from a random search. In fact, you could also ask people who are experienced at doing this how long they would take to do the tuning. And it was fastest of all on the germanium silicon nanowire. The one that it found most difficult was the silicon germanium heterostructure. But in each case, it was actually rather faster than a benchmarked experienced graduate student. One of the things that is an advance in the field is what's called, sometimes called physics-aware machine learning. And that's where we put into the machine the best model that we know how of the physics. And here's some examples where we're looking at supercoarse tuning, where we fed into the machine the basic structure of the device and the electrostatic fields, and we're letting the machine learn where the impurity atoms must be that are causing fluctuations in the potential that cause it to depart from what would otherwise be a perfect design. And again, the machine is rather good at this, and the physics aware enables you to accelerate the learning process. It also enables you to build simulators, which are very good for training the machine learning, also actually for device development. So here's an example of the supercoarse tuning that's led by the model. And we compared the number of successes where it used posterior samples with the number of successes of instances using random disorders. And you can see that there's a significant improvement from 28% success to 67% success in this experiment. So I'm going to skip stages 2 and 3, but there have been some very important advances in the application of machine learning for those stages. So stage 4 is refining it, and for this we do use a deep neural network. And what we're using here is a deep neural network that compares the characterization that we're looking for with what you actually get from the sample. So if you can imagine you've got a deep neural network, and using conventional deep neural networks, you're taking it down to deeper and deeper levels. What it does right down at the bottom is it tries to reduce the distance between the target specification and the actual parameters that you've got. And then by minimizing those, it tunes up the device and does this stage of fine-tuning. So here's a sequence. I'll just go back and show you again. There's a sequence of it running through that, and those pictures are shown at the bottom there. And what you're looking for is the picture of the 2 nice triangles, because that shows you you've got a nice double dot structure. And actually, we can extend that to the final stage of looking for something that's essential in these singlet triplet qubit devices, which is being able to detect Pauli spin blockade when you've got a triplet rather than a singlet. So that's how you're going to do the readout of the qubit. So here we are nicely tuning up for Pauli spin blockade, and here are lots of results. And again, here you can see the success rate according to the different kinds of learning that we put in. So the blue shows you the success rate when it learned only from simulated data. The orange shows you the success rate when it learned from only experimental data. And the green shows you the success rate when it learned from a combination of the two. And you can see with the success results on the left, where there were Pauli spin blockade, well, you do best of all with the green, but actually in many cases, each of the 3 gives you pretty good results. And then here finally is tuning the system up for optimum Rabi oscillations, as illustrated by that bottom curve there. And here it shows you the iterations along the horizontal axis and the optimum frequency that was found against the map on the right. So forgive me, I've gone very, very fast through that because time is short. You can imagine I'd love to talk for hours about each of those results, and I'll be very happy to answer questions on them. Now, this was work that was developed in my laboratory starting in 2015, where the advisory board, we had a meeting and we were saying, look, these experiments are getting so difficult. How do we use machine learning to accelerate the experiments? And with the help of the advisory board, we developed a program in that. By about 2020, by the start of the lockdown, these methods were in use in 5 laboratories, including ours at Oxford, around the world. These were just academic collaborators who learned about our methods, realized that they needed them too, and asked us to help them implement the methods in their laboratories. And because we're academics and we like collaborating and we like being helpful and helping people, we very much enjoyed gaining experience as to how the methods were so transferable that they could be used in different laboratories, in different systems, with different kinds of qubits. And the reason that's possible is in the word learning. It's machine learning. So whereas hitherto one programmed the computer to undertake a task, what we're doing here is programming the computer to learn how to do the task. And that's why it's so versatile and it can learn how to work in different laboratories. Well, here's the team in the university laboratory that contributed to these results. And you can think there's been sort of 30 or 40 person years of pretty impressive students and postdocs who've been working on this. So there's a big investment in the development of it. But we got to the point where we'd reached the limit of our capacity to be able to help people just because we're academics and we like helping people. And so with 2 of the people in this team, Natalia Ares, who heads up the laboratory, and on the right, Dominic Lennon, who was the first of our students to graduate in developing these techniques, we set up a company that was there to meet the appetite of other academics, yes, but also of commercial users who wanted to be able to harness these techniques to accelerate their own developments of quantum computing and the deployment of quantum computing. And the first product of the company is Quantum H 1.0. There'll be a preview of it at the APS March meeting in Las Vegas, and the product will be released probably in the second half of this year. And what's the point of all this? Well, the point of it is to go back to where I started, that we'd all love to have quantum chips that just behave like a classical CMOS integrated circuit. You design it, you make it, it behaves as you designed, and it keeps behaving as you designed 100% of the time for the lifetime of the product. And what the machine learning will do is it'll enable the quantum computing experience to feel like that, because the machine is stabilized, is tuning, if you like, calibrating and keeping the qubit, the quantum chip, calibrated. Thanks so much.
Thank you, sir. The house is open for the questions, if any.
Everyone is stunned into silence.
Calibration is a very big task compared to even tuning. How do you do it, calibration for your equipment? Calibration.
Well, if you define calibration for me, I think I'm separating it into tuning and characterization. Does that answer your question, or is there a deeper question that lies behind what you're asking?
No, the whatever calibration, how do you do calibration for your equipment?
Sorry?
Calibration, how will you do calibration?
Well, are you happy with the way I separated calibration into tuning and characterization? or not? Are you asking a different question?
And the calibration of the equipment I'm asking. How do you do calibration of the equipment? This is a big challenge.
I'm not sure that I fully understood your question, because what I've been trying to explain is how the machine learns how to do the calibration, both the tuning and the characterization. And we don't program the machine to do it, we program the machine to learn how to do it, using these different machine learning techniques, each of which is carefully chosen for the particular stage in the calibration.
I think probably what he meant is that, benchmark it against another machine, but what he is saying is that, you make it learn to produce the result, expected result. So that's what you're doing, right?
Well, with any machine learning, thanks for the clarification, with any machine learning, you have to set the score function. You have to say, what are we trying to do, and what's our criterion for achieving that? And I glossed over this, but particularly in the early days, we used to spend as much time working at the score function as we spent working at the machine learning techniques, because it's a very hard question, a very important question. So you really have to tell the machine what it is that you want optimized. Okay, so it could be the number of Rabi oscillations, it could be the duration of the Rabi oscillations, the number of operations you could do before they decay too much. It could be the T2 time of the qubit, the phase coherence time. Increasingly now it's the fidelity. But even then you have to specify, well, the fidelity of what? Is it the fidelity of the readout or the fidelity of a single qubit operation, or increasingly people are looking at the fidelity of a 2-qubit gate as a benchmark of success. So a lot of thought goes into the design of the score function, and at the end of the day that has to be something interactive with the user.
One last question, I think, if you don't mind. When you say tuning the qubit, you mean to say keeping it in the coherent state, or that is dependent on something else?
Well, again, it depends on the score function. So the first thing, if it's a double quantum dot, the first thing is you want to keep it so there's one and only one electron in each of the two quantum dots. It would be a different criteria for a superconducting qubit, because they work differently. But again, as you get more advanced in this, you might be wanting to keep the fidelity of 2-qubit operations high. So that might be something that you're seeking to achieve. In fact, it almost certainly is something you want to achieve.
Hello, and thank you very much for a very interesting session on this. Just for my clarification, I just want to know, I think you're using reinforcement learning primarily for
yes, we
teaching
do
the
use
machine.
reinforcement learning.
Yeah, because you are defining the functions,
yes,
and you want to make machine learn to optimize for.
Yes, yes.
So primarily reinforcement, and you designed and optimized the reward functions accordingly. And is it so?
That's right. Yeah. But within that, there are different techniques that we use for different stages in the process.
Yeah, stage-wise. Yeah.
So in the middle stage, we used deep reinforcement learning, whereas at the start and the end, we're using, well, Gaussian processors, but more a kind of Bayesian optimization.
Thank you for clarification.
Thank you so much, sir. Your words were very enlightening. Now I request Dr. Niels Bultink, co-founder and CEO Qblocks, Randstad, Netherlands, to share his ideas.
Much for your introduction. Also, thank you everyone. It's already a long day, many talks, a lot of information, but I'm standing here in front of you, and I'll try to be as to the point and direct as possible as we also build our technology. So, let's go. This should be here. So, I'm going to be talking about high-performance computer integrated control stacks towards quantum advantage. And that's what we built at Qblocks. So what does Qblocks do? We are a bit like quantum machines, also in the intermediate layer between, on the left side, the user, and on the right side, the quantum chip. So our primary goal in its most simple and abstract form is to translate programming languages like quantum assembly, the most elementary operations on a quantum bit, into the electrical pulses that hit the qubits in a pure and fast way as we can do it. Okay, and I really like the front page of this conference. You've chosen an embodiment of the idea of open architecture in a way that I have not done yet, and I've been working on this topic already for a few years. So the reasons why I like it is it's these Lego blocks, and what you can see is these are blocks that are not transparent necessarily, but the way they connect to each other are very open. And that is precisely open architecture. Like open source would be even transparent blocks, but here you have blocks where you can work on a block of intellectual property, on a block of technology, and connect that in a well-defined interfaced way to other ecosystem players. And that is what we at Qblocks have always been about. So we were founded in 2019, in that sense, the youngest player in the control stack ecosystem. And we have always found ourselves surrounded by great ecosystem players, and have always cherished bringing others to fruition. So you can think of other smaller companies like ourselves, like Controlox, Blueforce, Orange Quantum Systems, Delft Circuits working on cryogenic cabling, but also big corporates like Intel, Microsoft, who are in the Netherlands as well on campus, and also the bigger governmental institutes, TNO, TU Delft, that are big partners for us. A bit about the company itself. We are currently actually a bit over 60 people already. This was our last end of summer barbecue. The Netherlands doesn't have the weather of India, so here it could be today, but for us this is really peak August, September. And we have a customer base or a partner base around the world of now more than 80 labs, and that's really growing very fast. And another big important step for us is that we recently got our own independent building where we will also be hosting our own independent full stack experiments. So that's a really great step for us. And that helps us in creating scalable control stacks that enable useful quantum computing. It was already mentioned where we are, but I can maybe substantiate the statement a bit more with numbers. So if you take the state of affairs right now in quantum computing, we find ourselves roughly on the bottom left under this logo, which means tens of qubits with about 1% error rate in the qubits. And if you look at going to practical applications, you can think of two forms. The first is the noisy intermediate scale era, and it means a little bit more qubits, but a lot better error rates. And that's one direction that will lead to first application, but we also believe that the real economic value lies in fault-tolerant quantum computing. And that will take also a lot better error rates, but especially the scaling up is really by a few orders of magnitude before it starts to become fun. So that is what we are doing in this control stack domain. And I'm going to be talking about the challenges for scaling up quantum chips to begin with. So that's number one, to get from this lower left corner just diagonally into the right. Then the specific challenges for NISC that also ties in with high-performance quantum computing a lot, or high-performance computing. And talk a bit about fault-tolerant quantum computing, and not just at the scale of 5 qubits, but at the scale of thousands qubits. So let's get started with scalable qubit tuning. So what do you need to start with quantum computing, to start building systems at the scale that we now have available around us? So first of all, you need modular and integrated hardware to package all this. Typically, labs look like many different devices tied together to each other. So we put this all in one modular integrated system. Then we have our own processor technology, our own processor architecture, classical architecture, to drive many qubits in a parallel and fast fashion. And then there's a lot to say about analog excellence. That's where qubits are really different from bits. They are analog to begin with, so precise and stable control is really necessary. So let's dive into modular and integrated hardware. That's what we do with this modular system. As you can see, this is our main product, the cluster. So it's not just one monolithic box, it's a box with slots. And in these slots, you can load now 4 flavors of modules, what we have there. And for some quantum hardware, you need different configurations for spins or for superconducting qubits. So the type of platform you're working on will dictate the configuration with the different modules. To give 2 examples of this, so it seems my laptop is a bit jammed. Yes, there we go. So first example is for superconducting qubits. You see here that for controlling 4 superconducting qubits, you need about 4 modules on the left side. So a 4-qubit processor is just a quarter of this box or a fifth of this box. And you can also feel already like a 20-qubit processor can be all driven from this one device. Similarly, can the story for quantum dots, but then the configuration is slightly different because of the different control needs. But we can do it in a similar density, similar fashion. We also do this. Okay, so what's inside of these modules? What is this classical processing architecture that you need to drive these qubits? So there are a couple of features that qubits have why you need such different processors. You cannot just use an ARM core or a GPU to control quantum devices. And that is because the timing needs to be extremely precise and it needs to be deterministic. The sequences of actions needs to be very predictable, down to the nanosecond, and normal processors are not capable of that. That is why we set out to develop our own processors. But this processor is at the same time Turing complete, so you can do any type of calculations with it, multiplications, jumps, branches. And the other quantum specific thing is the synchronicity. So we have many cores running in our devices, up to 120 now in one device. And these all run synchronously down to the nanoseconds. That's again this timing constraint. And then there are some other properties that have to do with the fact that you need analog pulses in a quantum computer. So you're not sequencing NOT gates like a logical operation. You're sequencing pulses, and these pulses are generated by these cores as well. These are fully configurable, fully tunable, and you can do that in a fast way. So now a bit more on how do we make these modules work together, because it's a modular system and modularity brings also challenges. And we can do that in the cluster, as I said, with up to 120 cores. You can see it here in the picture on the right side. There's a bit of an artist impression where you see that the quantum chip in this case has up to 80 combination of inputs and outputs. In this case, it's a bit more outputs than inputs, but that depends on the modules. And here you see how the information flowing out of the quantum chip is shared to all of the other sequencer cores. So this is really a massive logistics thing going on in the back of these devices to make this information flow from one readout module to all of the other modules in the system, so that all the control can be arbitrarily, with arbitrary logical flows. And this happens in just 320 nanoseconds, so this is really fast compared to anything related to normal processors. You can think, for instance, a simple use case is to do parallel qubit reset on all of the qubits at the same time. Yes. So let's continue with the presentation, if it wants to. It's not having its best day. Let me just try to do it like this, it's maybe easier. Okay, so why do we need these fast processors? It's to speed up the calibrations. And ultimately the running of NISQ algorithms. If you take a look at these simple calibration procedures where you're trying to find qubits, you're trying to create 2-qubit gates, you need a lot of these tuning procedures. And here we show that we can speed up such a tuning procedure from 1.5 hours in a conventional setting to just 13 seconds. So this is really a day and night difference from a lunch break to just 13 seconds checking your phone. So that's really day and night type of differences we achieve. Similar example here for quantum dots, but that's maybe too detailed. The topic of noise and drift. That is very important, especially as the system scales up. So how do you push these gate fidelities further and further towards these applications? It is because the qubits become better, but also the pulses that you drive the qubits with need to grow along, and they need to be very precise. And that's what we do with our very low noise outputs of our system. And then the second big topic is drift. So it was already mentioned this by Professor Andrew Briggs about, what was your analogy? Yes. Yeah, your harp, yes. We have harps. But actually the control stack makes it very harpy. So by building a better control stack, it becomes more and more like a piano. And that's what we're doing. So here we're achieving drift in these control stacks that are comparable to the best DC equipment that you can get that has been developed. It's detailed, it's technical detail, but that's necessary if you want to build a great stack. So I'm just giving you a flavor of this. Then there's about the tuning up of the system and how to compile abstract notions of quantum systems towards the actual pulses. And we have opened up this compilation process. So there's, our customers can fully engage in this process. They can build their own compilers. We have opened up our own assembly language of our devices as well. So this is a very transparent side of our company where the Lego block is a bit more transparent than closed. Yes, okay, now let's talk about the more bigger, hairy, audacious goals. Let's start with NISQ. So what makes NISQ algorithms so hard to do? It has to do with the control stack again. So here you see this flow from high level to low level. And where the NISQ problems lie is in this upper translation. So going from the software part of the stack towards the hardware. And there you have actually milliseconds. I'll show you in a second why. So you have milliseconds, so you can use these milliseconds to employ the best possible resources. And these are HPC computers, because you have milliseconds, so you can afford to go back and forth to your system. So why do you have milliseconds? So this is an example of a typical NISQ algorithm. They actually almost, from an abstract sense, look the same. This is a Kawa optimization, where you interleave quantum circuits with classical optimizers. And what gives you these milliseconds? That lies in the fact that the circuit that you execute has to be repeated for thousands and thousands of times to build up statistics. And only after building up statistics, you go through the loop of optimization. And that is where you get some milliseconds to do calculations. So we have benchmarked our own stack to see where do we stand. Where do we stand compared to an IBM stack? And where can we improve? And the good news for us is we're quite fast. We can do many iterations of a NISQ algorithm in a second. And this is fast if you compare it to an IBM stack, which takes minutes for these type of things. But the bad news is this is about a factor 100 away from reaching the speed limit. So in this loop, we're still spending 98% of our time in classical optimizations and only 2% of the time in the quantum circuit. And that's where we need HPC resources to speed this up. So we provide the infrastructure for this, where we create a very fast lane using the best HPC standards to connect to clusters of HPC clusters, and we connect them very directly down to the very modules of our system. And that's something we can do because we can open up this part of the stack as well. So we give our users really deep down control of the system. And this makes these HPC NISC type of applications very improve a lot. Okay, now the even hairier goal of fault-tolerant quantum computing. Quantum error correction has been mentioned, and it has been mentioned also that it needs to happen on an extremely fast timescale. And the reason for this timescale has all to do with the fact that you need to do many quantum error correction cycles within the lifetime of the qubit. So if you're taking a transmon qubit or a quantum dot, these just lives for tens of microseconds. So if you want to be at 1% of this lifetime for quantum error correction, you're talking about hundreds of nanoseconds. So this is very demanding, and you don't have to think of going back and forth to HPC stack, because already by the time you're on a PCI Express protocol, you're a microsecond away. So then it's game over. So we need to do something new, something much cleverer, and that is where we step in and create this sort of control flow, where within the cluster we can gather the quantum error correction measurements in a central point, and on the central point you can do error decoding algorithms. So this is the architecture that runs now in our device at the level of 20 quantum bits. That is nice. That is good for the most advanced implementations that are out there right now. So we're pushing forward the field, but this will not take long, because we want to go to hundreds and thousands of qubits. And that's why we are already very far in the technology of combining not just the results of 20 qubits, but the results of 1600 qubits into one bucket. And that translation, so combining all these measurement results, computing, and then sending them back to all the modules, that happens still in this time frame of 400, 500 nanoseconds. So that's where we really make this very difficult task of error correction actually pretty close by, at the level of 1,000 qubits. Okay, so that was the content of my talk. So I hope to let you appreciate the difficulties in the control stack when it comes to getting to actual applications. So we do this in many quantum devices. We have key projects in quantum error correction, largely funded by the European Union and also the US government. Then we work on quantum networks in metropolitan scale, so tens of kilometers creating networks. And we have a big project in HPC integration. So thank you very much. I hope I've helped you in your journey, and I also hope you can help me in my journey. So let's build an ecosystem together, and I'd like to open the floor for questions.
Yeah, thanks, Niels. I would like to just take you back to your graph where you shown that NISC versus fault-tolerant comparison.
Yes. Yeah, here's one, yes.
Oh, I think it's not displayed there. Yeah.
Oh, yes.
Yeah.
This one?
Yeah, this one. Now, if you have clusters of these NISC, which is lesser qubits, but if you have clusters vis-a-vis one big computer which is having hundreds of qubits of these fault-tolerant qubits with higher error rates, would that cluster be able to perform better as far as the overall performance is concerned? Definitely it will have higher fidelity. But if you have clusters where, let's say, the the different components are located slightly away from each other. Does it perform well? As far as the performance is concerned, I mean, maybe Andrew or anybody can answer that.
Yes, so when I'm talking about solving NISQ applications in this paradigm, I'm talking about one monolithic quantum processor. And that's still very achievable with tens to hundreds of qubits. So to have one array, two-dimensional array of quantum bits. And when you think of going bigger, for some technologies, it will be necessary to cluster the quantum devices as well. That's not part of our architecture necessarily, but we fully support that, or our hardware already supports that. But making these modular quantum devices work well, that is mostly on the quantum hardware to solve. So companies like Quantware or Pascal, IQM would...
Maybe I think, can I deflect that question to Andrew?
Yes.
What's your question? The question is that, let's say I have 20 qubit NISQ computer. I make a cluster of 4 of such devices, or maybe 5 totaling to 100, and they may be located slightly away from each other, vis-a-vis 100 qubit fault tolerant, which is giving a better performance. And if those 20 qubit devices are located slightly away from each other, is the performance degraded in any way depending on the geographical location?
I think this is a wonderful question. I think it's a major topic of investigation and of policy at the moment. And I suppose in the terms that you formulated the question, the 100 qubit with fault-tolerant error correction would be better, I suppose. But actually, I don't think that is the choice. And I think that you get the best results if you have the small nodes have error correction built into them. So they may be small nodes with a limited number of qubits, capable of only limited quantum operations. They've got to be able to do entanglement, for example, and are capable of fault-tolerant error correction within the small nodes. And then what you do is take a large number of such nodes and connect them together. And the result that was slightly surprising to me when we first, a colleague first derived it at Oxford, is that provided the individual nodes are of very high quality with error correction, the connections between them do not need to be of such high quality. So you can accept quite a lot of noise in the connections between the nodes, which I suppose means that in principle they could be separated by quite large distances, though in practice you may want to have them co-located. And the test for that is what Barry was hinting at for fault tolerance this morning. That is to say, supposing you have a certain number of such nodes with certain levels of error, and you get a certain fidelity. And now you make the network bigger, but with the same parameters for each node and the same parameters for each connection. Does it get better or does it get worse? If it gets worse, then it's not scalable. If it gets better as you get bigger, then it is scalable. And in a particular simulation that was done using parameters that at the time were what could be achieved experimentally in ion traps in the Oxford ion trap laboratory, it turned out that the fidelity of the connections needed only to be about 83% in that particular simulation. And provided the connection fidelity was higher than that, then it was scalable in the sense that the bigger you made it, the better it became.
Rather than one single big cluster, big machine.
Yeah. But
compared to that.
Well, the calculation, that particular study didn't compare it with one big machine. It was more looking at the feasibility for having scalability of this idea of nodes that were connected, interconnected. Now that was several years ago that that was done, and I'm fascinated to see that the IBM policy, recently announced, is to go in that sort of direction.
Yeah. But I think for general and in computation, for computational purposes, you want to have as many qubits as well connected possible. Because if you have some, for computation purposes, poor connections quickly cancel the whole benefit of scaling. But when building quantum networks, really for communication purposes, and in the long run, connecting different computers, real computers at a distance, there they are really focusing on these long distance links, and there you can suffer quite some performance. But if you want to do NISQ algorithms or like next stage quantum error correction, up to 1,000 qubits or that era, I would like to keep them as close by to each other as possible, because otherwise you suffer a lot of performance degradation. That's,
Sure, thanks. Thank you.
Okay, thank you very much.
Thank you so much, sir. Now I request Dr. S.D. Sudarshan to felicitate Dr. Niels. Thank you, sir. Now we will take a quick tea break of 5 minutes and then resume the session.
Should I just disconnect this one?
Good evening. Welcome back. As you all know, we have a wonderful session from morning by eminent speakers. We appreciate your participation. Now we continue with the earlier discussion. For this, I request Dr. Sadiq Hafizovic, CEO and co-founder, Zurich Instrument Limited, Switzerland, to share his views. He is connected with us virtually.
Hello? Hello? Sadiq, you're on mute. You're on mute.
Okay.
Yeah.
Hello, this is Sadiq from Zurich Instruments. I'm not quite sure if if you can already hear me in the auditorium.
We are able to hear you.
Aha.
You can start now.
Oh, yeah. Okay. Yeah, very happy to be able to join you remotely, albeit from Switzerland. Unfortunately, I was not able to come with my colleague Andreas, who you might have already met at the symposium, but I'm more than happy to be able to participate like this. So I am the CEO and co-founder of Zurich Instruments. It's a company that I co-started in 2008. At that time, we introduced a new generation of lock-in amplifiers to the world of research. Today, we are more than 150 people worldwide, very international, more than 20 nations. We have offices in various countries and partners in various others. For example, in India, we work with VT Vacuum, whom you might have also met at the meeting. I believe Nishant is there and Praveen too. Since 2021, 2 years ago, we are part of Rohde & Schwarz. Rohde & Schwarz is a much bigger company, and with the backing of that company, both technologically but also financially, we see ourselves well put up for for further strong growth and challenges. So what do? We have a quantum mission, and that is we want to help build the quantum computer and be the leading quantum computing control system provider in the world. We're doing this already for quite a while. We started in 2014, where at that time, quantum computing was still in its infancy. We used our single boxes and we were the first ones actually to program them in a way that is application specific to quantum computing. Soon after, in 2018, we had our first generation 1 system complete. And today we're at generation 2. And of course, we don't stop here. After generation 2 will come generation 3 and so on. But what's really important here is that through the times, we have always maintained full compatibility so that all investments in the previous generations can also be used in following generations. Generation 2, what is hot and new about the second generation? Well, we have further integrated the system. We have gotten rid of all mixer calibrations because there is no more IQ mixing. This makes the system more stable, less calibration required. We've improved all the analog specs, but we've also included the digital horsepower in the system. Also, we've added a strong software layer. We call it Lab1Q, Lab1 Quantum, which is a programming language that abstracts away the instruments. And you're programming much closer to the qubits. I'll have some examples for this further down the road. And also, what's really important, quantum computing is really a performance game. A performance game in the sense that as the quantum computers grow and you get more qubits, the calibration and bring up methods, they become way more complicated, and the error correction also becomes way more complicated, so that the performance of the classical system becomes more and more crucial. The most recent addition to the second generation is this hardware, a piece of hardware. It's a control system for the parametric amplifiers in the fridges that amplify the readout signals from the qubits on a quantum limited performance. And we're the only and the first company to offer such a system. And it's an example where we help the quantum community at all different levels of the stack to overcome and reduce the entry barrier. Because of course it's possible to build something in a lab, but it's saving a lot of time and improving the quality if an off-the-shelf solution can be used. Yes, so we look at all different scale levels at Zurich Instruments. There are smaller systems with 1, 2, 3, 4 qubits, and those systems here a lot is experimenting, is characterization, performance and flexibility are key here. A lot of interesting science is happening here, and as an example here I have a spin qubit, so that's also a technology that lies very close to our heart. Then when we go the next level, and we're now talking maybe 20 to 200 qubits, this is where today a lot of action is going on. And as an example here, I have the Surface 17 chip from ETH Zurich, Andreas Wallraff, but also the Berkeley Lab testbed setup. Here, additional topics are added. Feedback for rapid initialization and quantum error correction become a topic. So this is added to the requirements of the small systems. And then when we go even further towards 1,000 qubits, again, a new set of requirement comes in. And today we're working on these new requirements. The new requirements are that the system has to be tileable. You want to have tiles of both the quantum hardware, but also of the control system. And we have to reflect the architecture of the quantum hardware in our control system. And as already mentioned by the previous speakers, high performance computer center connectivity is really key. And here we're also working with actually companies to develop interconnection standards. Yeah, so the architecture I already mentioned is key. So what does it look like? Our architecture is a star-like architecture. And for small systems, by the way, a single box already can control, for example, 6 qubits of fixed frequency cross-resonance coupling, for example. But if you go to larger systems, you need to grow the system, and you need to grow it in a way that you can still have global communication on a very high speed. And this is where our Z-Sync interfaces come in. Those are the lines. They go to a central piece, the PQC. So this would be one tile of our system. The PQC is a programmable quantum system controller. And by the way, this part here in the center, the PQC, has an open FPGA because this is where the error correction routines are encoded. And we've already heard that the error correction decoding is highly timing sensitive. So here we give our customers access to the FPGA. And all the other instruments, we believe we have designed signal processors of such good quality that the customers do not need to go into such deep detail. So it's a multi-layer architecture in the sense that each unit of it already is an intelligent piece of kit. For example, operation that is often done in quantum error correction is the reset of the ancilla qubits. It's a good thing if this can happen really quickly, and all it needs to know is it needs to read out those qubits, and it needs to know whether they are active or not, and if they're in an excited state, reset them. That decision can be taken locally because all information is available locally. However, in quantum error correction, where you need syndrome decoding, you need inputs from way more qubits, ancilla qubits. All those readouts are transferred, the results are transferred to a central piece of central knowledge, and here the decision making is taken on where errors have occurred, and then this is down communicated. So we have a local and a global decision making architecture. And this is what makes it truly scalable. Of course, if a global decision takes more time, so here we need about 500 to 1,000 nanoseconds, which in the realm of the required time for syndrome decoding is totally okay. So the architecture, of course, needs to support the anticipated systems as they grow, but nothing is possible, nothing works without a great team. And this is something where I'm quite happy to say that Zurich Instruments is really strong. So in our marketing and sales team alone, we already have more than 25 PhD level physicists, and this is not counting our R&D team. And with these people, we participate in a selection of government-funded collaboration project. Here I have a selection for you of the ones that I think are really interesting. And please note that they are quite international. We are in America, in Germany, in the Netherlands, and in Europe. And here we work with leading customers, researchers in their field, and it's a two-way relationship. Of course, we do our best to help our customers be successful. At the same time, of course, we learn from them. There are new things, new ideas coming up every day. And what we do is, all the learning, we bring it to Zurich Instruments, we organize it, we cast it into products, but we also share it, of course, with our other customers. So in this sense, I think Zurich Instruments has an active contribution to bringing the quantum field forward. Those are research partners here that you see. We don't only have government-funded research partners, we also work with privately funded companies. And this is something I'm particularly happy about, because for a company like IQM, Jan Götz, I believe, will be speaking tomorrow. For such a company, it's incredibly important to select their control system wisely, because their company truly depends on it. IQM, for example, has a roadmap to 150 qubits and on. HPC connectivity is a big topic for IQM, so is error correction. And together with IQM, we are developing a control system that paves the way to scaling up. And more recently, we have also been selected by the American startup Atlantic Quantum. It's a spin-off of MIT. And for them, for example, instead of developing their own system, we greatly reduce capital requirement and we speed up their startup process. And a very important argument here is that our QCCS is a very open system. We're open to the world of the quantum computing software ecosystem. For example, there's Qiskit, there's Quasm, there's Pipe, there are also other software companies like QControl, and they are all invited to connect to our stack. all of Lab1Q is programmed in Python, which by itself already is a very open platform, and the source code is available to our customers. Speaking of Lab1Q, now I'd like to take you on a little ride for a reality check. This is all quite high level and makes sense, but what if we look into reality? And here I'm really happy that I can use a photograph that has been provided by ETH Zurich of a real chip. So this one is from a Nature publication last year, where the Wallraff group has demonstrated feasibility of quantum error correction on a 17-qubit surface code chip. And when you look at this chip, what you see is you see all the different control lines and readout lines and flux bias lines on the outside. And in the center, you see the qubits. And this is not a huge chip by any means, but it's already quite something. And to give you a taste of the intricacies involved, as shown in the appendix of this publication, there are the flux lines, the green lines, and the green lines here you bias with a magnetic field the qubit to tune it. And it's a current that we inject by pulses like 20 nanoseconds duration. And the return current is in the ground plane. There are good reasons to do it like this, but the disadvantage is every flux line has a crosstalk on all other qubits. So we have 17 qubits and a cross-coupling matrix that's dense, 17 by 17. Now, whenever we bias one qubit, we need to compensate all others. And now, of course, you want to bias qubits simultaneously, and pretty soon, already with only 17 qubits, this becomes a challenge. So it's really important to have a software level system that can abstract the underlying complexity away in order to make quick progress. And here I'd like to show you a couple insights into how the software works. The software Lab1Q. Here you see an example code. In this case, it's a resonator spectroscopy. So we have a readout and a readout line. And here we do the readout for several qubits. This is something one needs to do initially, but then again, once in a while, it's repeated so as to find the resonance frequencies of the qubits and the readout resonators. What's important here is that it's done optimally. So what you see here is we have a quire loop RT. RT stands for real time. So this will happen with very little overhead. And then we do our frequency sweep. And we do 1,000 points with 10 milliseconds integration time. So if I do 1,000 times 10 milliseconds, this gives 10 seconds. In reality, it takes 10.5 seconds. So we are 95% perfect. There's only 5% overhead. And this is what really matters, because otherwise the quantum computers will get slower as they get bigger. Then I have another example here, parallel qubit spectroscopy. Again, notice very compact code. And there's a concept here, it's called sections, which I will explain on the next slides. And what we do here is we do the spectroscopy of all 5 qubits simultaneously. And again, this whole procedure happens more or less perfectly, 97% duty cycle, only 3% overhead. And these operations, they need to be done again and again and again. And therefore, it's important that the building blocks are efficient. Going on to Rabi-Ramsey, very similar. Again, we have our Lab1Q code written in Python. And here the Lab1Q compiler makes sure that the Rabi-Ramsey sequences are not only done quickly, but also efficiently in the sense that little memory usage is required and only as little data as possible is generated and transferred to the instruments, which again leads to a speed up. And here I'd like to introduce you to the concept of sections. So a section, here you can see 3 of those. The acquire loop, that creates a section by itself. Then here, which is the blue box, then there's another section. And here you can see the parameter alignment right. The length is given here, plus Ramsey max, and that's the orange section. So alignment right means whatever is inside this orange box will be right aligned, and the length will be fixed. So even when we move stuff around here, this will always be the same length. Then we have another section, the readout section here. And because it's in a section, the system will pack them back to back automatically. And then there's a relax section, which is not shown here, I believe, to allow relaxation of the qubit. And by means of this concept of sections, it's actually possible to specify big systems, like with 1,000 qubits, because it's kind of hierarchical and the timing is auto-regulating. And so after having coded those sections, of course, you want to see the result before you execute the experiment. And for that reason, we have a pulse sheet viewer. So this code here executes, and always there's a pulse viewer code generated, which you can have a look at in your web browser. It's HTML. And you can zoom in, zoom out, click on stuff, filter, and look for events. And what you see here is we have a Rabi sequence. You see how the drive pulse is getting longer and longer. You see the different sections. Here's the sweep section. There's the qubit readout section. Within this, we have the drive and the acquisition and the relax that you can see here. And then on pulse level, you can see where we play the pulses. You see what the qubits actually see. This is an indispensable tool for rapid progress working on your quantum hardware. Yeah, with this, I'd already like to conclude my presentation. What are we focusing on today? Supporting and collaborating with quantum groups and companies is really a very central thing for us, be it in America, be it in Asia, be it in Europe. Only many new groups are starting out in the world, and we find this an exciting time to get on board. For example, at Berkeley or more recently actually in South Korea with Chris. We are growing our team. The growth, of course, is a very central thing. As more and more customers are joining the ship, we need to bring more Zurich Instruments quantum people into the company. So we have open positions. We're also looking to hire in Asia. And in India, by the way, our mother company, Rode Schwarz, has a significant office, and we will use that office to also serve the Indian market. Then reduction of setup size, complexity, price per qubit is really key for 2 reasons. One is, of course, as the systems get bigger, they need to come down in price per qubit, but also as time goes, we learn how things work, we can make them more cost effective. On the software side, more automatic bring-up characterization and benchmarking methods. We have a library of these methods that is free to use by all our customers. And then new features, be it speed up, runtime performance, especially when moving towards larger system, working on this HPC interconnectivity, both on the physical level, but also on the protocol level. And then there's a lot of work still to be done on quantum error correction. We're kind of leading with work in with the work at ETH Zurich here, but to try out new syndrome decodings that run efficiently in the FPGAs, this is where the science and also our work is today. With this, I'd like to thank you for your attention, and please feel free to come to our booth. There's Nishant and Praveen from VT Vacuum, and I'd be more than happy to hear back from you. Of course, you can also reach out to me directly.
Thank you so much, sir. Now the house is open for the questions, if any.
Hello, can you hear me, Sadiq?
Hello.
Yes, I hear you well.
Yes. So this error correction which you would be doing, is it totally in the hardware domain or it is a mix? Software, hardware?
Just a second, bringing up a slide that I think, here we are. I think this is a good slide for this. So it's there are many different hardware correction algorithms. And the way it works is that there are ancilla qubits, and the ancilla qubits are there only to detect leakages and errors that occur in the data qubits. We do the readout of all the ancilla qubits, like the parity qubits, if you will. And then there's a very sophisticated and challenging algorithm to execute in very little time to determine the original error, which we then correct. And this determination, it's called syndrome decoding, is computationally intensive, but unfortunately, we have to come to a conclusion within a microsecond. So we can't run big algorithms. So the way we do it is we run those algorithms in the FPGA, and the scientists are today evaluating different kinds of algorithms that can do it with the best performance and the quickest way. So the error correction always takes the loop back to the classical world and then back to quantum.
So that means if we have to design a system, what is the ratio of the data versus the ancillary qubits when we have to keep in mind?
It's roughly 50-50.
50-50, all right. Thank you.
It's roughly 50-50, but eventually the ratio becomes even worse because you need many data qubits to encode one logical quantum qubit. So with these 17 qubits here, it's actually one logical qubit.
All right.
It takes a very significant overhead to go towards fault tolerance.
Right. Thank you.
Thank you so much, sir. Great to have you, Dr. Sadiq. Thank you.
Thank you very much, and I wish everybody a further interesting symposium.
Yes, sir. Thank you. Now I would like to request Mr. Nitin Nigam, Solution Engineer, Keysight Technologies, to share his views.
Hi, good evening, everyone. Thanks for the introduction and inviting me for this international symposium. I work with Keysight Technologies as a solution engineer. I'm a part of the QCS team, which is Quantum Control System team. Since morning, we have been learning a lot about the quantum. I'll not take much of the time because this is not the best time of the day for this type of presentation, but I'll still try to keep it as minimized as possible. Keysight has been, no introduction required for Keysight. It's been into test and measurement for a long time, almost more than 75 years. We have been working in quantum domain for the last 4 to 5 years now, and the solution and the challenges which have been overcome by the solution that we have offered, I'll be focusing more on that. Okay, so this will be my agenda. I'll talk about the control challenges. We heard just from Dr. Sadiq about a lot of control challenges. I'll try to minimize them into few slides so that we have a clear picture what exactly the challenges are, and then just reveal the new QCS system, which is by Keysight. We have recently launched this system, been working on this for last 4 or 5 years, but we have recently launched up with some of the specifications, some of the system requirements that are required for quantum computing engineers. Okay. Summarizing all of the challenges that we have, I have put up my slide into 4 major pointers: high fidelity readouts and the gates, so the signal that we simulate in terms of the pulses in the quantum circuits. The scalability of the system, suppose if you are working on 5 qubits or we wanted to scale up the system to a more higher number of levels, that's one of the scalability factor that comes into picture. Feedback and quantum error correction, and this quantum oriented system approach, because the quantum system is not the classical way it works. It requires a lot of different approach in terms of the circuit compilation of the quantum bits, in terms of the simulation environment. So how does the quantum approach that Keysight has adopted into the whole ecosystem of the quantum, that what summarize it all. So if we look at this particular slide, the single slide demonstrate everything right from the end-to-end solution. How does the hardware, the software, the integration of them together coming up and helping solving the problems in terms of the quantum computing. So the system is completely compatible if you are working on different quantum technologies, even if you are working on semiconductors, superconducting, NV center, neutral atoms. So the system is very common to all of it, and it can work in the same environment with the same precise and accuracy at different places. What are the main requirements that we saw when it comes to the high fidelity gate? Clean signal, stable tones, high precision virtual Z gates. How do we achieve that? Okay, this is the typical approach with the terms of the signal generation or the quantum circuit that we wanted to simulate as an algorithm. The problem is that most of the signal generator nowadays, they use LOs, the basic local oscillator, and then they have an image suppression which gives a noise figure into the circuit simulation itself, in the quantum circuit itself. What we adopted, if you look at the diagram on the right hand side, we have used an NCO in the hardware, which is a numerically controlled oscillator. So it is a fully digital signal that does not require any calibration. It does not create any LO. So whatever signal that you generate is completely noise free. It has the best SFDC that we claim. How do we achieve that? We have designed our own custom ASIC. So Keysight has a fab which designed their own custom ASICs. We have designed a specified custom ASIC for this particular product on quantum. So this system does not integrate to a lot of applications. We have restricted down it specifically to quantum domain because of the low phase noise that we are being achieved onto this particular platform. The system that you see, the custom frequency reference, is designed by Keysight. It's a custom ASIC in terms of the hardware. The phase noise, if you compare the phase noise of this particular product, which gives the precision and the stable tones in terms of the circuit simulation. Okay, of this self, if you look at the same diagram, I have some of the practical diagrams what we have been working globally with a lot of customers. But if you look at this diagram, there is one Keysight custom source, which is a reference source, which is going integrated in all the different boxes together. So it's a kind of a modular platform. Why we have given it modular? Suppose if you are using an FDM technique for the readouts, you can have more readout channels or less readout channels, more generation channels. How do we integrate them together? They're completely integrated using a standard box, synchronization box, which is integrated into the same platform. So the diagram itself shows the phase coherence between the pulses is very, very high that we are achieving. So they are almost 99.9% phase coherent to each other. That's been measured onto the system. Okay. How do we achieve this approach? So as I told you, this is a completely a modular approach. The signal generation, the readouts, it's all complete hardware. From the classical point of view, how do we get into the quantum domain? That would be a later part of it. From the classical control electronics, the digitizer, which is used for the readout pulses, then the digital IOs. We also are a lot of other hardware which can also be integrated into this particular platform. But just to show you a diagram that how does a scalability system looks like. This is an example of a 500 control qubit system. It does not use FDM, which is frequency division multiplexing for the readout. So we have integrated this whole system using a standard reference source across all the PXI platforms. So right from the top to the bottom, every channel that generates a signal or the quantum circuit pulses, they are all coherent to each other and they are in phase control. So you get the same performance when it comes to the generation of each and every individual control pulses at every stage. Okay, another thing is how do we achieve this feedback and quantum correction? This is very important because we need the readout and the generation in the hardware itself in order to have the faster, in order to have a faster communication between the readout and the generation, we need to have the error correction within the hardware itself. That's where we have integrated this topology between the inter-chassis communication. So if you look at the center block diagram, which is a system timing module, this timing module is connected to all the required generation as well as the readouts so that you can integrate them and there is no latency between the readouts and the generation part. And the feedback can be achieved within the hardware itself. So this is the communication platform that we have achieved. We have the daisy chain approach, which is a star topology that has been used into this particular platform. So if you have many number of qubits, so one chassis typically would be good enough for 16 qubits, but it definitely requires the type of FDM technique you are using. So if you are using FDM techniques, you will have more control of the qubits. If you are using without FDM, then you would require more readout channels. So the number of maximum qubits that are being currently supported typically goes up to 16 into a single chassis. But if you have multiple chassis together to generate, operate, then we can have a daisy chain approach within the chassis system, and then you can have a communication between them. When I say the feedback correction, this is the block diagram for the 5200, which is we call as a digitizer for readouts, and AWG, which is 5300. They are completely integrated together using a system module. So whenever we generate the pulse being sent and the readout being done, the feedback is generated within the hardware itself. How do we do a readout? Okay, so if you look at this algorithm, I'll just skip off this in the interest of time. Okay, if you look at the system that I'm talking about from top to bottom, we have this particular hardware from Keysight, which has a real-time sequencer inbuilt into this, which is marked as this red one. Then there are hardware drivers and the pulse sequence compiler, which is the exact hardware. That's where you generate different type of pulses and readout. If you look at the next level of the approach, this is a real-time sequencer, that DSP that we have processed. So that's basically the internal FPGA hardware processing has been opened up for the users who wanted to do a modular platform, and it's completely inside the hardware. The next level of stack of software that we talk about is the diagnosis, benchmarking, and error correction. We have integrated, so there is a company known as Quantum Benchmark. So Keysight has acquired Quantum Benchmark, which is used for error suppression and error mitigation. So that particular algorithms from the Quantum Benchmark are integrated into the hardware that I'm talking about. So this complete hardware gives you a provision to generate, read out, and do an error diagnosis and mitigation into the same hardware. And the software itself is also integrated within the same hardware. So there is no separate library or hardware which is required to do an error mitigation and error diagnosis and error suppression. So it's one dedicated software that does all of it. On top of that, we are the new development which we are working with a lot of simulation software like Qiskit or CircuitPyQuil. All of these libraries are getting integrated within the Keysight quantum control system. So all the APIs, so the API that we call for this particular hardware are completely open. So you can integrate all of these libraries into the same platform, and you can design your own circuits, take the feedback within the hardware, the same so that software from the Quantum Benchmark is known as TrueQ. We call them TrueQ. It can, I have seen example, there was a question from sir that if you wanted to go for a 100 qubit, if you have clusters of qubit, then how do we do the error correction? So I've seen some of the examples. We have some of the application note from Keysight and Quantum Benchmark, where they're demonstrating this particular error correction into the software as well as the hardware, which I have seen up to 50. Probably I can share more, but this dedicated hardware and the softwares help you to generate readout into the same hardware and software together with the help of TrueQ. On top of this, this is how the TrueQ experiment looks like. This is the integration that we are trying to do with our APIs. It's almost there. We will be launching a few of these things, which will integrate the TrueQ completely into the hardware itself. So generation over the same hardware, readout over the same hardware, and the feedback correction over the same hardware. Scalability is also at the same hardware. So you can do all the 4 challenges that we are talking about right from top to bottom, the same platform, right from the hardware to the software up to the application layer. So you can design your algorithms, you can dump it onto the software, the APIs that is being provided by Keysight, and you can generate your signals, read out, and do an error correction into the hardware itself. So that's the platform that Keysight is working with, and we are happy to launch this solution. This solution is being used at a couple of places, where we can take some of the references to go for. Okay. So this is the complete hardware that we are working with, and there's a lot more hardware which is designed for this particular product is available in the next quarter or so. We'll be launching all of these hardwares together, and this system goes completely upgradable. What exactly is the different in this system is the complete solution right from end to end. So if you are looking from the control electronic side, the hardware is directly from the Keysight, and the integration of the software is from the Keysight. That's something unique that we have done. Another unique thing that we have done, if you look at the phase noise number of this particular generation of the signal, they are brilliant. We claim that, I have not read the couple others, but we claim that's one of the best in the hardware in the quantum space. So that's something that we have done. The digitizer that we have introduced has the best noise floor that is possible, that we have integrated. And all of these coming up into a complete modular platform with a scalable architecture is something that we have done into this space. So wait more for some more updates very soon on the quantum hardware. We'll be coming up with this. Yeah. Okay. This is just an example of I've just taken an example of a 2-qubit processor. How do we do that? We also have a Labor software. In the interest of time, I'll not speak about it, but Labor is something where we can do all of the, it's a GUI-based platform where you can do all of the programming, but you can also do a programming in terms of the Python space. Labor is something like that. We have a hardware which are these AWGs. Then we have a digitizers. So all of these are generated, and this is where we do on the bottom side, we do a control and the readout. If you look at the same in the 10-qubit processor, that's how it looks like. The same hardware, depending upon the chases, you can include multiple modules into it. You can generate signals, and you can do a readout basically into the same hardware. Okay, just to show you how exactly. So I just created some of the examples for your reference. These are basically the APIs that we call. Let me just show you how exactly. So what I've done, if you look at the flow of the APIs, so first of all, I have integrated the complete configuration of the hardware. So how many number of AWGs you have, how many number of digitizers you have into your system, I have uploaded them into one particular file. Second particular file, I have done the calibration of that particular system into the software itself. We don't require hardware calibration, as I mentioned, but if you just wanted to run, make sure that I've included a calibration file which will do a calibration file of the same hardware that is integrated. The third step I do is to generate a signal. So in order to generate this experiment, I have imported the QCS.API, which is the first line that you see. I have imported the readout channels, I have imported the entities and the complete control system into one particular file, and created this particular file to generate our Rabi experiment. So you can create, depending upon the hardware that you define into this particular APIs, you can generate. You don't require any separate software for this. The APIs of this particular hardware are completely usable on any platform. You can use them, you can download them, use them, simulate them. So if I had to just to simulate, so I just simulated, just a second, yeah. I just simulated some of the experiment, but this is This you can do in a real time. If you have an hardware in place, we can generate, we can control, and we can do a readout of that particular channel itself. So that's where Keysight stands right now into the quantum space. We have a dedicated team. We call that team as a quantum engineering solution team. So that's a dedicated team of lot of PhDs which are a part of that particular team who are designing this particular hardware and the related software in the quantum space. Thank you. I'm open to question. I guess I was fast. I didn't want to make you wait till a lot of time in the evening. So I understand the pain of sitting at 7 o'clock in the technical seminar. So. Okay, so you mean to say different hardware as in like AWG's digitizer? Okay, okay, yeah. I have a slide on that. Can you just slide it? Okay, so if you look at this, the block diagram in the center, okay, the black box, this is the system timing module. Okay, so this system timing module is connected in the backplane to all the required hardware. So whatever is a PXI chassis basically, right. And the best part is there is a clock. I don't know if you can see at the bottom side there are blue cables, the small blue cables. So there, it's a 2.4 gigahertz reference clock which is connected to every individual module. Okay. And then we have a system module in between. So this system module always has to be in place. Okay, and then you can connect your hardware on the left and right hand side, and then this hardware is integrated at the back plane with the same clock reference. So they are completely synchronized in that.
Okay, so that system timing module is another FPGA which only sets the clock references.
Yes, it exactly sets at the same place, and then
so
we
that
have
clock reference is used for any
all of it, right? So there is a.
Okay.
So if you go back to the.
So another thing is
this slide, this clock reference.
Yeah,
This is a 2.4 gigahertz clock. Okay, this is this is the same clock that goes into the every hardware for the complete synchronization and the phase control.
Another thing is that when you consider the synchronization, one is optical delay, another one is the electronics unit delays. It's two both of things been taken care.
The channel to channel delay you are asking about.
Yeah, so the optical delays which we
between the channel or the readouts.
No, between the channels.
You mean the same module AWG channels?
Yeah.
So it's completely phase coherent. Okay. The channel to channel delay is it's basically worked on to minimize it in terms of less than nanoseconds. So if you look at the two chases, so okay, if we talk about one chases which has multiple RF modules, and you wanted to know the module to module delay between one module will be completely phase coherent, the other module is also phase coherent. When we talk in terms of the multiple chases, one chassis and then second chases, that channel to channel delay is being worked on. So that's still into the roadmap. I can't share the number right now, but it's still into the roadmap.
So coming to the error correction, which that module sits on the same FPGA itself.
No, it's actually, so if you look at the hardware part of it, you generate from the AWGs, you read out from the digitizers, and then the TrueQ compiler, the software, is basically the software which will be integrated into the APIs. Okay, so as soon as you do the readout, it will go into the TrueQ compiler, and then you can do the error checks.
Okay, so that basically corrects the errors.
Yes. So if we go back to this particular slide, okay, this slide, this import and export thing that you see on the right hand side top. Okay. So this company Quantum Benchmark is a Keysight company now. They are specialized into the error correction. So we have integrated them into our hardware.
So it's not part of that. It's an API basically runs on the.
So no, this is a dedicated software, okay, which will be included into the APIs of the Keysight hardware. Okay. So the one that you see that is complete code. So the bottom side is the pulse sequence API. This is the dedicated API. This is the circuit APIs which will be with the help of this QSkit and all of these simulation software. So Quantum Benchmark fall into this category, and then we will integrate it with this same APIs down below, and from the waveform based sequence that we generate or the primitive real-time backend we can generate.
Thank you.
So it will be a top to bottom approach that will be followed. Okay. So do we have any more questions? Thank you so much for listening to me. Enjoy the evening, and I'm really sorry back again at this time.
Thank you so much, sir. Now I request SD Sudarshan to felicitate Mr. Nitin. Thank you, sir. Let us now proceed to the panel discussion. This session is chaired by Dr. SD Sudarshan, ED, C-DAC, Bangalore. I would like to call Dr. Manjunath RV, Senior Director of Quantum Hardware, QPI AI, Mr. Krishna Kumar, Scientist G, C-DAC, Trivandrum, Mr. Mark Yellow, CMO and GM, Tabor Electronics Limited. He is connected with us virtually. I like to invite on.
Hello. Hello,
Good
Mark.
morning from California.
Can you hear us?
I can hear you.
Yeah, please share your presentation with us, and you can proceed.
Hello. I request the session chair to take forward the session for the panel discussion.
Yes, have a good morning, good afternoon, good evening from all people collecting all over the world. Thank you so much for the patience. As the session started, it was told that today we have a car equivalent but running at 5 kilometers per hour. So quantum things go a little slow right now. So don't, please bear with the time. But we are learning a lot. The interactions are showing the key interest. And towards the end of the session on the control and measurement electronics and calibration, one of the key criteria for any system to be successful, both in terms of being able to use in real life situation and also being able to compare and contrast with the rest. This is very important. Typically, measurement and control in industry, other places are used for protection purposes. But here, this has few more applications beyond just protection. To increase the uptime, as was mentioned by some of the speakers, the calibration, because of the drift that is possible, the instabilities that come in this kind, require a much more stringent measurement electronics and control electronics. So we have an extreme talented teams here. So maybe I will start with Manjunath from, he is the Senior Director of Quantum Hardware at QPI AI. Can you highlight that, maybe in the interest of time, the top 2 challenges and what are the unique things you have done, quickly?
Yeah, so in this aspect of measurement and control, firstly, I think the goal towards open quantum architecture is a very good move because we want to define well-defined interfaces between the cryostat environment and then the control environment and then the signals that go up to the application layer. So we are working with several of our partners to define this very accurately. And the other thing is that so we have various algorithms which we start from generic small circuit algorithms, and then we go towards variational quantum circuits and then hybrid quantum classical interfaces. So how do we run these all these algorithms in a well-defined interfaces between the application layer and the control electronics? So a key aspect is the quantum circuit layer, that we worked upon in our team. So basically, this quantum circuit layer needs to have a generic language, which in this case is the open QASM-based language thing. So once we bring all our higher level application algorithms to be run on the quantum hardware, which is a quantum accelerator, we split those instructions very specific to the quantum hardware through the QASM instructions that can be sent to a server which is close to the control electronics. So if we define these kind of interfaces very well, then the higher level application and algorithm engineers need not worry about the complete flow, what happens below that. So this is one of the key challenges, and this one that is being addressed, and also I think with all the partners we see that this forms a good layer. And the other thing is, when we go towards algorithm and software engineers, they don't want to learn new language. They don't want to work on a new programming language, learn this one. They want to use this generic flow of the C, C++, or even Java. But we have an abstraction that we provide in such a way that all these languages can be supported by the control hardware through the open QASM interface. So that is one thing. The other thing is understanding from the lower layer, which is the cryostat environment. So basically, you know, the superconducting qubit system is still a noisy based system. So it's based on Josephson junction, and although we do on a wafer scale, if you do a 10 millimeter by 10 millimeter dice for a 10 qubit or a 17 qubit, we do see that we won't get 100% yield. It's always less than 20%. And to get the Josephson junction resistance very accurate, to get the frequencies very accurate, a lot of post-processing step occurs. And the other thing is that, so here this causes a lot of, I mean, the coherence time is reduced because of these kind of two-level defects that happens in the processing itself. So that is not known to the control system people or even the application people. So again, a very accurate interface between the cryogenic system layer with the control layer to know, okay, for every qubit pulses or whatever we send it to from the microwave, from the room temperature all the way to the cryogenic environment, we get a well-defined component level inputs from the cryogenic environment.
Yeah, so maybe this is a aspect I think very important. Basically, you are abstracting the complexity and let people use whatever language they are comfortable, whether it is C, C++. Yes. Probably top two things make it easy for those who don't have the background. That is fantastic. So now we have Mark Yellow online from Tabor. Thank you for waiting after waking up so early in the morning. Thanks, Mark. I'll just
thank you very much.
Yeah, same query to you. The top two things that you thought in this particular area, and how it is going to benefit the end customer or the end user. If you highlight that, I think that will be a good takeaway before we go for a grand dinner. Thank you.
That's fantastic. Yes, I'll just use these slides to help me talk about the top four things. So at Tabor Electronics, we make direct-to-RF quantum control hardware. We've been in the business for over 50 years, helping physicists solve some of their most complex problems. We see that, you know, number one, the problem today, the biggest problem is the complexity of a quantum control system. Everybody today has very polished slides that look excellent with great graphics, but at the end of the day, a real-life quantum control system is a lot of cables, a lot of uncertainty, a lot of drift. Sometimes you can use some software to take out some of the errors introduced by the cabling, the mixers, the upconversion, the frequency translation, or you could use a different approach, which is the direct-to-microwave approaches, which we use with the Tabor one. So that's number one, is taking out the complexity of the measurements to be able to come to some measurements really quickly. So the second thing that we want to solve very quickly is how easily you can do that And, you know, typically you need to prove a qubit's a qubit. So the second way is how quickly. So first we reduce complexity. Second, we do the measurements very fast. And so some of the other vendors have already commented on that. So to do these measurements, standard spectroscopy, the Rabi oscillation and the T2 decays, we have implemented an algorithmic layer that allows you to do these quickly. You can measure on many qubit chips. Let me show you an example of a qubit chip. Like this guy here, have multiplex readout lines. So when we digitize the signal here, one of the things that's very important is to have also, and this is the third thing, is to have a digital processing library within the chipset or on the silicon of the device. So we can do with a single unit control up to, do 10 readouts. So we have 10 digital down converters implemented in our silicon, and then you can control multiple instruments from those readouts. So, you know, we have built the system, and this is point number 4, to be scalable, so massively scalable. And we have both industrial customers and laboratory customers across the US. So number 4 is, once we've got those readout lines in industrial system, you know, you're going to scale up to tens, hundreds, maybe thousands of qubits. So you want to be able to build this in an industry standard way as well. So it's kind of 4.5 is not only that we're scalable and controllable across all these modules from the single multiplex readout line, we can scale up to hundreds and thousands of channels, but using the same technology as well. We can characterize a single qubit or a couple of qubits on a chip in the laboratory environment as well. So those are the 4 things, essentially. Reduce the complexity by going direct to microwave, having algorithms that allow you to do your standard qubit measurements, have FPGA processing that allows you to do them very quickly, and then be able to scale the measurements or scale to many, many qubits on a single chip. And just to show you that we've been doing this for a very long time, 51 years. We have the largest installed base of this type of technology in the USA for quantum across industrial and the national lab system. We have strong university collaborations, and that's shown in our the multiple publications that we've had, including Nature and also the prestigious Physical Review Editor suggestion, which was a good one. And in terms of our footprint in India, and Nick Hill, our local guy, is there in the crowd with you. He runs a global R&D center in India where we do more quantum algorithm development. And we also have a growing installed base already in India with TIFR, IIT Bombay, IISER Pune, and CMET. So that's how I would answer your 4 questions with the aid of some slides.
Thank you very much, Mark. That was really crisp and great. And good to see that maybe you'll be happy to know most of your clients you are mentioning, they are part of the symposium, they are very much here. That's great. And direct to microwave and scalability, really something so nice. And the hardware acceleration was mentioned by several. So in the interest of it, maybe we'll take just one question or 2, because panel should at least get a chance to answer a question. Maybe 1 or 2 questions, and then we'll wind up. Thank you.
Sir, he's there. Krishna Kumar ji is there.
Is he online?
Krishku is there.
KK, are you online?
Yes, sir.
Oh, then you also get maybe a couple of minutes. Quickly, you can highlight, what we are doing at C-DAC. In particular, the Pune contribution and Trivandrum, Bangalore, you can highlight. Please. So Krishna Kumar Rao is the person driving lot of RISC-V related activities, and he also handles the team, anything related to hardware control measurements and he has joined online. KK, please.
Sir, can I use slides?
Yeah, maybe just one or two so that people can also read, that's fine.
Yeah, just first let me, I don't want to start by correcting the chairperson, but I am a different Krishna Kumar, not the Krishna Kumar Rao that you mentioned who's doing the describe.
Okay.
I come from the communication background. I am with the...
My fault. It said Krishna Kumar Rao here in the printer.
Yeah. So just to means my background is basically communications and signal processing, and what we have, whatever I'm placing here is basically some thoughts which we gathered from myself and my colleague Mr. Baiju from the Strategic Electronics Group across here with the interactions that we had with ISER Pune, Professor Umakant Rapol and his team. So one takeaway that probably, like, are my slides visible by the way, or
they're visible, but as a deck. But
okay,
just you can go ahead.
Yeah, sorry. So
yeah, now it's good.
Yeah, okay. So basically, a few thoughts, like the perspective that we look at is as the quantum processing unit as a black box, not first and foremost because we don't understand the quantum that well as the physicists do. We take a engineering point of view, and the idea is to define those two interfaces, which the purple interface that we have shown here between the quantum system and the control electronics, and also between the control electronics and the user domain. So the reasons could be like the underlying quantum processing can be anything, like what we discussed. But this is mostly motivated by us as the interaction with Professor Umakant, where they are working on a trap-down kind of architecture, but it could be anything. So there is a certain level of generalities required, but as we have seen throughout the day, there are different types of signals that are of interest, like it could be digital or analog on the input or output, it could be continuous wave RF, or it could be some arbitrary waveforms and all that. So we have certain core competencies which can be used, like we have not started working, like the Bangalore team, Hari Babu and his team has started working on a collaboration with IASC for a superconducting based system. But this is my views are more general in the sense that I'm just trying to highlight what we have. We have embedded system development capabilities, analog, digital, mixed signal hardware capabilities. RF, we have a good RF lab here. We can work up to about 4 to 6 gigahertz at the moment. We have developed systems up to 2 gigahertz, but we can easily scale up to 6 gigahertz. Then there's a power electronics group which can offer power supply design, and of course Krishna Kumar Rao's team who are actually working on the microprocessor this thing. And on the product design side, we have capabilities like multi-layer high-speed, high-density interconnect, PCB designs, and some amount of product design and some amount of compliance design in compliance with MIL standards for the EMI, MC, and the environmental specifications. So one point I just want to bring out here, this is thanks to Colonel Nath for motivating this concept, that SDR, which is a software defined radio, which we have been working on in some of the earlier applications. So this as a concept which can be probably thought about for developing control electronics. So it could be like, as I said, different types of physics can be running in the QPU, so which may need different types of signals and with the different parameters. Since the systems are evolving, some trial and error approaches may be required, some parameter configuration required. And as we have seen, there is some RF in many cases, whether it is superconducting or even what we learned from Professor Umakant is that in trap-down systems also there are some RF signals that play around. So the SDR philosophy offers the required flexibility and configurability. But yeah, so we have been working in SDR for quite a long time, but I'm not going to delve into all those things. These are some of the work we have done already, but these were mainly for military communication applications and not for quantum systems. I don't even know what a qubit is probably. Like I have a great regard for all the physicists who worked in this, starting from Max Planck on to the present day things, but I was not as intelligent as the physicists, so I learned engineering. So, but what I look at it is basically this team looks at it is like we have certain capabilities, and the concept of SDR where you can use the same hardware or the platform to give it a different personalities, targeting different use cases or different applications. For in this particular example, you can develop probably SDR based systems for control and measurement hardware for different QPUs would be the idea I wanted to present here. So that's all. Thank you so much for listening to me at this.
Thank you, Krishna Kumar. Yeah, earlier you were not visible. Once I saw you, I know the other Krishna Kumar. So I got corrected as was expected in a control measurement session. That's good. So what we are trying to communicate here is probably C-DAC has its own strength in control electronics. For the quantum computer being developed by Indian Institute of Science, the complete control hardware is being done by C-DAC. There we have various aspects, but we can interact over the interval. Haribabu also will be there later during dinner, and I am also around. We have our teams. So again, just maybe any one question if there is any. Dr. Anindita. Or anyone else? Any one or two questions? Okay. So then I'll basically have the only pleasure of thanking right now, so that the next session, which is still awaited, they can take the stage. Thank you, Mark, Krishna Kumar, and Manjunath. Thank you for entire audience for staying this much, and your patience is really appreciated. Thank you.
Thank you.
Thank you so much. Thank you, sir.
Station chair to felicitate the panelist. Thank you, sir. Now I request Colonel Ekinath to felicitate the session chair, Dr. S.D. Sudarshan. Thank you so much, sir. Now we move to the last session, which is about brainstorming on quantum algorithm and quantum error correction. The session is chaired by Mr. Aditya Kumar Sinha, Director, C-DAC Patna. I would like to call Dr. Anirban Mukherjee, TCS Mumbai, Dr. Vishwendra Singh Punia, IIT Roorkee, who is connected with us virtually on the dais.
So good evening to all of you. I have a good news that this is the final session. And thank you for patient listening. It was a long day. So this session is basically talking about this quantum algorithms and quantum error corrections. We have two speakers. And Mr. Vishwendra Singh Punia is Dr. Vishwendra Punia is from IIT Roorkee, and he's from academics, and we have from industry, Dr. Anirban Mukherjee. So we'll start first with you, Anirban. Okay.
Can you put up the slides, please?
I'll just, in the morning, Professor Briggs mentioned about that quantum computing plays by different rules, and so with the algorithms. A lot of references had come in the morning. about the quantum search algorithms, how it is faster than classical algorithms and all. Quantum factorizations, where it has been implemented, quantum simulations, quantum machine learning have been referred a number of times, quantum optimizations and all. Quantum cryptography is another area, and quantum error corrections. So we have a very apt speaker today. Is Mr. Dr. Anirban Mukherjee. He is already having kind of 5 years and more experience in this quantum algorithms and quantum many body theory, okay, of correlated electronic systems and all. I would like to listen more from you, your insight and your thoughts on the, in general, this quantum algorithms, error corrections, and particularly on the kind of work what you're carrying it out.
Thank you.
Hello. Slides, please.
Hello, everyone. Thanks for staying back for such a long time. And in TCS, we are working on 4 verticals mainly in quantum. One is simulations, another is machine learning, and also security areas, optimization, these 4 areas. I am working in the simulations area, and I'm looking into the aspects of studying large molecules and what to do with the present day quantum algorithms and how to work towards fault tolerant algorithms, which could be useful for resources for simulating large molecules in the future. Next slide, please. So basically, this was discussed in the mornings. One of the speakers, they mentioned about the importance of this quantum algorithms in the pharma industry. Indeed, that is the case, because the big problem that we are coming closer to, given the magnitude of different viruses and diseases that are going around, we need a very good assessment of drug ligands. Why? Because the way the drug ligands interact with an environment, maybe water, solvent, or protein, different industries have measures. Somebody measures hydrogen bond propensity, somebody measures binding energy. These are some real numbers that they look for in order to distinguish which ligand will act better against preventing a disease or against another ligand, which one will do better job. So there we need a good estimator of binding energies, and the problem is that the binding energies that we are looking for are often orders of magnitude smaller than the total energy of the system. Let's say the total energy of a system is 1,000 kilocalories per mole, then the binding energies is of the order of 1 kilocalorie per mole, which means that if there is an error in the estimation of the total energies, then in the differences of this measuring the difference is to be constructed to measure the binding energy, that accumulates the error, and the error actually, it doesn't remain within 1 kilocalorie per mole. It actually is much or orders of magnitude higher, like tens or hundreds. And the problem being the fact that we rely very strongly on something called the density functional theory, invented by Walter Kohn. And the technique, although it has the fantastic scaling in terms of the number of molecules and still considered to be the most industrially usable state-of-the-art technique, but its limitations are that it doesn't provide the amount of chemical accuracy that is required to distinguish between 2 drug ligands. And then come some more state-of-the-art techniques like couple cluster, singles, doubles, triples, which is considered to be the gold standard in quantum chemistry. but it has a very dangerous scaling, like n to the power 7 if triples are considered, where n is the number of atoms, spatial orbitals. So if imagine that if you have just 70 spatial orbitals, that's just one isolated drug molecule. Then also 70 to the power 7 means that you are dealing with something of the order of 10 to the power 14. That's a very big matrix size that you're dealing with, because you need to actually diagonalize that matrix, or you need to get some numbers out of that matrix. And that matrix appears in form of a Jacobian, which needs to be solved iteratively in order to get those numbers, which are useful to assess the energies. So that is why we need a more efficient algorithm to implement these well-known quantum chemistry methods. Now, there has been some work towards that, but in the NISQ era. So the NISQ algorithm, like the variational quantum eigensolver algorithm, that actually has a very bad scaling in terms of the number of C0 gates. The number of C0 gates scale as n to the power 5, and the number of parameters scale as n to the power 4. Now, if I just do a rough calculation, 70 orbitals, 70 to the power 5, it's a very big number again, 10 to the power 9 C0 gates. No computer will give you in the NISQ era also, and then there is no point in thinking of a variation algorithm of that, because 10 to the power 9 gates have to be implemented, and this has to be queried multiple number of times in the variation algorithm sense. And then in a variational optimization landscape of n to the power 4 parameters, you will face barren plateaus, you will not be able to converge, and then you will have to fall back on meta-heuristics, and then again goes the chemical accuracy out of the doors. So that's the problem. So that is why most of the pharma companies are very keen in finding the quantum resource estimates for fault-tolerant algorithms. Now, what are the fault-tolerant algorithms we have? Unfortunately, we have much lesser fault-tolerant algorithms than the number of NISQ algorithms, at least for usable for quantum chemistry. I'm not talking of Shor's or Grover's. They will not work for quantum chemistry. For quantum chemistry, one of the most state-of-the-art techniques is called the Kitav phase estimation technique, which is a quantum phase estimation technique, which was one of the earlier works, but then came in something called qubitization by Lo and Chuang from the Microsoft. They finally later moved on to Microsoft, but then that technique sort of allowed to get a better number in terms of the quantum resource estimates. What we are seeing is that what are the number of logical qubits? What are the number of Toffoli's? Those are how to get those numbers which are small, which are at least accessible within a fault-tolerant future. So currently the numbers are pretty big. I will showcase some of the numbers, but again, the approach of the fault-tolerant algorithms need to be revised. We need more research in the fault-tolerant algorithms region. So what TCS what I have been doing is working on this approach called problem reduction, where what we are doing is that we are saying that we'll start with a large active space, let's say 70 orbitals, 58 electrons, and then we will do downfolding to reduce the active space size. That means we will be able to downfold electronic correlations and put it in a smaller space, let's say 30 or 40 orbitals, and we can keep it shrinking down, and in that process, as we shrink it down, we get the energies that we want. So that process of downfolding means that we do not directly solve the problem of the 70 orbital. We rather redefine our expectations and compute the simpler problem out of a bigger problem at every step. And this problem of downfolding can be obtained by removing the very far away orbitals from the homolumo space. The homolumo space is the sacred part of quantum chemistry. All the electronic states that are close to homolumo are the ones that participate the most in computing the final energy of the system. So if we can remove the large orbitals and fold their effects onto lower orbitals, then we will be able to obtain a more effective problem for lower dimension. Next slide, please. So what we did was that we tried to get some numbers now. Given that we have an approach, can we get some numbers? So we took 3 molecules that have been well studied with respect to quantum resource estimation. One is a molecule, the first molecule, FeMoco, that's a cofactor of nitrogenase. It is something that allows in nitrogen fixation, biological nitrogen fixation. So the idea is that we do not know what is the charge and the spin configuration of this molecule also. We do not know that. It's too difficult to compute. And we only know from DFT what is the resting stage or the resting structure of the molecule. We do not know what are the different catalytic pathways that it can take when the reaction proceeds. We do not know that. So what people do is that they try to come up with all possible DFT structures that can happen, and then they try to compute that for different DFT structures they get different Hamiltonians, and from that they compute the resource estimates. So we compare the resource estimates of this FeMOCO molecule with the works done by Microsoft in 2020 using this qubitized phase estimation, which is the newer version of the phase estimation technique. And what we find is that if we consider the number of logical qubits, the scaling is similar, but if you consider the number of Toffolies, it's quite different. And the reason being is that we are trying to estimate the simpler Hamiltonian or the simpler problem out of a bigger problem, and we're doing it in a set of recursion steps. So we are breaking down the problem into multiple circuits that need to be serially performed. Whereas what they are doing in their approach is that they are trying to measure the entire set of circuit, they have one single query circuit which they are querying number of times. So that is how the job gets distributed in our case, and therefore the number of Toffolies remain low. If the Toffolies remain low, that means you can perform better error correction with using less, because this is the number of logical qubits. This is not a number of physical qubits. The number of physical qubits will actually be at least 1,000 times, if not 10,000 times bigger than the number of logical qubits. So now, if we can do better error correction, then we can reduce the allocation of the number of physical qubits, and therefore we save a lot of quantum resources. Similarly, if you have Toffolies which are less, then every execution of the circuit can come down. We feel that those are the reasons why we are trying to come up with an alternate technique for estimating the energies of such large molecular systems. And furthermore, we are not just interested in single isolated molecules, we are interested in the environmental interaction of the molecule, because that is where the real chemistry lies. Second molecule that we are interested in is directly of the pharma industry usage. It's the cytochrome P450 protein, which is it's a cancer drug molecule. So there again, we give the numbers comparison with what Boehringer Ingelheim, for example, has. So these are the numbers that we are getting from our approach. We will be releasing the archive work on it soon, and we'll let you know once that's done. The third is again a molecule of interest for the sustainability issue, carbon capture. It's a catalyst, ruthenium, and there again we are able to obtain better numbers in terms of the number of Toffolies and the query complexity. And runtime, by the way, it's not that we actually run on a quantum computer, it's the estimates that we best have from companies like PsiQuantum as what is the microsecond in 0.10 microseconds rather, one Toffoli gets implemented. That's the assumption. If we can make that assumption, then this is the runtime hours that we get. By multiplying the query complexity with the number of downfolding oracles that we used, we multiply that to get this number. Then next slide. So this approach that we have developed is actually again a technique inspired by the couple cluster technique, but put on the quantum algorithm, put on the fault tolerant circuit. So the takeaway message is, what are the newer fault tolerant algorithms that we can devise to update all the chemistry calculations that have been there and have good scaling, like order N6 and order N7, they are not that bad scalings. If you can re-implement them using quantum circuits, and but for a fault tolerant regime, then what are the numbers that we can get? For large molecules, I mean, because couple cluster being the state of the art gold standard should have a fault tolerant equivalent. So this is what we are developing here. So this is one aspect. Please go to the last slide. That's just so this is some results that we got from our steps. But what I want to give you the takeaway message is that in TCS, this is just one of the areas that we are working on in quantum simulations area. But rather, we are actually also have a team of 35 members out there, and there are 5 PhDs. And we are working on problems ranging from quantum machine learning and optimization in the finance domain, and also we are working on problems related to cargo fleet optimization, job shielding, portfolio optimization. All those problems we are also working on, but we have different verticals, and the model that we work with is that we have expertise corresponding to different regions of interest. So I'm coming from the simulations background, so I give a simulations overview, but in general TCS has all the 4 verticals in which we are working. And we have around 15 patents and 15 papers and 10 patents, and we're working for more. Yeah, thank you.
Thank you, Anirban. And now we have a second speaker. Please take your seat here. We have a second speaker, Dr. Punia from IIT Roorkee. He's having a very interesting interest on quantum biology and biomimetrics, quantum photocells, quantum random number generators and all. Over to you, Dr. Punia. He is joining online.
Yeah, hello. I hope I'm audible.
Yeah, you are audible. Yeah.
Yeah. First of all, thanks a lot for having me in the panel. Special thanks to Colonel Nath and Dr. Gurumohan. So I'll share my thoughts on our work on quantum control. And so let me quickly tell that generally what we have on one side is the theoretical advancements in quantum algorithms and quantum error corrections. And on the other side, we have multiple hardware realizations of quantum computing. And nowadays, it seems that the view that is emerging in the community is due to different advantages of different hardware realizations, that possibly in a QPU, different qubit realizations might be used for different applications. For example, superconducting qubits might be used for fast gate implementations. Spin qubits might be used for storage purposes or storing information for a long time. So what it means is that we need to have different, we need to run different kind of algorithms on different hardware implementations. So what I'm trying to bring to discussion in this symposium is that we should be looking into hardware-aware quantum algorithms. Dr. Itamar pointed to it to a certain extent. And I'll elaborate on this in the next slide. And second point is that not only, so QEC is an integral part, but apart from QEC, quantum control techniques are used to, all of us know quantum control techniques are used to improve gate fidelities. So quantum algorithms amenable to quantum control techniques should also be one of the focuses while looking from a practical point of view, which means that apart from the theoretical analysis of performance of quantum algorithms, it's also essential to do hardware-specific performance analysis of various algorithms. So now let me elaborate a bit more on quantum algorithms. Quantum algorithms, as all of us know, are based on a quantum circuit model of quantum computing, which means basically performing sequential operations on quantum gates. And where gate fidelities play quite important role, and that's why quantum error correction approaches, the quantum error correction becomes extremely important. So, for example, the quantum, one of the key operations in various important quantum algorithms is quantum Fourier transform, and this is how quantum Fourier transform looks like. What it means is, theoretically speaking, a QFT requires arbitrary phase operations between any two qubits. But the problem is that our hardwares do not allow that. And similar is the case with the Hadamard transform, which is also, again, another key component of multiple algorithms. And if we look at the realistic quantum hardware architecture, this is how they look like. And what it means is that we cannot arbitrarily do operations between any two random qubits. We need to, even a 2-qubit operation needs to be done through via transferring quantum information through multiple qubits. Moreover, doing a Toffoli operation or a 3-qubit operation becomes difficult, and possibly in many cases needs to be broken down in multiple 2-qubit operations. So that's why the real performance of various quantum algorithms, even if they are performing very good in theoretical analysis, the real hardware performance becomes extremely or very poor as compared to their theoretical performance. So that's why quantum algorithms which are aware of underlying hardware architecture should be, I guess, one of the, should be one of the focus areas. And moreover, we have quantum control techniques, and one of the most basic quantum control techniques are dynamical decoupling pulse sequences and gradient ascent pulse engineering. The reason is that generally all the RF operations that we do on qubits, most of the RF pulses, they contain inhomogeneities and slight, or they are not ideal basically, and that's why the gate operation is not ideal, which results in lesser fidelities. So the point is that in order to reduce the quantum error correction overhead, quantum algorithm community should also be aware of the underlying quantum control techniques, which means that algorithms which are more amenable to quantum control techniques, they should be quite active area of research. So in summary, what I would like to say is that that even for the standard quantum algorithms, we should be doing analysis, or generally in many cases we already do that, but the hardware aware quantum algorithms are extremely important, because different kind of hardware realizations may be using different, or different algorithms may be running on different kind of hardwares, and quantum algorithms which are more amenable to quantum control techniques should be the focus. Moreover, in order to analyze the performance of quantum algorithms, end-to-end hardware requirement of the algorithm should also be analyzed while analyzing the performance of the algorithms. And one interesting thing that we can do is, that can be done, is to identify good and bad implementations of the same algorithm, because an implementation which uses multi-qubit operations, arbitrary phase operations between 2 qubits is not a good implementation. The implementation which is which can be done more efficiently on a given hardware using less multi-qubit operations is a good implementation. So these are some of my thoughts on this topic. I am not exactly in quantum algorithm area. I am more focused on modeling of spin qubits and devising quantum control techniques. But from that perspective, these are my thoughts on this panel on quantum algorithms and quantum error correction. And I'm sorry for not being able to join in person because of another conference. I'm also sorry to keep you sitting at this time, and thank you, everyone. Thank you.
Thank you, Dr. Punia, for your thoughts and insights. Now, floor is open for the questions. We may take up 2 questions. It's already been late, so we may take up 2 questions maximum. Yeah.
Hello. Yeah, Dr. Punia, thank you for nice talk. In the quantum computer, when we submit a circuit, this processor does this thing, quantum transpilation, before running it on actual device. So I believe that transpilation solve most of the problems which you address.
Yes, transpilation means basically making it more compatible with the underlying hardware in the system. But that might not be feasible when we are having, let's say, a composite realization of hardware. For example, in a QPU, if there is a spin processor, spin qubit-based processor is sitting along with a superconducting qubit-based processor, and they are talking via, let's say, photonic qubits, then I think what I said might be more relevant. But at the moment, as you said, that's true. That's the case.
Thanks.
Yeah. Any other questions? So thank you very much, and thank you for sustained attention. And we end today's sessions, and we have now you take word from there.
Thank you, sir. Now I request our session chair to felicitate the panelists. Thank you. I request Colonel Ekenath to felicitate Mr. Aditya. Thank you, sir. With this, we come to the end of the first day of Symposium. Let us meet tomorrow at 9 a.m. IST to listen some more exciting sessions, continue our journey over the Symposium. Good night and take care. Dinner is served at Rooftop Cafeteria. Thank you.